energy takes away the best of me. I remember when we were young, you made friends with the gun. You didn't leave, fell in love with the streets. September you were out, now we're all the way in February. Bittersweet, these roads ain't for the weak. Oh, these bitter streets, don't fall asleep. Bitter streets, these roads ain't for the...
Hey, hey, hey. Is that 3? Yeah, it's 3 or 6. 3, 2, 1. Lovely, lovely, lovely. 3, 2, 1. 3, 2, 1. Give it a go.
So much of us is hidden under cover. And if we can't do this together, speak about all the love you started out.
We'll get you going, wouldn't it? Sweet. All right, good morning, everyone. It's cultural protocol that the last person to sit down has to do an interpretive dance of everything I'm going to talk about. Still a bit early in the morning, hasn't registered yet? Well, for those of you that are here, my name's Brendan. I'm the cultural representative and cultural educator for a metropolitan local Aboriginal Land Council. And our Aboriginal Land Council's under Australia's Land Rights Act of 1983. We are the cultural authority. We are the guardians, custodians and caretakers of lands and waters within our boundaries. Our boundaries in Sydney is one of the biggest, and I'm here this morning to perform a tradition and a ceremony of welcoming you to country. Now, the welcome to country is not a welcome to Australia. Our definition of the word country is in reference to our homelands. We more or less, we have a nation within a nation. We have possibly over 500-600 different language groups within Australia. different groups, different tribes that have their differences. We dress differently, our diet's different. But one of the core things we have in common is we all refer to our homelands as country. We have more Aboriginal nations in Australia than anywhere else in the world. So every year, I currently reside up in the Blue Mountains, and my homeland, maybe 12, 13-hour drive. But every year when I go home, I always say, I'm going back to country. So the welcome to country is not a welcome to Australia. It's a welcome to the lands that you've gathered on. The traditional lands that you've gathered on here this morning belong to Gadigal. Gadi means grass tree. Gal means people. These were the lands of the grass tree people. One of 29 tribes that make up what we call the Eora Nation. And the boundaries of the Eora Nation start from the ocean, and they're surrounded by three of Australia's most beautiful rivers. We have the Hawkesbury River, the Nepean River, and the Georges Rivers. In between those three mighty and beautiful rivers, there was 29 tribes that made up the Eora Nation. But the name of the tribe we're gathered on here this morning is Gadigal. There's a story, look, a welcome to country is no different than welcoming strangers into your house. Except our house, it can take you days and weeks to walk from one end to the other end. Traditionally and to this day, we don't walk on each other's country unless we're welcomed on each other's country. Prior to colonisation, you could get into a lot of trouble for walking on someone else's country unwelcome. There's a man over in Narrabeen on the northern beaches. He's known as the Narrabeen Man. This man, when they found him, it's the world's oldest recorded homicide, 20,000 years old. He's a result of not being welcomed onto country. I'm not saying that's going to happen today, but this is how important this welcome to country is for us. It's as I said, it's disrespectful to walk in each other's country without being welcomed. Traditionally, when I'm welcomed onto my neighbour's country, there are a few things I need to know. Obviously, and for me, this is common sense. I need to know what food is available on your country. I need to know what your totems are, because we don't eat our totems. We've lived here for over 60,000 years and never wiped out any species whatsoever due to our totem system. So I need to know what your totems are. I need to know where your sacred sites are that I'm allowed to visit and not allowed to visit. I need to know where your sacred waters are I'm allowed to drink from and not allowed to drink from. And the most important thing of all is I need to know where your toilet is. These protocols are no different than when you welcome strangers into your house. You all have an expectation of when you welcome strangers into your house. You expect them to respect your property and everything in your house. You show them where they can sit, where they can't sit, where the food is, where the toilet is. And you all have your sacred sites in your house, your no-go zones. Your bedroom would be a sacred site. It's a no-go zone. You don't welcome strangers into your house and show them where your bedroom is. Sometimes ceremony takes place in that room. Sometimes it doesn't. Then again, some of you might welcome strangers into your house and show them where your bedroom is. That's okay. You don't walk into your neighbour's house and help yourself to their food and have a sleep on their bed. Again, some of you might. I don't know what type of relationship you have with your neighbour. But this is what our welcome to country is. It's a ceremony really based on respect. Respect for country and respect for each other. It's always an honour for me to perform this tradition of welcoming you to country. This morning I'm going to share with you the story, the creation story of Sydney Harbour and all the rivers that run off it. Sydney Harbour is a flooded estuary. We have carvings in the water. in Sydney Harbour. Our people believe that Burra, the long-finned eel, Burra raised the waters to punish the local people, and they weren't following their law. There's an island there called Goat Island. In our language, it's called Meemau. Meemau is actually the head of the eel. When Burra raised the waters, he moved around on the top of the lands, the waters followed him in. He created all the rivers and waterways that run off Sydney Harbour. When Burra finished his journey, Burra finished at a place called Parramatta. Parramatta. This means place of many eels. Every year, Burra swim down the rivers and waterways into Sydney Harbour. From Sydney Harbour, they go all the way to Vanuatu, they turn around and come back. This is what we call a songline. Songline. Prior to colonisation, these songlines were ours and they were our responsibility to look after them. Everyone lives here now. It should be everyone's responsibility to look after them and to keep them alive. On behalf of those Gadigal ancestors, because we know their spirits are still in the lands and waters, their songlines are still alive and thriving. On behalf of Metropolitan Aboriginal Land Council, our board and our members, it gives me great honour to welcome you here this morning. Welcome to the lands and waters of the Gadigal, and I thank you for having me.
A big thank you to Uncle Brendan there. And Uncle Brendan just made a little promise to me just now that he'll return on Wednesday morning before the keynote and come with his didgeridoo. So please, if you're here on Wednesday morning, please come 15 minutes earlier than the published schedule. I'll update the webpage to reflect this, and we'll hear Uncle Brendan with the didgeridoo. All right, now on to the conference. My name's Steve Blackburn. I work at Google here in Sydney and also on faculty at the Australian National University. And it's my very great pleasure to welcome you to this wonderful city. This year I'm General Chair for CGO, whose turn it is to lead this fantastic federated conference. And I've got to say, this federated conference is really a wonderful thing. I'm very proud that we work so well together, and I think there's a great future for this federated conference. On stage with me, Tony Hosking, who's General Chair for PPoPP, and Shui Wen Leon Song, who's the General Chair for HPCA. We've collectively done our best to make sure this conference is a success, and if you have any feedback, like if there's anything wrong, please talk to these large guys over here. If there's anything good to say, you can come and tell me about it. I want to make a special call out to our volunteers. You would have all seen them. They're all wearing colourful Indigenous shirts downstairs. And please take the time when you see them to thank them. They've volunteered and they're helping out with the conference and doing a fantastic job. So when you they're not in the room, so no need for any applause yet, but when you see them in person, please take the time to say thank you for their service. And I wish to finish this welcome by thank you for coming all the way to Sydney. Most of you have come a long way to get here, and I'm eternally grateful for the fact that you've travelled so far, and believe me, I know what it's like to travel. So I thank you very much for coming all this way to Sydney, and I wish you a terrific conference and a great stay here.
I just wanted to steal the mic for 1 minute before we get the proceedings on the roll. This conference would not have happened except for this man standing here. We were in quite a dire straits at the beginning of last year. It wasn't clear whether the venue was going to be even on the cards. It wasn't even clear that Sydney was on the cards. And I just want to thank Steve Blackburn for all the work that he has done to single-handedly pull this off. Leon and I have a great debt of gratitude to Steve, and I really thank him for what he's put into this. Thanks, Steve.
Thank you both. All right. Now, it is my particular pleasure to introduce our opening plenary keynote speaker, Professor Saman Amarasinghe. Professor Amarasinghe is the recipient of the 2025 ACM IEEE CS Ken Kennedy Award. And he's going to present his award lecture here. And I'll now take a moment to introduce the award and to read some of the citation for the award. Ken Kennedy, who's on the screen here. Ken Kennedy was a leader and pioneer in the field of high-performance computing, and he left a prodigious legacy. At a personal level, I never met Ken, but I know that he coined a term that I've lived with and made a motto for my career, and that is the idea of abstraction without guilt. And this award is in memory of Ken and his legacy. The citation for Saman's award is for contributions to programmability and productivity in high-performance computing, together with significant service. For technical contributions, this nomination points to a number of projects that have had significant impact and are well known to many in this audience. Streamit, Halide, Taco, OpenTuner, and early work on applying machine learning to compilers. One of the most significant of these is Halide, which is used in a number of products, including Adobe Photoshop and Camera Raw, Google Pixel Visual Core, and the Qualcomm Snapdragon Hexagon DSPs. So he's had a real impact on products that many of you are actually using. He has a startup. He had a startup, Determinia, a runtime security startup that was acquired by VMware. So he's had a real impact in terms of startups as well. But aside from these amazing technical accomplishments, which you'll also see reflected in his publications, incredible publication record, Saman's service has been unique. It includes bringing technology to the developing world, including his startup from when he was a graduate student, Lanka Internet Services, and his role as faculty director of MIT's Global Startup Labs, GSL, for over 15 years. GSL has conducted over 100 summer programs for local university students in 10 developing countries, including Uruguay, Uganda, Ghana, and Sri Lanka. These summer programs train students to start information technology-based startups. Many companies that got their start at GSL, for example, Prep Class in Nigeria and 4Access Solutions in Sri Lanka, are thriving. Often service is also interpreted to mean mentoring, and of course, Saman has a long list of students who've gone on to faculty positions to mentor their own students and impact industry. There's a long list of such people. And with that, I would like to welcome Saman to give his keynote talk and award presentation at our conference. Thank you, Saman.
Thanks, everyone. First, I want to thank Steve. This award is normally presented at supercomputing. And I ran into Steve in Singapore a few months ago and casually mentioned that it would be nice to get this award at CGO. Why? I find CGO to be my home conference. I can actually understand most of the talks that happen at CGO, unlike other places, and I can probably agree with most of them, and I actually also published a lot of papers here. And Steve just went and made it work. So thanks so much, Steve, for doing this in here. So it's a really honor to get an award like that. However, get an award named after Ken Kennedy is really special. When I was a young graduate student just starting, Ken was the pillar in our community, especially looking at automatic parallelization community in here. And if I just think a little bit, I think start of my career, lot of things have to be attributed to Ken's ideas, Ken's vision, became part of my vision and my drive. And that was part of my thesis that became in there. And also, if I look at that time, one of the most fun things I can remember was my interview at Rice. Normally, when you go through academic interview, nobody considers it to be a fun thing, that you memorize it as a fun thing. But Ken made my visit to Rice so much fun. We had to have half an hour meeting that we blew off and talked for almost an hour. We talked about very conceptual, high-level, aspirational things, all the way down to perfect benchmark suite, line numbers, and loops, and how we are parallelizing each of these things. I felt so validated that somebody like Ken was appreciating the kind of gritty stuff I am doing. I think it gave me a huge amount of confidence. So thank you so much, Ken, for that early push. That was my early push. However, I wouldn't be standing here just because of that. This award actually belongs to so many people. Being at MIT, you are so lucky. I'm so lucky to be part of, have amazing group of students and collaborators. I have had collaborators from around the world in here. Had huge number of MIT undergrads, amazing people that lot of times humbles me, be part of that. So lot of ideas, papers, sweat, and blood and tears went into a lot of that work. Came from these people. So this award is, I think, a lot of these people equally has a share of this award. Thank you, everybody. So what I'm going to talk about today, I want to, normally when people give a talk like this, they tend to celebrate the successes. I am kind of going to talk about a little bit of failure, which I hope you guys don't throw me out for saying these things. We'll see. So I want to start from the beginning. When computers came about, many different companies started building their own computers. They were different because there was no common idea. Everybody has their own separate ideas. And like if you want to write matrix multiply in all these computers, you have to do something very, very different. There's a really good reason for this. Because all these machines had an extremely diverse set of architecture. Their registers were different. Some had normal like 16 registers. Some had 1 register. Some has vector registers. Their instruction execution, even the execution models were different. What you need to do to get performance were also very different from something like register allocation and CISC operation optimization for System 360 to dealing with the page 0 optimization in PDP-8 and vectorization in Cray-1. So no wonder you need to write different programs in there. Then Fortran came. You can write one program and it will run everywhere. I hope you have read the first Fortran paper. If you haven't, I strongly suggest go and read it. It's actually a humbling thing to read that paper because what you find is many things that in modern compilers today were in that first compiler. They dealt with things like basic blocks. They dealt with control flow graphs, loop analysis, all these things that now we think are very modern were in part of the first compiler. So it's kind of interesting to see how much they got right in the first compiler. So in fact, for that, John Backus won a Turing Award very deservingly to build basically. These were the giants of the time, basically changed how people program. And in fact, not just John, Fran Allen got a Turing Award for all the optimization she did. What this compiler did was they were able to abstract out all the architectural details and without a performance load. From that point onward, many people just wrote Fortran, and that code compiled on many different machines and gave performance. That's all you had to do. That was an amazing achievement, what was happening before to what Fortran did. So this is a great start in there. Then I came to this scene around 1990s as a graduate student at Stanford. And at that time, the biggest compiler out there was the GCC compiler. It has this structure where you take the program and you go through multiple parsers with intermediate representations, lowering it until you get this assembly code, this process in here. And across my corridor, there are a bunch of people working on NLP system. basically taking a text and translating it and doing different things to text. Even though the context was different, the structure of the NLP systems were very similar to GCC. In fact, GCC was pushing the hardware limits of these days, and NLP systems was pushing hardware limits. So we had a lot of productive conversations and learned from each other how to build this infrastructure, how to optimize this infrastructure in there. That was amazing in here. So now, if you bring us to today, if you take me from my chair at Stanford and immediately transferred me to today into my office at MIT, not that I program that much these days, but I will be shocked at probably the resolution of my screen and all the cool things that the editors can do. But within a few hours, I will be familiar with LLVM, and I probably can even understand and do certain things within that and probably go into the guts and figure these things out. So what that says is the compilers haven't changed that much. Contrast that to NLP. If you take somebody that was my colleague during Stanford days and transfer them today, first they would be amazed at what NLP can do today. They were struggling those days, and today it's just doing amazing things. But if they were shown the guts of NLP system, it'll be completely alien to them. They won't understand anything out of it. It was right now the NLP system today. I have nothing like the NLP systems in the 90s. So what that says is NLP has gone through a huge revolution. Compilers haven't. What does it mean? That means, are we built such a good thing that we don't have to do anything new? So you look at state of the art of current compilers. Where are we with this LLVM type? I'm not just harping on LLVM. This is the general compiler community. How are they doing? First of all, compilers are huge. If you look at something, some of these compilers, millions of lines of code, thousands of people are using on that. It's probably still one of the largest and most complex software systems out there. It was like that before in the 90s, same thing in here. Also, it's way behind. So if you look at something like x86 architecture, Intel spends billions of dollars adding new instructions. And the compilers natively don't even take advantage of that. They don't even know how to generate some of these codes. To give one specific example, this add sub instruction was introduced by Intel in 2004, a great instruction. It was only 2014 that LLVM is able to generate that instruction natively. So that is not what I consider fast. And then how have we contributed to the performance? I mean, we all know Moore's law. For a long time, every 18 months, we double the performance. And Todd Probstein came up with this thing. Compilers have improved performance 2x every 18 years. And in fact, he came a corollary to that saying, oh, that was too optimistic. We don't even do that. So this is a kind of a sad thing, because I feel like this is what I spend my entire professional career building with compilers. And if you really look back, am I being extremely happy that we have done a lot? Probably not. I feel like we haven't made that much progress. And I'm telling it to my friends, because most of these, okay, people who are only on CGO, others don't laugh at us. But CGO community, I feel like we could have done more. You guys are probably, most people here are new, so they probably don't bear the responsibility. But I feel I'm responsible because I was there from the start of that time period. And this is not a good reflection of how we have spent this time. So what has it happened? So what has happened today? So assume you want to get the best performance out of matrix multiply. So you can say, you can write that code right top in the small in C, but nobody does that. If you want to get best performance in an Intel CPU, you have to write this piece of code. Okay, all these like hand optimized. On the other hand, if you want to get performance out of NVIDIA Ampere, you have to write even a larger piece of code in here than this nice 4 lines in here. And NVIDIA Blackwell, not only you have to write even a larger piece of code, now we have to do embedded assembly. There's PTX assembly embedded in here. we basically have gone back to pre-Fortran race again. Every machine, different piece of code, and we are even writing assembly in here. This is not good. And I don't think as compiler community that we can be happy about where things are. And this is a very long walk backwards. So the question is, can we get back to the ideals of backers? Can we get into a single program abstraction that can abstract away all the architecture detail? Can I write that piece of code up there in the top left corner and expect to get really good performance on every machine that's out there? That should be our goal. So I believe we really need to rethink compilers. I think the current pace is not going to work. So what I'm going to do next is give some of the ideas that I think what we can do and focus on one thing. We need to find better abstractions. So if you look at why, starting from Fortran, they did really well, because they found really good abstraction that can capture very large class of programs, but got rid of all the minute details and that can focus on the most important parts, including things from the basic blocks, stuff like that, and later things like SSA, data flow analysis. They did the right thing, and they are very powerful. Even something like register allocation. If you just look at that problem, it's daunting. But then if you look at abstraction like graph coloring, it's not only simple and powerful, it can be run really fast. And we have been doing it for few, but for the modern machine learning, I think we haven't discovered or come up with a lot of abstraction necessary. I think there's a really good need for coming up with right abstractions. For me, compilers is something with few abstractions that capture a large part of it. It's not like you have millions of abstractions. We can't do that. We have 3-4 abstractions that capture everything. So that's very important in here. Another thing that galls me is, from the time I can remember, we have developed many different algorithms, faster and better algorithms. Things like integer linear programming, SMT solvers, other theorem solvers, deep learning. None of these things have really seeped into a traditional production compiler still. Yes, there are papers published out of using most of these things, but it's not used in practice. We should get our traditional production compilers to a lot more deep techniques that are a lot more capable techniques. I think these techniques can solve some of these hard problems, so we should do that. Another thing that bugs me is, if you look at something like circuit layout, it's a very hard problem, but they solved it not because they had amazing abstraction, by brute force. It's run on thousands of machines for multiple days, and they do a job that's still production use. For us, compiler people, if the compiler runs for more than 5 seconds on a CPU, we said, whoa, too long. We have to stop. We don't do that. I want not -03. I want -0 million. I want to be able to say, if I want to solve something, I will run it on a cluster using everything, GPU, CPU, every power for a week, and we should be able to solve that problem. If we try all these things and fail, and hopefully we'll know why we fail. If we find some foundational reasons why automatic optimization is not good, humans are better, I'll give up. I'll be happy to say, okay, we tried as a community, we have reasons why it doesn't work, okay, we can give up. But this is a too important problem to give up without trying, as we are doing today. We haven't tried these things, we haven't tried all these techniques, I haven't seen that, so I am imploring our community to go try these techniques, push the limit of it, and see what we can do, and hopefully we'll be surprised, we'll get back what we have lost in here. So that is my negative part of the talk, so hopefully people are going to harass me afterwards. You can. I'll try to argue my case. So the next I'm going to do is spend some time saying, okay, the positive part, what do you think we can do? There's a lot of things we can do. I am going to focus on deep neural networks and large language models, what these systems can do for compilers, because this is what's in my mind these days. So if you look at a compiler, You can think about this as you have front end, you have optimization, you have code generation. This is the internals of compiler. But when you're looking at something like large language model, you have to look at the entire big picture. What that means is even program, there's a human who takes a problem and write the code in here. Also, if you look at what these things are, somebody takes a language manual and write a front end. Somebody takes a huge architecture thick manual and not one person, multiple people write the code generator. And probably somebody takes something like a Dragon book or many other things and will write the optimization part in here. So this is the entire compiler ecosystem that happens today. So what can be in the future? I believe there are 3 interesting possibilities. One, can LLMs augment the traditional compiler? So you build a traditional compiler, there are large part of the traditional compilers that machine learning and LLMs can do better and can provide features that currently not possible. So I'm going to touch on that. Second thing is, compilers are huge. It takes a long time to write these compilers. Can LLMs help us generate part of the compiler? So we as humans don't write it. LLM actually write part of the compilers. This is interesting part too. The third and the most scariest part is, can LLMs replace the traditional compiler? So you don't have a traditional compiler. As we know, LLMs do the work. So this is interesting, and I'm going to address this at the end. So let's go with the first thing. Can LLMs augment the traditional compilers? So what I'm going to do is I'm going to talk about a bunch of projects I have worked on for a long time. If you look at the machine learning part of these talks, you'll see they are ancient because machine learning changed that fast. On the other hand, if you look at the compile aspect of the project, they're not ancient because compilers haven't changed that much. So even today you can do that to the compiler, that part exists in the compiler. So you'll see that difference, the speed of different technology movement in here, which is kind of interesting. So the first thing I want to talk about is, okay, can I change what compile optimization is about? So I'm going to go back a long way. In 2003, we published, I believe, kind of the second paper to deal with machine learning in compilers. The first one dealt with outside the compiler, phase ordering issue, how to phase order different compiler parsers using machine learning. And we are the first to delve into the compiler and say, can we use machine learning? So what we did was, if you look at a compiler, even today's compiler, there's this thing called priority functions. What that means is you have a choice. You can do A or B. So you're so far away from code generation, you have no idea which is profitable, whether A will be profitable or B will be profitable. So you have to make a decision with very little information. There's a lot of choices, you have to choose one. And this is everywhere in the compiler. From scheduling, graph coloring, hyperblock formation, there are a lot of things. It's about, I have to make a decision. I have a lot of choices. Which one do I choose? I use a lot of techniques. And this is where, at that time, I thought, we experienced compiler people use our intuition, knowledge, experience, and come up with these choices. And even that time, I was humbled to say, the data-driven techniques can really beat the humans in here. And the other thing is all these priority functions are legal. So this is ancient. Machine learning was just like a small subfield those days. So we use what we call genetic programming. Idea here is we find bunch of features out of a program, extract bunch of properties, and randomly generated a function. And that function decides the priority function. And you generate a bunch of these random functions, and then you iterate through random functions, finding which ones produce better code, and keep modifying them, sometimes randomly, sometimes things like hill climbing type method in here. And to our surprise, they did really well. This is optimization that was at that time somewhat new. When you have a condition, you have to make a decision. I am producing a branch instruction, or I am going to do conditional execution. Branch instruction basically only do the then or else part, but there's branch misprediction overhead and a lot of overhead if you don't do it right. Conditional execution, on the other hand, writes smoothly, but you have to write both sides of the part, so you are doing extra work. Depending on the many things, the architecture, how the predictable the branch is, all those things, you get different costs in here. And it's not clear which one wins. So we just learned that. And what we found was what we learned actually did really well. And at that time, we were hoping machine learning will give some insight. So we looked at what function it created. And we could make head or tail out of that function. And today, I guess nobody's looking at the hidden states, trying to understand what LLMs do. We have given up on that. But those days, we were hoping to do that. But the interesting thing is we still get good performance. But then we said, let's try something that's almost established at there, which is register allocation. So at this time, there were hundreds of papers on register spilling, very complex algorithms. Nobody was studying because we considered it's done deal. We know exactly how to do that. And we did that, and to our surprise, we were about 3% faster than the best known algorithm. Yeah, 3% looks small, but for something that is so well studied, that was a surprise. So even from that point onwards, I start doubting my ability as a compiler engineer to do the right thing versus data-driven methods in here. So I had tried many different data-driven methods from then onwards. One of these things I want to talk, the next thing in here, which is okay, hold on a second. Let me get. So can also a large part of a compiler be replaced by a machine learning part? So the idea there is auto-vectorization is a large part of a compiler. And right now, there's a lot of human effort goes into this. I mean, if you look at LLVM logs, there are like tens of people spend their entire careers building auto-vectorizers. Okay, can you just learn that? The first thing is, can I just get the program, feed it to some machine learning system, and produce the output code? That seems very exciting, but there's the unfortunate fact that as a compiler people, we have trained everybody to expect 100% correctness. And we can't get to 99.9 correctness and claim victory. People expect the program, the compiler, to actually produce exactly the same program that went into that and do the same thing. Not fun, but we have to live with that. So LLMs or most machine learnings are notoriously stochastic, not produce the correct thing. So this doesn't work. So what can you do? So this is the time of AlphaGo. And what we realize is, even within the rules, there are a lot of choices. In AlphaGo, every stage, there are millions of different moves you can make, or thousands of different moves every time you can make. And then the complexity is finding the right move. And if you find the right move and iterate through that process, you can be a world champion. If you do something stupid, you'll be like a normal alpha player of Go. So there's a lot of techniques going on there. Can you do the same thing? So when you look at vectorization, you can look at a program and say, OK, how many statements can you merge together to create a small vector? So you can build the vectors incrementally. I can say, OK, at this point, I have A1, A2, A2, A3. I can combine these things to form a small vector. So I have a lot of choices. The interesting thing is which one you choose. And then what you can do is you can choose one and do that, and then iterate. Then what you can do, that's a new state, and then we can move back and keep iterating over that until you get the right answer. And then your reward is, okay, how fast your program ran. So you have to do this. You're not making any incorrect things. There's always correct transformation. You have a set of correct transformations. The difficulty is figuring on what to do and do that. And we basically use a Markov decision process to do that. Just before this, we built this system called GoSLP, where we use integer linear programming to find the optimal vectorization strategy. So this is great. You find optimal strategy, so that should be the best. The problem with that one was it was both slow, and if the program was little large, like if the basic block was more than like 30, 40 instructions, it just didn't finish. For small programs, it was great. Large programs, it didn't work. So this was a great experiment, great research, but it was not really applicable. So we said, hey, we will use GoSLP to train this system. So the idea there is we need to find valid choices. So we found basically partially vectorized program graph in here. and then say, okay, what of these things can be merged together, these subcomponents of the graph, and then we can, once we merge together, we can produce the merge graph, and there's a new state, so we can iterate on that. So now we can move this graph in here and iterate. And so we use greater graph neural network to do this, and then we was able to train a policy network to do that selection. So we had, for every of these graphs, we had the right selection that we understood using GoSLP, because that's optimal selection, and we trained that a policy network. So if you look at performance, this is GoSLP's performance against LLVM. In bunch of things, it was doing better than LLVM. To our surprise, when we did this Vimal machine learning, it was doing really, really well. For many things, it was matching or exceeding the performance of GoSLP. Just a learned system. It just learned this thing. So this was really good, and we were very happy. But now, if you are paying attention, you are going to ask this very important question. Just 5 minutes ago, I told you GoSLP was the optimal solution. Okay, I am building the optimal solution. How the hell am I going to be faster than optimal? Optimal is supposed to be optimal. And I am running something faster than optimal. That seems very strange. That doesn't mean optimal is actually optimal. In fact, if you look at some cases, one case, it's even worse. The optimal is worse than LLVM. So what is going on? Why is optimal not optimal? The problem is optimal out of what? The interesting thing is optimal out of some kind of a cost model. Okay, you have to calculate optimal. And in here, we had a linear cost model. And you all know you can't have a linear way to figure out how architecture runs. Architecture is a lot more complicated. So here, what I'm showing here is a bunch of unique loopness. And left-hand side, the loopness that got optimized the most. Right-hand side, little optimization. Blue line is what LLVM did. And the red line says for each of those loops, what we were able to do in GoSLP. And most of it, of course, we are beating LLVM. But there are certain things we are worse than LLVM. Not because optimal is wrong, but our cost model was not right. So this led us to looking at cost models. What we realized was the cost models that was out there was really bad. So there were cost models like LLVM, MCA used in LLVM, make a lot of decisions in here. Intel have its own cost model called IACA. They were basically way off the real machine. So assume we give it a basic block. Assume it's deterministic. That means all the data is in the cache. There's no branch mispredictions. Everything is hot. And you ask how many cycles will it take. And you have to predict that. The problem is this Intel beast in here is very complicated. You have to figure out all these things happening in there to predict how much time it's going to take. There could be bypasses, there could be interlocks, there's so many things going on there. Worse, since Intel is proprietary, certain things are not even publicly visible, what's happening in here. So this is a hard job. So in order to do that, some poor engineers has to go through these huge, thick manuals of Intel instruction set. And it's not even clear. Like, for example, the add instruction is described in one manual, saying, okay, here's all the conditions, how many cycles add instruction take. Then, completely different manual says, by the way, if the add instruction, if the inputs are 0, there's this bypass that runs that instruction 2 cycles instead of the normal, whatever, 8 cycles. That's in like 1,000 pages, it's even a different document. So you have to know all those things to actually come up with the cost model for add instructions. And something like LLVM MCA did this thing and came up with thousands of lines of these different costs that it identified for each instruction in here. So this thing is tedious to develop and maintain. Huge number of things, because as new instruction added, you had to do that. There's a lot of human error. There's a lot of modeling error. And to add salt to the wound, the LLVM's Intel performance model was something Sony produced using AMD hardware. Long time ago. So Intel is building this amazing new hardware with new optimizations. LLVM still look at the AMD hardware to predict how to run this thing. And so no wonder you don't get the best instruction sequences in there. So this doesn't work well. So we said, hey, can we use machine learning to solve this? So what we did was a system called Itamal. And there, what we did was, given this basic block, can we use some kind of machine learning system to predict its cycles, both fast and accurate? So what we did was, we have this instruction sequence. We didn't do any featureization. We directly went and tokenized those instructions and came up with embedding for each of these instructions in here. Fed that into the best thing those days, which is LSTM. And for each instruction, I got LSTM trained to do that. And then you fed all those LSTM things into a second LSTM that produced the throughput prediction in here. So 2 levels of LSTM, just this thing in here. And training this, we basically collected like millions of basic blocks out of non-benchmark suites, ran them, measured their time, got the ground truth on a different architecture, and then we can train the neural network out of that. It's pretty easy to train the neural network using backpropagation in here. The cool thing here is our accuracy was 2x of what's out there those days. And for example, even Ivory, Ayaka didn't even exist. They haven't modeled it in there. When it existed, we were 2x better, and a new architecture comes, no big deal. We have the basic block set in there, and we run it. We train it. Within a couple of days, we have a new cost model. And in fact, right now, Google is using this methodology in their XLA compiler to make decisions in there. They are using their trained cost models in here. So what that means is certain things that are really cumbersome, that doesn't propagate very fast in modern compilers, we can use data-driven ways and really do a better job. So now I'm going to switch a little bit. Can LLMs generate a traditional compiler? Traditional compilers are hard. They're big. Can we do something? So I'm going to talk about this system called Vegan that basically we again generated a vectorizer. So our group, we were building a vectorizing compiler. And we want to build a really good one. And of course, we had to generate code for x86, SSE, MMX, AVX, AVX512, all those new versions, thousands of instructions. The Intel has had that, we have generated that. So there are so many instructions in here. So I was telling my graduate student, I have one student doing this, okay, we need to do this. And he was like, there's no way in hell me alone can go through this 3,000 instruction and code everything up. And I was like, you are lazy, go do something. You had to do that. And he came up with this ingenious idea. He realized the Intel instruction manual has a very clear description of what each instruction does. Okay? Can I use the Intel instruction manual to generate my vectorizer and using that information? And that's what we did. And the neat thing about that is, in fact, nobody had tried to execute the instruction manual. We found a lot of bugs in the instruction manual because if there's a bug, humans won't catch it, and we are trying to run it, and we found issues in there. But they have done a good job, not that many bugs. So now what we can do is that generated one, we can give a normal input program and to produce a vector output in here. A new architecture comes. Hopefully I have a new manual. Within a few hours, I have a new vectorizer for that. So let me give you an interesting case study. This is a very important kernel out of TVM in there, doing vector matrix multiplication in here. So if you feed this kernel, this was a few years ago, into ICC, it looked at the kernel and said, wait a minute, these are all small loops, I can unroll everything. So it unrolled. But unfortunately, ICC don't have a SLP vectorizer. It didn't know what to do after unroll loops. So this left unrolled, no vectorization, pretty bad performance. GCC, on the other hand, did a little bit of a better job. It figured out some vectorization, got 50% performance. Clang LLVM is doing really good, 2.2x performance, and produced this code. And we fed this into our system, Vegan. It produced 4 lines and was 11x faster. Not because we had amazing new optimizations that Clang LLVM did. In fact, we didn't do half the things Clang LLVM doing. But we had every instruction because our system basically generated the latest instructions into our vectorizer. There was a dot product instruction that recently added by Intel. And Clang haven't still gotten around to identifying dot products and producing that instruction. And we were doing it. And it was not the simple thing. There's some complexity to set the data right, but we were doing all this thing automatically. And the minute we have the right instruction, 11x faster, very limited code, voila, we were doing the same thing. And I believe this is important because architecture development has accelerated. If you look at this, there's so many people are building new accelerators, different changes. It's in a much faster scale. And in fact, there's a lot of work that has gone into reducing the development time of new architectures. There's a lot of work, a lot of new tools that's doing that. But the Achilles heel of all these systems are going to be the compiler. So you get I get that. I get calls from many startups. Suddenly they realize, oops, we need a compiler team. They can handwrite few kernels, but then what do you do? You need a compiler, and this architecture is very different, and building compilers is really hard. So we need systems like this that when a new architecture comes, you can develop. And for architects, think about you want to add a new instruction. How do you know that instruction is useful? If you have this system, within a day, I will be able to add that instruction into my compiler, compile a large benchmark suite, and tell you how many times I can use that instruction, or what changes I need to put that instruction. That will help architects too, so if you have a system like that. So we need to use this data-driven machine learning type systems to actually generate than going and trying to write this in human. Okay, now I am going to get to my last part of the talk. Can LLMs replace traditional compiler? In fact, this is a scary part. Because this, if they are completely successful, my entire career is washed away. Everything I did, I mean, this has happened to many other fields. Everything, all the things they publish is no longer in use, and they are in the history bin. So this is interesting thing. In fact, there are companies doing that. This company, the standard kernel, what they're doing is they are taking high-level English description or just Python description of a program in there, and they are generating CUDA and PTX sometimes faster than the NVIDIA library code with no compiler. It's just feed in the high-level program into like a LLM with some other things, LLM things, kind of things like good prompts and stuff like that, and some pre-training type things, and voila, they're getting the results. So this is scary. But I don't believe that you can give any 1,000-line C function and expect a fast assembly yet. However, we should be able to help this process, because we as compiler people for a long time have done a lot of work for analyzing front ends, back ends. So for example, I can provide an agent that look at the program and say, hey, I can tell you something about the complex semantics of that program. I have a lot of interesting analysis like data dependence, data flow analysis, stuff like that, and tell people, the LLM, about what they can do and cannot do. I have really good information about the backend architecture, semantics, instructions out there that I can use that to feed that. So LLM process normally is iterative process. If you are writing something with LLM, it will produce English. You will look at the English, you will comment that English, and you will feed it back. And it will iterate until you are satisfied. If you are doing a program, generating program using LLM, again, it will generate the first program. It's probably buggy, don't do exact same thing. You give feedback, you iterate until you are happy. What do you do with a compiler? Because you have input, which is a program, output, which is assembly. So what is the right IR that both for traditional compilers and LLMs, how do you communicate within that? Oops, what happened? Okay, hold on a second. I think it's my end. Am I back? Yes. Okay, small technical glitch. So how do you communicate? What's the intermediate representation? It's not Python. Yes, Python will represent input program, but as you keep transforming the program, lot of things happen to that program that I can't capture in Python. So I can't use Python as a communication mechanism. It cannot be assembly because that's way too late. If I want to communicate early on, assembly is not the right thing. It's done everything, and I can't communicate that. It's not LLVM IR. That's way too complicated. We are trying to help the darn LLM. If the most of LLM's time is spent generating LLVM assembly, it's not helping it. It's just hindering. Assume we give a budget to the LLM and said, hey, use that. It's not going to use most of the budget generating LLVM IR. It will say, I'll try to do everything myself using hidden context in here, hidden state. It's not English. That doesn't work. So what's it? This is a question I'm thinking right now. I have Zoom calls with my students last week, basically discussing that. It's even more interesting. Who's going to design it? We as human compiler engineers, we know a lot how program represent what matters. Should we design this thing and give it to LLMs? Or is LLMs going to design it and give it to us? Or there's a hybrid process. These are very interesting questions. And I don't have any answer, but I think we need to answer these things and come up with these things. This is very interesting right now. Another interesting thing that happens is once we give control to LLMs, you lose notion of correctness. Because in the compiler, we guarantee we work very hard to make sure it's correct. And if we just outsource small parts, we can still guarantee correctness through the compiler. But now LLM is doing all the work. How do you guarantee correctness? So we need to look at that, and I think we have a couple of ways in doing that. These are very still early stages. One thing is, while LLM produce the program, we can also ask LLM to produce test suites. And then what you can do is run these together and validate that. In fact, 99% of all the programs we use today are validated using test suites. So everything, even the complex, like assume this presentation software, there's no proof that it's correct. Probably Apple ran huge number of tests and they said, okay, it's ready for release. That's what they do. Even more exciting about proving correctness. So you can basically use, because humans hate to write proofs. You write your program, you said, okay, I'm done, the program works. Why the hell I have to spend trying to write proofs in here? Nice thing about LLMs is still, they are not complaining that much. So we can tell them, okay, you also have to write a proof, and then we can write some kind of core outside proof validator to prove it's correct. And there's a much better chance we can get a large chunk of code or large chunk of compiler build that actually proved correct. That will be even better than everything we are doing today. So there's a lot of interesting things in here that's very early stages to deal with the incorrectness issue. So I'm going to talk about one more thing as my last part in here, which is the biggest problem with LLMs, they hallucinate. As LLMs increase, the hallucination haven't gone down. It's a foundational issue with LLMs in here. So how do you deal with that? So one thing we realized was hallucination is stochastic. You don't hallucinate same way twice. But the correct program is very deterministic. The correct program has to do the exact same thing again and again and again and again. Can you take advantage of that? So here we assume we have a prompt that says, okay, some English sentence of a program you want to write. So instead of getting LLM generate 1, we get LLM generate n of these programs. And we can use a little bit of variations of prompts, multiple different LLMs to generate a lot of these things. Then also we ask LLM to generate inputs, not output. Just say, because given the problem will say take 2 integers. Okay, generate bunch of combination of 2 integers. So generate bunch of m inputs that will run that. And then we'll do is we'll run all these programs with all these inputs. And we'll cluster them. The intuition is the correct program will be deterministic, doing the same thing again and again and again. So all the correct programs will have a large number doing the exact same thing. The hallucinated programs will be intermittent and they'll be doing differently. They'll be clustered differently. And so one of the programs from the biggest cluster should be a right program, correct program. So we tried this thing. And it's very interesting. So one thing you realize about modern LLMs is they are like a 4-year-old. They are way overconfident. They haven't learned humility yet. So what they do is, even if they know the answer, don't know the answer, they will just answer it. So what happens in this human eval benchmark suite is, if you just ask it, 83% of the time it will give an answer, right answer. 17% of the time it was wrong answer. But then if you cluster it and figure out if there's a large cluster, then about 20% of the time it can't find a large cluster. It will say, sorry, I don't know answer. I'll be humble. I do the answer. And then it's 90% of the time, and if you give a lot more variation in my LLMs in here and multiple prompts, in fact, 27% of the time he says, sorry, I don't know answer. But when he answered, I get the correct answer. This is what I want. Not answer every time, but don't give me a wrong answer. Either tell me you can't do the problem or give me a right answer. So we applied this much harder benchmark. This is live code bench. This is not the latest version of LLM, so if you just gave the live code bench to that version of ChatGPT, it was pretty bad. 61% of the time it gave a wrong answer. Only 39% of the time it gave a right answer. If you start clustering, we get better and better, and at the end, we actually both multiple, like a Claude and ChatGPT, we were getting about 90% of the time correct answer. Yes, 7% of the time it said, I can't answer your problem, but when it can, I could believe the answer. So still we are worried, why is there 2.2% time that it's giving a wrong answer? So we looked at the problems and realized it is our problem. So most problem descriptions are, in those problem descriptions, so ambiguous. And the answer LLM was giving could be interpreted as a right answer. But the benchmark suite's answer was different. It was also a right answer, the ambiguous problem. So if you eliminate the ambiguity and did that, it was always correct. So what this means, that there's a path forward with LLMs to get the correctness. I'm not saying this is the only thing, but we can use other techniques around LLMs like testing, validation, verification, all those things to basically get back the correct answer. And we need to really push on that. To finish up, LLMs will augment traditional compilers. It's a given. It's going to happen. Okay? And we should think about that. I think the fact that the compilers are so behind, we can use LLMs to generate part of the traditional compilers. And if we do that, we can be in the race with the architects as they keep moving. We can also follow them closely than the way we are building compilers today. And LLMs may replace a large chunk of traditional compilers. They might completely eliminate them, or they might put it into small, like a side part on the entire process. This can happen. And given the pace, I think if I ask me to take a vote, I will say there's a good chance this will happen. So what does it mean? I think compilers will go through a transformation similar to what NLP went into a decade ago. In 5 years, the programming tools will look nothing like what we are doing today. Not just the compilers, even the languages we program will be very different, because right now, LLMs can even use English as a language. So there will be interesting hybrid languages how we program today. So everything is going to change in here. So as a community, what I would say is, think about this hard. Don't get pulled out of legacy compilers and try to improve legacy compilers. Think big, aim high. I think if we do it right, we will be able to get the kind of the Fortran type abstraction given to everybody and build something using all these tools in here. And finally, this could be the worst of the times for us or the best of the times. In fact, in 5 years, every paper I publish would be in the dustbin. Nobody might be using that in there. That's the worst of the time. But on the other hand, the next compiler still has to be designed. And we have the opportunity to basically design what will be a compiler and what will be a programming tool for the next 2 or 3 decades. And we get that opportunity. That's a once-in-a-lifetime opportunity. That is the best of the times. So I hope you will take advantage of that opportunity, and we will lead this revolution and not get left behind. Thank you.
We'll thank Saman for both an inspiring and challenging talk and for a thoroughly deserved award. So thank you, Saman.
Thank you. Thank you.
Now we have a mic stand at the front there, and there's an opportunity to come and ask questions. If you wouldn't mind introducing your name and your institution, your affiliation when you ask your question, that'd be fantastic. So please come to the mic at the front, and there's time for some questions for Saman.
Thank you. So this is live broadcast, so you are in there. So.
Mark Hill, University of Wisconsin. Great talk, Saman. I want to ask you a question even more important than compilers.
Okay.
So when Fortran was introduced, it was said it was going to eliminate programming.
Yes.
Now that we have these DNNs and these large language models, is it going to eliminate programming?
That is a very interesting question. I'll answer it 2 ways. So one project we did was we got a bunch of Python programs and gave it to LLMs to optimize this program. And what we realized was the LLMs were using the comments in the program to optimize it, not just the code. So if you eliminate the comments, the optimization doesn't happen that way. So what that means is not just the code, the English part of the program, written, the comments part was actually useful in there. So that is like very interesting. That means the code only pays some part one. See, it's another interesting thing. I was a summer intern at Microsoft very long time ago. And those days, there was this clash between programmers and like project managers. Project managers were these Harvard MBA types. What they used to do is they used to write specification, APIs, and the programmers used to basically code them up. There's always a friction between those two, and I think in the subsequent years, the programmers won. So we don't have huge project managers in here. But now when I look at what I am doing with LLMs, I'm like, damn, I am doing project management again. I am writing this high-level specification. I am managing a bunch of finicky LLMs. You have to treat them like some junior engineers, and you have to manage them properly. You have to guide them. You have to encourage them. You have to warn them. You have to do all those things you do with a person in here. And we don't, and this is something I worry a lot, but as a professor, what do I teach our students? I mean, we are very good at teaching them coding. We make amazing coders, but we don't teach them to write project documents. We don't read them to manage things. So do we have to go back and teach a different set of skills to do that? That said, what I would say is there are certain precise things that you cannot write in English. But it might not be code. You might be able to write things like a diagram. We might be able to do like data flow graph. There might be multiple ways to convey some stuff you might write in English. And the nice thing about LLMs is they are multimodal. They can handle all those things. So the programming language, programming might become a much more complicated thing in here, what you provide in there. So it's fascinating. So I don't think we'll end up with Python or like a very homogeneous language. We'll end up with a bunch of heterogeneous way of instructing these systems what we need to generate. And yeah, it's fun.
Andrei Bochenko, Huawei. First, thank you for really amazing talk, and congratulations with a well-deserved award.
Thank you.
Yeah, one of the first slides really struck me about Fortran. Well, indeed, we, our predecessors, the very first language for HPCA is portable and provided near assembly level performance from get-go. And now, we still don't have a productive, portable, and high-performant language for ML.
Yes.
So, question, maybe we just had a wrong start. Maybe Python, which not originally designed for ML, was a kind of curious, but drags us down and what we can do it.
Yeah, it's interesting because I think compilers went through this wild period where the input was in very complicated C languages, C-like programs with complicated control flows, stuff like that. We are wrestling with those things really hard. Information is not available. A lot of information is dynamic runtime. So we were wrestling with that. Then, now we are doing matrix multiply. Come on, how simple could it be? Simple, very elegant, there's no dynamism in there, and we are still failing. So part of that is, I think, what we were struggling in the 90s, if you're looking at mainly for machine learning, the problem is even easier. But I don't think, because we focus on different things, we didn't focus on how to get something very predictable, very statically, all the things known fast enough. So I don't know whether it's a language issue or a compiler issue. Because these things don't have aliasing. These things doesn't have very complex control flow or access functions. You can write it in anything. You can write in Python. You can write in something like einsams. Even you can give it C without saying no aliasing. I think it's the compiler that's failing right now. It's not the language. And I don't think compiler is able to take that and deal with all the transformations necessary to get performance. So that's my view.
Thank you.
Joseph Torrallas from Illinois.
Joseph.
Saman, so one of the things that we're seeing today is that companies are becoming very powerful, right? The Googles and the NVIDIAs, huge numbers of engineers, lots of money to do their own stuff, and they keep it basically proprietary, right? How do we break this cycle? What can we do with our few resources and few people to have an impact on these huge systems?
I think that's
any thoughts?
Very good question. So the issue is, the thing about a compiler is it has to work for all programs. So you have to come up with the right set of abstractions. Simplicity matters. Today, what companies are doing is they are brute forcing their way into performance. Because saving grace is they don't have millions of lines of code to deal with. It's few matrix multiply, few simple kernels, and those kernels are getting brute force that companies, and what they're finding is even what they call compilers only can compile that program for that architecture. And if the architecture changes or anything changes the compiler, the compilers break down. Because they are basically hard-coded brute force. And the thing about, if you look at this, all these people, they have the manpower, but they don't have the patience to think through the problem and come up with this essence, come up with the right abstractions in there. So whereas I think as academics, what we can do is we can have the patience. We don't have to deliver something tomorrow. What's the right abstraction? So we are dealing with all these like accelerators. Is there a set of good abstractions that can capture those accelerators? I think if we go in that direction, I think we can beat, because I know the companies are amazing people, but I don't think they have if we look at them, they have a lot more short-term vision. And what they have to do is get the performance of the current LLM pipeline on the current hardware. And that doesn't mean building general purpose, general compiler things in there. So that said, we also face this notion on machine learning that a lot of things the companies can do with these frameworks, we don't have the resources. So for example, we can't train a large LLM ourselves. We don't do that. So it almost feels like what mechanical engineering departments went through. They could not build airplanes anymore, or aero-astro department. They are unable to build airplanes, so how do they become relevant? Because they are not building airplanes. We also did that with hardware. There was a time the universities produced state-of-the-art chips. Not anymore. I know you're building chips. I know you're building interesting things, but you can't build a commercially viable chip at 3 nanometers out of a university anymore. There was a time when it was 100 nanometers. We built things that are compatible in that. So, but still, what you're doing in your group is very important, because you're finding the essence that will go into these chips that in there. So we had to go one step up and say, find those essences that the industry will implement. So I don't think in software, this is a new concept. Hardware people, I think, had to deal with it for a while. And software, we haven't. So we have to figure this one out.
I'm afraid we'll have to stop now. We're just about out of time. Thank you so much, Saman, for such a great talk. And I know there's a lot of people who want to ask more questions, which is a reflection on your talk, and there'll be an opportunity to catch them on later, I'm sure.
Definitely.
So thanks again, Saman.
Thank you. Yes. Sorry for telling all your work is for nothing.
we have a very short break now to move to your next session. If you're in PPoPP, you stay in this room. And could I ask those who are staying in PPoPP to move to the grey seats? Please do not sit on the blue seats if you're at PPoPP. Move to the grey seats, please. And for everyone else who's going to CGO and HPCA, CGO I think is mostly on level 2 and HPCA is mostly on level 3.
Losing you. If your heart could find a new reason for someone special to hold on to, I wonder if I would do. Because of the time we shared, time we lost in love with one another. Days we had pay the cost of losing hearts desire so soon, so soon, so soon. I'll be sending my love all over you. Take me back to the distance. Oh yeah, late night cooking in my kitchen, dirty dancing in my room. I love the things you do, and I send it all of my love to you. I'm sending all my love. You're the only one that I'm dreaming of. It's true. I'll be sending all my love. I'll be sending all my
Well, I wanna let you know my mind is made up and I wanna go. And I've been thinking about what to do. Been thinking about me, about being you. For a long time, I tried to find reason to stay here in this cage of mine. Well, I don't need no borderline. I don't need that frame of mind. Let me tell you, I don't need nobody. Nobody but me. I don't want nobody, nobody but me, nobody. Listen, now you're gone back, and I want you back. Those things I ever said, regret seeing. Need somebody. I need my baby. Yeah, yeah.
Hello? Yeah. We will start the first session of PPoPP in 2 minutes. In the meantime, please come down and sit in the in the gray chairs. Okay, why don't we get started? Hi, everybody. Thanks for coming and welcome to PPoPP. I'm Madan Muswati from Microsoft Research, and me and Kenjiro Tora are the program chairs of PPoPP, and we are very privileged to welcome you all. Our first session is going to be on concurrency control, and Zhe from Fudan University will be giving the first talk. So one thing before we start, I just wanted to say we have an excellent program, lot of great papers, and 6 papers stood out among these. And so these are all tagged as best paper nominees in the program, and this presentation is one of the best paper nominees.
Okay, may I start now? Okay, thank you everyone. My name is Jojo from Fudan University, and today I'm going to introduce the work binary compatible critical section delegation, and this is a joint work with Alibaba Cloud. Firstly, let me introduce some background about cache stretching. We know that when we have a concurrent program, when multiple threads are contending for lock, the lock word as well as the shared data will move between cores when the critical sections are handed over between cores. And this handover will trigger a lot of, will waste a lot of cycles, mainly because the movement will trigger interconnect traffic and messy cache coherence protocol, which are all costly. And according to a lot of measurement, there will be more than 200 cycles for a single cache line movement between core. Okay, and a critical section delegation can ease this cache stretching by refactoring the critical section into parsable form like a function, and then by sending the request, by sending an execution request to one core, so the critical sections from different cores can be executed in a single core. In this case, the shared data as well as the lock word will stay in the server, in the combined or delegate core, so the cache stretching can be just eliminated. And the throughput can be several times higher than the lock handover cases. However, if you want to use critical section delegation, the most challenge you will face is refactor complexity. If the critical section is pretty simple, like a single shared counter increase, in this case, you can just turn it into a parsable function pointer or function. However, when the critical section comes with multiple entries, multiple exits, in this case, refactoring it into a parsable format can be very difficult, and things can be even more complex when the critical section spans multiple functions. In this case, if you want to make them into a parsable format, you just need to refactor multiple functions, which can be painful for a large concurrent system. And a very recent work, DC log, mitigates this problem, the refactoring complexity problem, by stack swapping. They don't assume developers will refactor the critical sections. They just assume developers will use their supplied lock and unlock APIs. And in the lock API, they just pack the thread context into a parsable format, and then parse the saved register context into the combiner server. to allow the combiner server, the combiner, to swap his stack into the waiter's stack and then jump into the instruction pointer saved by the waiter. This achieves a very swift thread switching. However, the thread switching is pretty incomplete because only general purpose registers are saved and restored during the swift thread switching. Some other registers, like FS base, which is a thread local storage pointer, as well as kernel states, are not saved and protected during such switching. And you will trigger a lot of undefined behaviors in a lot of cases. For example, if a critical section contains a thread local variable accessing, you will just trigger undefined behavior. And in a lot of other cases, like the compiler may insert TLS access semantics into the critical section. Like when you trigger a function, call a function, which would throw an exception, and for handling this exception, the compiler may insert TLS accessing semantics into the function. And because kernel states are not protected, so if making a syscall within the critical section, it will also be undefined. And the stack swapping eventually causes a deterministic scheduling, which is not perfect in this case. If a critical section is delegated by the combiner or the delegate, if the critical section synchronizes with some places later will be executed by the combiner, then you will deadlock. So our goal is try to achieve binary compatible delegation. The binary compatible means that there is no modification to the binary. And it's totally transparent to not only developers, but also end users. So it achieves out-of-box acceleration. And it's not specific to a certain type of lock. Customized locks can also experience acceleration because of binary compatibility. However, the first challenge is where to delegate if we cannot modify the binary. So our answer is try to ask the kernel to profile the running process to know which critical sections are hot and deserve delegation, and try to identify the entry and exit of those critical sections. And then use an in-kernel virtual machine to execute the identified critical sections. And the second challenge is, where do the critical sections start and end? Because we cannot touch the binary of the user space. Okay, a hint is that when the process triggers field test wait, and it might be the start of the critical section. And when it triggers field test wake, it might be the end of the critical section. Because many user space lock scheme use field text for parking policy. So our binary compatible delegation works as follows. First, the kernel is always profiling the field text invocations, and high frequently invoked field text words will be selected as the candidate for delegation. And for those locks, for those user space locks, they still use user space fastpass to contend for the lock and try to execute the critical sections, which are not changed. However, if the user space lock, fastpass lock fails, you will trigger field text wait and enter the kernel. In this case, we do not follow the traditional kernel method to handle field text. We just make it into our customized VWQ, which will be introduced later, and waiting for delegation. And some other threads may complete their critical section execution and triggers field test wake to wake another thread to continue to execute. In this case, one waker thread, one thread that is triggering field test wake, will be selected or elected as the delegate, and the delegate will execute a batch of waiting thread to complete their critical sections. And the execution is completed in a supervised way. So it doesn't jump to the waiter's instruction point. And it has bounded execution, so it may early abort. And in such early abort case, it will eliminate unsupported critical sections. And for the early aborted cases, it will just, the waiter thread will just fall back into traditional slow pass and will enter the fuel text and waiting for wake up. And the in-kernel VM is very crucial for the supervised delegation. We use the user space bypass, which is a work for allowing kernel to safely execute user space instructions in kernel. And we will supply the register context saved on the full text wait to the in-kernel VM UB. And the in-kernel VM UB will execute from the instruction pointer register saved in the PTREX, saved in the register context. And all other general purpose registers, including the FS base, which is a TLS pointer, will also be honored during the in-kernel VM execution. And during the execution, the waiter core will spin and waiting for notification. And there are several exit for the in-kernel VM. Firstly, if we are fortunate enough, the in-kernel VM will start from full test wait and exit at the full test wake. In this case, a complete critical section is just delegated, which is perfect. However, if the lock acquisition fails because we have user space fastpass, the lock may be stolen by another thread somewhere else. In this case, the in-kernel VM will start from full test wake, but ends still at full test wait because it didn't acquire the lock. In this case, we just fall back to slow pass and put the waiter thread into the full test wait queue and waiting for wake up. And the in-kernel VM may reach the instruction count limit because it has bounded execution. In this case, the in-kernel VM just exit at a user space instruction. And in this case, we will notify the waiter to switch back to the stopped point and to continue execution. And the last case is that if an irrelevant syscall is just invoked. In this case, because kernel states are not saved protected. So this is similar to the instruction count limit reached case. The waiter thread will be notified to return to user space to continue from this point. And the bottleneck we met is the full text wait queue. The full text wait queue is highly contended when the user space lock is highly contended. Because no matter if full text wake or full text wait, they will access the spin lock protected full text wait queue. So we just designed a non-blocking per core queue for delegation. And we do not use the full text wait queue expect the fallback slow pass case. And the queue is very simple. It's just an atomic integer. And each core corresponds to a bit in the integer. And if a thread wants to in-queue, you just flip the bit he owns from 0 to 1. And if the delegate wants to dequeue all the cores, you just fetch and clear the queue integer. And we have delegate election scheme to achieve NUMA aware. In each NUMA node, there will only one delegate thread. And all threads, all cores in the NUMA node will compete for the winner to the delegate. They just use a lock. All threads, all weaker threads try to acquire a per NUMA node delegate lock, and only one thread will win the lock. The winner will be elected as the delegate, And the delegate will compete for a cross-NOMA global lock. And the winner will delegate a batch of waiters in this node. And after that, you will wake up the waiter threads for the loser wakers, because all wakers will increase a pending wake request counter. So by waking up the counter numbers of waiter threads, it achieves the equivalence of executing multiple waker threads. And those losers will return immediately to user space. So all the waker threads, all waker tasks are executed by the waker, by the delegate. And according to our evaluation, more than 50% throughput can be achieved in a very wide range of core count. And it achieves very close throughput to TC lock, the spin lock variant of TC lock. And the throughput is much higher than the blocking variant of TC lock. And the throughput curve is very flat against the thread count, even crossing NUMA or oversubscribed. And the factor decomposition shows that the VWQ, valve-led WQ, is very important. Without the VWQ, we can barely get acceleration. And the delegate election helps a lot when the thread count is very high. And in the macro benchmark, we saw a lot of acceleration for Memcache, LevelDB, and Splash 2x suit a lot of apps. And our future work is try to delegate spin locks in user base. In this case, spin locks have no full text invocation, but we will try to use catch miss to predict the existence of spin locks and try to insert breakpoints into user space by kernel to try to hook the lock acquire and the releasing process. And thank you for your listening. And the takeaway slide is that concurrent apps can now be accelerated without modification. Thank you a lot.
We have time for questions, so if you have a question, please come down to the mic. Okay, so I actually have a question about this paper. I really enjoyed reading the paper. You talked about how you're dealing with spin locks. Given that you have a very efficient way to delegate, do people need to still use spin locks? Or more generally, how will programmers change if you have such an efficient lock mechanism in their disposal?
Okay, very good question. Firstly, how many people will use spin lock if we have a very efficient delegation scheme? Is that even though we have very efficient lock schemes, developers just ignore it, just do not use it. They just use the lock they thought to be very effective. And we cannot change their mind. And there are a lot of legacy apps, especially in a lot of non-AI or non-mainstream cases, scenarios. They have many legacy apps. Those apps just use spin locks, even self-made spin locks, very slow. So we still need to try to optimize them from the kernel part. For those apps, we just cannot touch the binary, let alone source codes. Okay.
Thank you. Congratulations for a very great paper. So I guess this is partly answered in the experimental result, but do you give me a sense of how much cache lines critical section needs to touch for this system to pay off? So when the delegation pays off instead of executing normally?
How many cache lines? The acceleration varies.
So
According to the cache lines, it retrieves during the critical section, during the delegated critical section. And in our paper, we showed the throughput change with varying cache lines, even with like tens of shared cache lines touched, there still be positive acceleration.
Okay, so in your micro benchmarks, so you showed the result of the critical
1, 2, and
section
4.
touching only a couple of lines.
Yeah, 1, 2, and 4. And even higher, there still will be acceleration. And we have another, 1, 2, and 4.
I see.
And even there are acceleration is higher when the shared cache line accessing from 1 to 4. And it can be even higher, but then there will be slowdown.
Thank you. And so I am slightly confused about what you call the in-kernel virtual machine. So what happens in the in-kernel virtual machine? Is it basically the same as what would happen in the user level? Is it the only difference being that it is executed in the supervisor mode?
A short answer is no. It's not just simply execute the same instruction. It execute very different instructions in kernel, but achieve the equivalent effects as returning to user space and continue to execute. And this is the in-kernel virtual machine is another work. We call it a UB, user space bypass. It's a work, and I'm the first author of that work. It appeared in OSDI 2023. It uses instrumentation. It just inserts a lot of checks into user space instructions, and it translates a lot of user space instructions into kernel-safe ways.
I see. For safety, yes.
Yeah, for safety.
Thank you. Let's thank the speaker again. So our second talk for the session, unfortunately, the speakers could not travel due to a last-minute emergency, but they did record the presentation, so we will stream the presentation for you.
Hello, my name is Dave Dice, and this is joint work with my co-author, Alex Kogan, and the presentation is HPCA's Value-Based Mutual Exclusion. Our context here is mutual exclusion, that is locks, mutexes, and the like. Specifically, we're interested in implementations in cache-coherent shared memory. And what we're looking for is generality. We want to allow large number of dynamic threads at runtime. Threads can come and go. Large number of locks at runtime. Locks can be created and destroyed dynamically. And we want threads to be able to hold an arbitrary number of locks and release those locks in any order they see fit. And our goal here is to decouple the implementation dependencies of the locking subsystem and make it easy to integrate. But also, we want to preserve the performance of the state-of-the-art locks and achieve some performance similar to what you would get with CLH, MCS, and the gold standards. HPCA locks borrow considerably from two other existing lock designs, the first of which is Tidex locks, which was originally reported in PPoPP 2016. Tidex locks are quite simple. They have a lock body has an arrive and depart fields. The lock is unlocked if those two fields are equal. They enjoy constant time arrival doorways and unlock paths. And critically, each thread has two unique identifiers, a primary identifier and an alternative identifier. To acquire Tidex lock, a thread first performs an atomic exchange of its identifier, in this case my ID, into the arrive field and obtains the previous value. And then it waits until that previous value equals what is found in the depart field. Critically, a thread waits on its predecessor to announce that it has departed the lock. Then it can enter the critical section. And to release the lock, it stores its own identifier into the depart field. This is relatively simple. As constituted, this is incorrect, however. There's one small fly in the ointment here, and that is that if a thread's residual values from a previous locking episode are still in the arrival and depart fields, then when it installs it, if it were to install its own value again, none of the lock state would not change and it would appear unlocked. So to deal with that situation, the TIDEX algorithm, not shown here, also pre-checks the depart field to see if its own identifier is in there. If its own identifier is found in the depart field, it flips and uses its alternative identifier for the remainder of that locking episode. So, what are the downsides to using the TIDEX lock? Well, the first is the minor annoyance of having to do that identity check on arrival to determine whether you're going to use your primary or alternative identifier. That's a minor consideration. The key primary problem with TIDEX locks is they have global spinning, so they generate considerable coherence traffic, and they're unfriendly and don't tend to scale on large systems. But we're going to try to address those ideas with HPCA values. We're going to replace the TIDEX thread identities with HPCA values. These are, in a sense, nonces, although not strong cryptographic nonces. HPCAs are 64-bit values. They're effectively unlimited, and in practice, they have no possibility of a wraparound. By convention, they're non-zero, and a HPCA value appears at most once in the history of the process. They're non-recurring, and the value is uniquely associated with a thread, a lock, and a locking episode by that thread on that specific lock. Naively, we could create HPCA values with an atomic fetch and add on a global HPCA allocator. In practice, though, that would just create another coherence hotspot, and we don't want to do that. So in reality, what we do is we mitigate that cost by allocating blocks of 64K values at a time, and then locally sub-allocate out of that block. And when the block is exhausted, we go back to the global allocator again and get another block. The next lock we're going to borrow from is TWA. TWA is ticket locks augmented with a shared waiting array. This appeared in Europar 2019. TWA uses an immortal array of 64-bit version numbers. Our array happened to be 4K in length, but that's a tunable choice by the developer. The array is shared by all the locks and threads in the process. And what we do is we disperse spinning over that array, so we reduce coherence traffic and coherence hotspots. This mitigates the impact of global spinning, and it improves scalability relative to the underlying ticket lock. To acquire a lock under TWA, we first advance the ticket field with an atomic increment to obtain a local ticket value. Then we check that value against the grant field. If they're equal, we have an uncontended lock acquisition and our thread can immediately enter the critical section. Otherwise, we need to wait. To do that, we hash the ticket value and optionally the lock address to form an index into our waiting array. This is a slot. Then we notice that we use a specialized hash to reduce false sharing. Any arbitrary hash would work, but a specialized hash can actually gain us some performance. We then wait for the slot to change and then recheck the grant field to see if it's become equal. This is slightly racy. We use a check and recheck idiom here, and that same idiom also appears in HPCA locks. To unlock a TWA lock, we update the grant field to ticket +1, and then we form a hash again with ticket +1, form an index into our waiting array, and atomically increment that slot to let waiters know that they might need to recheck grant. For HPCA locks, we're going to borrow from TWA. Specifically, we're going to borrow the idea of the waiting array. But instead of containing version numbers, the waiting array in our case is going to contain HPCA values. And those are the HPCA values of threads departing through unlock. So, how do we acquire HPCA locks? First, we create a HPCA value local to that thread. We'll call that H, it's a local variable, and we try to, as noted before, we try to allocate our HPCA value from our local block, and failing that, we go to the global allocator and get a new block. We then exchange our H value into the arrive field to obtain the predecessor's HPCA ID. We then compare that predecessor's ID against the depart field. Again, if they're equal, we have uncontended lock acquisition, we can enter the critical section immediately. Otherwise, we need to wait. To wait, we hash the predecessor's ID and optionally the lock address to form a slot index into the array. We again use a block-aware hash that specifically balances locality in the array versus the risk of false sharing and collisions in the array. We then wait on the designated slot in the array. If the slot happens to equal the predecessor's hapex value, then we're done, and we actually can skip checking the depart field. This gives us an accelerated handover for the waiters compared to TWA. We have reduced coherence traffic because we don't need to fetch and check the depart value field. If the value changed to some other value, we need to re-execute the waiting protocol, check depart, and then go back to waiting on the slot again. And if there's no change, we just continue to busy wait. The unlock path is relatively simple. We store our hapex value for that locking episode into the depart field. We hash H and optionally again the lock address to form an index into the waiting array, and we store H into that index. And notice that under TWA we needed to use an atomic increment to adjust the slot. Here we can just use a simple atomic store. It's worth calling out a few properties here. With hapex locks, the queue of waiting thread is implicit. This is somewhat like CLH. A waiting thread knows only the hapex value of its own immediate predecessor in the list, and a waiting thread does not know the identity of its own successor. Critically, in the contended unlock path, the value of the outgoing owner's hapex is the same as the immediate successor's predecessor variable. It's worth showing a worked scenario to show how this works. We'll show threads T1, T2, and T3 contending for a common lock, and we'll assume, for brevity, that there are no hash collisions. Initially, at time 1, the arrive and depart fields are both 25. They're equal, so the lock is unlocked. I've just picked 25 out of thin air. It's as a hapex value that has been retired. At time step 2, thread T1 arrives and calls lock. It generates a hapex value locally of 111, again, picked arbitrarily, but unique. The exchange on arrive installs 111 and returns the 25 value. That 25 value is the value of our predecessor. Our thread then inspects the depart value field and sees the 25 is also there. So at this point, we have an uncontended lock acquisition. Our thread can enter the critical section immediately. All is well and good. Next, in step 3, thread T2 arrives. T2 calls on lock, and it generates a hapex value of 222. It exchanges on the arrive field and installs 222, overwriting and returning the 111 value that was previously there. So our predecessor's hapex value is 111. We then hash that 111 value to form an index into our waiting array, and then we wait for 111 to appear in the array at that location. Next, at time T4, thread T3 calls lock, and it generates a hapex value, local hapex value of 333. It again exchanges on arrive and installs 333 over the previous value, 222. And again, T3 now waits on, it hashes the 222 value, forms an index, and then waits on that index in the array for 222 to appear at that location. So at this point, T1 is running in the critical section as the owner. T2 and T3 are waiting. Next, thread T1 finally gets around to calling unlock, and it stores its own hapex value, originally H of 111, into the depart field. And it also hashes the 111 value to form the index, and then stores 111 into the waiting array at that index. At step 6, T2 recognizes succession, sees the value it was the waited for value appear in the slot, and then it can finally enter the critical section. We note that there are two very interesting variations of hapex locks. The first one, which I just demonstrated, is what we call the invisible waiters form. We call it invisible because waiters do not write into the waiting array. There's also another form, which we call the visible waiters form. And very briefly, waiters register themselves or write into the array using a compare and swap to try to install their predecessor's value over 0 into the array. And this registers themselves in the array as waiting. This is faster, provides a faster path for contended handover under sustained contention. Critically, the unlock operation can skip updating the depart field if it can confirm the existence of a waiting immediate successor in the array. And it uses a compare and swap on the slot of hapex value in 0 to both determine if there is a waiter and to signal that waiter. The unlock and the waiting successor in a lock, in this case, do not access the lock body. So we have a further reduction in coherence traffic, which improves scalability. So how do HAPAX locks compare to state-of-the-art locks? To make a long story very short, they're about the same in practice. And that's actually what we wanted to achieve. So what are the downsides to using HAPAX locks? First, we can have collisions or near collisions in the array. And near collisions can induce false sharing, which is obviously undesirable. Our worst case remote memory reference complexity is really quite bad. And if all the hashes, say, were to collide on one slot, we would devolve to TIDEX, which again is not desirable. The upsides. It's FIFO, which is of course nice. We have constant time arrival, doorway arrival phases and unlock paths. Typically our RMR is good. We're fairly parsimonious with coherence traffic. And we got that generality we wanted that I mentioned earlier. Dynamic number of threads, locks, and we can hold an arbitrary number of locks and release them in any order without any particular penalty. Most critically, it's easy to integrate HAPAX locks into existing systems and under existing locking API. The lock and unlock methods are leaf methods. They have no dependencies. Critically, there's no allocation of queue nodes as you would find in MCS or CLH, and require that malloc to allocate a queue node. That often requires a lock and would result in circular dependencies in your software system. And for instance, we can use HAPAX locks in Rust in a no standard environment where there is no allocation available, and we can also use it in low-level runtimes. Another really nice property of HAPAX locks is it allows trivial constructors and destructors for lock and thread indices. To initialize a lock, we can just zero the memory underneath the lock. We don't need to do anything special to it. And to destructor for a lock is trivial. We don't need to do anything. And another nice property of this is there are no ownership changes, as in the Rust sense. We don't pass pointers around from thread to thread to thread. So thank you for your attention. I should note that there's a long version of this paper up on arXiv, additional benchmarks and implementation ideas and code variations are up in there. Obviously, here's the ACM DOI. Code will eventually become available on my GitHub repository, but very honestly, you have the code already inside the listings in the paper. And feel free to contact me with questions or comments. Thank you.
Thanks, everybody. So if you have any questions, please contact Dave Dice or Alex Kogan, and we'll use this time to catch up with our schedule. So the third speaker will be Amit Aravi. He'll be talking about fixing non-blocking data structures for better compatibility with memory reclamation schemes.
So is that okay? I don't see it in here. So it's true. Oh, okay. Thank you so much. Hello, everyone. Good morning. I am MD Amit Hassan Aravi from the Pennsylvania State University. And my today's talk is fixing non-blocking data structures for better compatibility with memory reclamation schemes. This work has jointly been done with Professor Ruslan Nikolaev
also from Penn State. Modern systems have multiple cores and needs efficient resource management. To address these, non-blocking data structures are becoming more popular as they avoid deadlocks, ensure system-wide progress, and improve scalability. Two common classes of non-blocking data structures are lock-free data structures, in which at least one thread always makes progress, and wait-free data structures, all threads always makes progress in a finite number of steps. As these data structures do not rely on mutual exclusion, we need safe memory reclamation techniques to manage memory objects safely. One classical approach is epoch-based reclamation, EBR. It is easy to use first, but it has one potential downside. That is, it may have potentially unbounded memory uses when threads are stalled or preempted. Other reclamation techniques, such as hazard pointers, address this and solve this issue, but hazard pointers is difficult to use, and as it actually takes care of the unbounded memory uses issue, sometimes this property is called as robustness, but hazard pointers is difficult to use and was considered not to be compatible with a lot of data structures that I'm going to show you next. Many non-blocking data structures, they use optimistic traversals to improve the scalability, such as Harris linked list and the Natarajan metal tree. So optimistic traversals is read-only traversals that do not rely on the ongoing concurrent update operations, and the search operation can proceed independently without any obstacles, no matter what kind of concurrent operations is going on currently. EBR naturally supports this behavior. However, HP fails to support optimistic traversals. Workarounds are sometimes available, such as if you replace Harris linked list with Harris-Michael linked list, but you have to forego the optimistic traversals, and no such modification are available for Natarajan metal tree. So before we talk about our solution is how our approach works to make compatible with those data structures to work with HP, let's first have a look on what actually goes wrong here. For example, suppose we have a Harris linked list from A to F, and there is a thread 0, which is currently deleting node B, so it marks it for logical deletion, and the thread 0 is stalled. Meanwhile, thread 1, searching for the node F and to locate it in the list, it is currently at node B, and it reserves node B at hazard pointer slot. Meanwhile, thread 2 is deleting node C. So at first, it marks it for logical deletion. And as in the Harris linked list, we can unlink a set of logically consecutive, logically deleted nodes with one regular cache operation. So when thread 2 is done with marking node C as logical deletion, it unlinks the entire logically deleted chains from A to F in this example node B and C. Now, after this unlinking, thread 2 tries to reclaim the nodes. As B is already reserved by thread 1, it reclaims node C. Now, coming back to the thread 1, it was searching for node F. So now it is trying to go from B to C. So it reserves C in hazard pointers, but it's too late because node C has already been reclaimed by thread 2. So when it tries to access node C, it gets a seg fault. So many reclamation techniques try to solve this issue of this optimistic traversal. But according to the error theorem, you can achieve 2 of the 3 highly desirable properties with a reclamation scheme. So there is no silver bullet. So that is why our approach is to fix the data structures and to redesign traversals to add local validation. And we call our approach as safe concurrent optimistic traversals, SCOT. So now let's have a look how Scott works for Harris linked list. Suppose we have a Harris linked list with node N1 to N6. So we have hazard pointers. So we start with 3 hazard pointers. We reserve the next with HP0, the current with HP1, and the previous with HP2. It is not available in the beginning. So now as we traverse or iterate through the list, we move the hazard pointers. So when you go from N2 to N3, so N3 will be reserved by HP0, N2 will be HP1, and N1 will be reserved by HP2. Now let's go back and think about the problem that we discussed, and let's recreate that problem in our approach. So let's say that in these N2 to N6, N2 to N4 are logically deleted. So in our paper, we call these, or we refer this as dangerous zone. And we need to be very careful while we traverse through this dangerous zone to avoid that segfault that we talk about in the problem. So now, as we iterate through the list, we reserve N2 by HP0 and N1 by HP1. And as we go from N2 to N3, so we reserve N3 with HP0, N2 with HP1, and N1 with HP2. Now, we make a key reservation here, is that in Harris linked list, you can just delete a consecutive logically deleted node, a prefix of that. You cannot just delete from the middle of the chain. So if you want to delete something from here, you have to do N2, or N2, N3, or N2, N3, N4, but not only N3. You cannot do that from the middle of the chain. And that helps to build our approach here, because we introduce an extra hazard pointer, which is HP3, and we reserve N2 by HP3. So we call this our first unsafe node, and N1 is our last safe node, and which is reserved by HP2. Now, as we move through or iterate through the logically deleted nodes in the dangerous zone, we need to validate each time is that whether our last safe node still points to our first unsafe node as we traverse. So as we are traversing from N3 to N4, we do the same thing here. We reserve it by HP0, and we use 0 and 1 just to iterate through the current and next, and we dedicate HP3 and HP2 just for our last safe node and first unsafe node. Now, what if that the validation fails? So due to a node, new node insertion, or the chain of logically deleted nodes being already eliminated. So we start from the last safe node, that is N1. But however, if it is also marked for logical deletion, so we need to start from the beginning. And our Scott also applies to the Natarajan-Mittal tree. Here in the Natarajan-Mittal tree, we have ancestor, successor, and parent, and the leaf nodes contain actual keys, and the keys in internal nodes are used for traversal. Now, as the same as Harris linked list, where we had the logical deletion, in this context, it is called flagging. So when, for example, here, the node GHE, the leaf node GHE are flagged, the corresponding siblings are tagged. And we can actually, a chain of consecutively tagged edges can be eliminated with a regular cache operation by updating the ancestral link from the successor to the remaining leaf node. And one point to be noted here is that successor node is the last untagged node. Now, for the Harris linked list, we use 4 hazard pointers, but for Natarajan-Mittal tree, we use 5 to protect current, leaf, parent, successor, and ancestor. So after each HP reservation, we need to check that the ancestor still points to the successor, just as like in the Harris links, we used to check whether our last safe node still points to the first unsafe node. And if somehow ancestor points to some other node, we need to restart from the beginning. And from our empirical evaluation, we have seen that the local recovery that we have for our Harris linked list is not very useful for the Natarajan-Mittal tree. So therefore, if ancestor points to some other node or successor becomes tagged, we need to restart from the beginning of the tree. One other problems with the Harris linked list is related to the weight-free traversal. As for the EBR, when it traverses in the weight-free traversal manner, even if there are logically deleted nodes, it can actually iterate through the list without going back to the beginning of the list or restarting. However, when we apply Scott to Harris linked list with robust schemes such as HP, if the validation fails due to the data structure state change and the last safe node is logically deleted, you have to go back to the beginning of the list. So it guarantees lock-free but not with freedom progress. So to address this, our approach is specifically tailored for the traversals, where we use path head record entry, and we avoid the non-standard instructions. Only we use the regular cache, and we avoid dynamically allocated descriptors. And to give you a high-level idea of how our approach works in the weight-free traversals, the search operation, it starts with a lock-free version for few iterations, and when it cannot complete, so that means there are some concurrent updates going on, which is actually having some issue to get the search operation to be completed. So the search requests help from the other threads, and it jumps into a slow search. So our approach was inspired by the Kogan-Petran's slow search, slow path, fast path method. And here, the search, when it cannot complete its operation, it moves to the slow search and asks help from the other threads. And the concurrent operations that ongoing, that is actually preventing it to be completed, the search operation. So it periodically checks for help threads, whether some threads are stuck and needs help. So if it is true, it jumps into a slow search and try to help the threads that are stuck. So sooner or later, every threads will jump into the slow search to help the threads those are stuck. So to coordinate between the threads in slow search, we use a value, shared value that is stored in the path thread record entry, and it is used for both input request and output result. So the helpy basically do the input request, and also it uses the output result. However, output is produced by both helpy and helpers. So in the input request, we have bit 0, which is used for the is input. If it is 1, that is the input request, and the value is the slow path cycle number. And in the output result, we have is input is 0 to make sure that is the output, and the value is true or false, which is the result of the search operation, whether the key is found or not. And we evaluated those data structures, Harris linked list and nitrogen metal tree in an AMD system with 128 cores and 384 GB of RAM. So in addition to hazard pointers and EBR, we have also evaluated other robust reclamation schemes such as hazard eras, interval-based reclamation IBR, and Hylin 1S, because they have the same challenges that HP has, and Scott also applies to them. And we also have a special case of no reclamation baseline, which basically leaks memory, and it is used as the upper bound. So let's look at the evaluation of Harris versus Harris-Michael list throughput. So we evaluated for key range 512 and 10,000 with a workload of 50% read and 50% write. We also did some other workloads. You can actually go to our link of code to check that. We will provide that in the later slides. So here we have, so we see that Harris linked list always outperform the Harris-Michael list for the robust reclamation schemes. And also we have shown here an optimized version of hazard pointers, which actually takes local snapshots and avoid excessive memory barriers. So here we see that some robust reclamation schemes such as hazard errors and Hylin especially, it achieves the performance of the EBR, and HPoPP always works better than the original HP. For the Natarajan Mittal tree, we show the key range of 100,000 and 50 million. So in the 100,000, we see that the robust reclamation schemes are achieving the performance of EBR, especially Hylin. And we also show another key range of 50 million where the key range doesn't fit in the cache. and it also shows the same trend as we see in the 100,000 Q range. And we also evaluated the memory overhead. You can actually check our paper for that. And our code is available in the Genodo.ui and the GitHub repository. And thank you so much, and I will take if you have any questions. Thank you so much for attending the talk, and especially the chair today.
If you have questions, please come over here to the mic to ask the question. Or I can bring the mic as well. Krishna.
Excellent insights. I was curious if some of these techniques can also be extended to other data structures.
Yeah,
Have
sure.
you thought about, or have they been,
Yes,
are they being very specific to just these two?
No. We have also worked on skip list and hash maps, so it will be also coming to our GitHub repository soon.
Similar techniques?
Yeah, similar techniques applies. Yeah.
Actually, I have a follow-up on that question. So as you're extending with these two, Scott, to multiple data structures, are you seeing patterns so that you could sort of automate semi-automate this approach?
Yes, because if you look at the Harris linked list and the Natarajan metal tree, those are different data structures, right? But we had our first unsafe node and the last safe node in Harris linked list. That same applies to the Natarajan metal tree as ancestor, whether ancestor still points to the successor, right? So that's a pattern. And we can do that with a single cache. That we can do that for the Harris linked list.
Thank you. Any other questions? Okay, let's thank the speaker again.
Sure, thank you so much. Yeah.
Thank you. Great. So now we'll have the last talk of the session. Guy Cochimilio will be giving a talk on transactional memory with dynamic multiversioning.
Okay, hello everyone. I'm Gaetano Cochimilio. I'm a fifth-year PhD student at the University of Waterloo. Today I'm going to present our work, Multiverse Transactional Memory with Dynamic Multiversioning. This is work that I did with my supervisor, Trevor Brown, along with our colleagues, Srivasan Ravi. In this work, we're interested in the problem of multi-threaded synchronization. So you can imagine you have some multi-core system, you have a bunch of threads concurrently running on that system, and these threads are going to access some shared data, and we want that access to be atomic. Now, if you want to implement this efficiently, you're going to probably use some kind of handcrafted fine-grained locking algorithm. But this is often going to be difficult, and it's often going to be error-prone. Now, one way you can get easier synchronization is to use something called transactional memory, or TM. With a TM, you can mark blocks of code as transactions, and then you can concurrently execute multiple transactions at the same time, where each transaction appears to execute atomically. Excuse me. Now, under the hood, the TM is going to handle all of that fine-grained locking for you. So you, as the programmer, no longer need to think of any of that. You just give your sequential implementation, you augment it using the TM API, and then you get back a sequential or a concurrent option. Now, one concept when you use transactional memory is this idea of conflicts. So if you have one transaction write to an address that a different concurrent transaction has already read or written, then this is a conflict. And in order to resolve conflicts, we need to abort one or both of the conflicting transactions. Now, in this work, we're focusing specifically on opaque TMs. So this is a correctness condition. And really what it means is that we want to control the behavior of both committed transactions and aborted transactions. So without opacity, you would not care about aborted transactions. Now, unfortunately, TM is not a one-size-fits-all solution. So TM typically can't handle workloads where we have really long-running read-only transactions in the presence of frequent updates. A classic solution to this problem, especially in databases, is to use multi-version concurrency control, or MVCC. So in a traditional STM where we have a single version, we might have some atomic variable, it has some value 5. If we want to update its value to, say, 17, we will just overwrite the value. We lose access to the old value. With a multi-version approach, instead of just having our single version, our single value, Now we have a linked list of version nodes. So every version node has a timestamp or a version along with the data that existed at that time. So now when we want to update, we don't override the old value, we just add a new version with the new value. And with this approach, what we can do is we can service reads by using snapshots, and snapshots allow us to read a consistent version of the data that existed at some point in the past. Now, there are some drawbacks to MVCC as well. Typically, it's more expensive than TM, especially in the common case, and usually it has some increased memory consumption. I put an asterisk here, though, because the more recent work in MVCC has really reduced that issue. All right, so what do we have in terms of prior work? Well, there are various well-known classic opaque single version TMs. TL2 is probably the best known single version TM. For opaque multi-version TMs, the only one that I'm aware of is SMV. And one thing you'll notice about these works is that they're all relatively old, right? 2011 being the newest here. Now, recently, there was a new advancement in TM, a new single version opaque TM called DCTL, and this now represents the state-of-the-art for single version TM. However, all the single version opaque TMs that I showed you here, they still suffer from that problem of not being able to handle these long-running reads. And while we have non-opaque multi-version TMs, this opaque multi-version TM is written in Java and it's heavily tied to the Java garbage collection, so there's some undesirable qualities there, performance issues. So our contribution in this work is a new opaque multi-version TM that we call Multiverse. It has performance that matches the state-of-the-art single-version TM for typical workloads where we don't have those long-running reads, but we still have the ability to handle these long-running reads without sacrificing too much performance. So let me take you through the transaction design in Multiverse. So our transactions can either be versioned or unversioned. If a transaction is unversioned, it behaves much like traditional STM, where we have sort of that single version style. A version transaction behaves closer to an MVCC approach, where we're going to service reads via snapshots. Now, transactions will always start as unversioned, and if a transaction performs a write, that is, it's an update transaction, it's going to remain unversioned forever. That has to do with some correctness issues I'm not really going to get into here, but you can imagine if you have to use a snapshot to read in the past, it doesn't really make sense to read in the past and then write in the present. Now, read-only transactions, they can become versioned based on some heuristic. So if based on something like how many times they abort, some recent history of transactions by the thread, and some other global state that we consider. And our design goal with Multiverse is to prioritize the unversioned transactions because they represent the common case. We want our unversioned transactions to be as fast as possible, mainly as fast as DCTL, the state-of-the-art single version TM, and then our version transactions should be as fast as possible without slowing down our unversioned transactions. All right, so now I'm going to take you through the data structures that we use in Multiverse. So I'll first direct your attention to these TM addresses. So these are not really a data structure that we use. These are just the addresses of the data that we want to atomically access via the TM. Now, each one of these addresses is protected by a version lock, and these version locks are stored separately in a lock table. Now, you could imagine that you might want to store the version locks alongside the TM addresses. For example, you have address 1, then lock 1, address 2, lock 2, and so on. But the gold standard in transactional memory is to not change the memory layout of the underlying user program. So for that reason, we store the locks separately in a table. And now there's a mapping function between the address and an individual lock in that lock table. Now, what is a version lock? If you're not familiar, it's just a lock that has a lock bit along with a version number. So where does this version number come from? The version number comes from a different data structure that we use, this global clock, which is just a monotonically increasing integer. And the lock versions are going to be changed potentially when we acquire and release these locks. All right, so now we have some other data structures here, and these relate to the fact that in Multiverse, like transactions, addresses can either be versioned or unversioned. And when an address is versioned, it needs to have a version list associated with it. So that version list cannot be stored alongside the data for the same reason that we can't co-locate the locks, so we store it separately in a different table. So in particular, we store it in this version list table, where a bucket in that version list table is a linked list of pairs of addresses and pointers to their corresponding version list. So you can see in this example, the address A1 is versioned because it has a version list present in the first bucket of the VLT. And now, as I mentioned earlier, a version list is just a linked list of version nodes. A version node is a timestamp and whatever data existed at that timestamp. And then lastly, if we want to figure out whether or not an address is versioned, what we need to do is traverse that VLT bucket, but in order to sometimes avoid doing this traversal, we use a Bloom filter, and the Bloom filters tell us whether or not an address is definitely unversioned. And one thing you'll notice here as well is that all of these tables that we use, they're the same size. They use the same mapping function, so you only need to compute that mapping once. And you can see that the mapping function doesn't allow addresses to map to the same index. So in this example, A1 and A2 both map to the first index of all the tables. And one thing I'll note, we version individual addresses, but when we unversion, we do this via a background thread, and we unversion at the granularity of entire VLT buckets. I'm not going to get into that here, but if you're interested, I can talk about it later. All right, so multiverse also has this concept of TM modes. So our TM operates in one of 4 possible global modes. 2 of these modes are stable modes, and 2 of these modes are transient modes. The 2 stable modes are mode Q and mode U. Mode Q is the queries version mode, and here we prioritize the unversioned transactions by forcing the version transactions to be responsible for versioning addresses. So they take on the burden when they need an address to be versioned, they're responsible for performing that version. In mode U, we flip and we have the updates version. Here we're prioritizing the version transactions by forcing all writes to version addresses that are not already versioned. And so we always start out in mode Q, and then we have our transient modes between the stable modes, and they're just there to facilitate a correct and safe transition between the other modes and maintaining some invariance. All right, so now I'm going to walk you through the unversioned and version transactions for our default mode of mode Q. So when you begin a transaction, you start out by reading the global clock to get your current version. And then if you want to do some transactional read of an address, say address A, you're going to directly read this address. You're going to validate the lock on the address, and you're going to validate it by checking it against your current version, the version of the lock against your current version. If this validation fails, this transaction aborts, and we'll have to retry later. If it succeeds, then we're going to add this address to our read set, which is just a set that keeps track of all the addresses that we read during this transaction. Now, one thing to notice here is that for an unversioned transaction, we don't need to access the version list at all. We don't touch it, we don't look at the boom filter, we just look at the data directly and the lock when we're unversioned. For a unversioned write, it's a sort of similar process. In this case, we're going to validate and acquire the lock, again, comparing the lock version against our current version. If this fails, then we abort. If not, because we're in mode Q, we have to check if the address is versioned. So if the address is already versioned, then we're going to update the version list. This is going to involve adding a new version, and that new version is going to be marked as TBD, and this TBD marker is going to remain on it until this transaction commits. And we'll see where that comes in a second. After we add our new version, we're going to add this address to our versioned write set. So this is a set tracking all of the version addresses that this transaction has updated. And then we update the address directly. If the address was not already versioned, we just skip right to going to updating the address directly. And then in both cases, we add the address to our standard write set. And the standard write set just keeps track of all addresses that we've written to, regardless of whether or not they are versioned. All right, so when we try to commit, if we're read-only, we don't need to do anything else. We're done. If we're not read-only, then we need to revalidate our read set, comparing against our current version and the lock versions of those addresses. If that fails, we abort. If it succeeds, we reread the global clock to get our commit clock. And then we use that commit clock to replace all of our TBDs, and we also use it to release all the locks to a new version. If we had this transaction abort, then we need to increment the global clock. We need to check our do our heuristic check to determine if we should retry as a version transaction or potentially in a different mode. And then, of course, we actually do that retry of the transaction. So for version transactions, we're just in mode Q here. Recall that a version transaction has to be a read-only transaction, so the only thing that's going to change is what we do when we do a transactional read. So now in this case, we need to check if the address is versioned. If the address is already versioned, we just traverse the version list, and we're trying to look for a suitable version. A suitable version is one that has a timestamp that's less than or equal to this transaction's current version. And now here, this is where the TBD version comes in, so these traversals of the version list are blocked by TBD versions. So this thread would need to spin if it encounters a TBD version that has a timestamp that is suitable. So if we find a suitable version, then we can return it, otherwise we have to abort. Now instead, if the address was not versioned, then we have to take on the responsibility of versioning it because we're in mode Q. So that's going to involve acquiring the lock, but in this case we're going to acquire the lock without validating the version. So we're just going to retry on repeatedly try lock until we acquire it, and then we're going to add a new version. This is going to involve allocating the new version node. For the timestamp, we use the lock version, of the lock protecting A, and then we use the current value of the address for the data. And now after we do the versioning, then we validate the lock. And we need to do this because we shouldn't be able to read the address if the lock was inconsistent. So if it was inconsistent, then we have to abort, but that address will remain versioned. And one last thing to note here is if it was already versioned, then we don't have to check the lock, which is the benefit of this approach. All right, so now you have an idea of how our TM works, at least for its default mode. Now I'm going to show you some performance evaluations. This was implemented in C++. The tests you're going to see here are on an AMD EPYC machine with 64 cores and 128 hardware threads, 20-second trials, average of 5 trials. We're comparing against the single version TMs that I showed you previously, TL2, DCTL, the current state-of-the-art, TinySTM, and NoRec. It would have been nice to also compare against SMV, but as I mentioned, it's implemented in Java, and that would be difficult to port. So let's look at some throughput results when versioning is not needed. So this is an A-B tree. It's a uniform key access pattern. Y-axis is operations per second, x-axis number of threads. This is a 90% read-only workload with no range queries. So what you can see here is that Multiverse is achieving as good or better performance than all of these existing single version TMs. So we've achieved our design goal here when the workload is such that we don't have these long-running reads. So what about when we have these long-running reads? So this is the same data structure, but now we have 0.01% range queries. And we also add 16 dedicated updater threads. So these updaters are just there to make sure that the range queries are having contention or conflicts. And you can see here now, none of the single version TMs really achieve any throughput whatsoever. Only Multiverse is able to achieve good performance in this case. And lastly, I'll show you a time varying workload. So this is a continuous 20-second run where we alter the workload every 5 seconds. It's always 64 worker threads and always 20% update. In the first and third workload, we have no range queries and no dedicated updaters. And the second and fourth intervals, we have 4 dedicated updaters and then 0.01% of very large range queries. And I'm additionally showing 2 versions of Multiverse here where we restrict the mode. And what you can see here is initially when the workload is such that we don't have these long-running reads, the results are similar to the first graph that I showed you where Multiverse is competitive with DCTL. But as soon as we introduce these large range queries, all of the algorithms except Multiverse and the variant of Multiverse where we restrict the mode to mode U, they drop to almost 0 throughput. And Multiverse is the only algorithm that can regain the throughput once we return the workload to one that does not include range queries anymore. All right, and with that, I will conclude. I'll just note that there's several other details in the paper. I'm happy to take questions if you have time. Thank you very much.
We do have some time for questions.
Yeah, I guess I'll just ask. I mean, first of all, I'm Ruslan Nikolaev, an assistant professor from Penn State. I guess I'll just ask a kind of general question. Do you believe in transactional memory, right? So, and it's kind of been, I think it was kind of, first it was popular, then it was kind of not so popular, but then there, as you mentioned, there is recently some other works in this area. Just kind of curious.
Yeah, so I think it's useful. I think one of the things from the old days, like one of the reasons why a lot of those old works didn't see much traction is there was this, first of all, the hardware wasn't really good for supporting TM back then, but also there was this idea of commit time locking in your TM. So what I showed you here is using encounter time locking, where you access the address and you lock at that point. And this allows you to abort earlier, which is nicer. Those old TMs were all using commit time locking, which that did not scale as well. And also, there was this idea that TM would not be useful in sort of industry-level transactions, bigger transactions. But these recent works, especially DCTL, has shown that that is maybe not the case. For example, in a purely read-only workload, DCTL on a tree could achieve something like 700 million transactions per second, which is very much within reason of getting close to a handcrafted algorithm when you're talking about those kinds of numbers. So if your workload is such that you're okay with maybe slightly below the most optimal handcrafted approach where you need a very experienced engineer to implement that, then I say transactional memory is certainly useful.
Okay, thank you so much. Very nice talk.
Thank you.
Hey, Guy.
Hey.
Ajay here from ICS 4th. So how do you reclaim memory in this TM?
How do we, sorry?
Are there any complications, or it's simple state-of-the-art memory reclamation?
Oh, yeah, so it's just a simple EBR reclamation scheme. The gist of it is that we tie the epoch advancement into the commit and abort of transactions, so that ties in quite naturally to EBR.
I see. Okay, thanks. Thank you. Good talk.
Any other questions? If not, let's thank the speaker. And I think now we'll head out for the break. Sorry.
Yeah. Hi, this is Krishna Nandiwada, session chair for the next session. If you are presenting next session, I request you kindly come check your machine and see that everything is okay. Right? Thank you.
As you live and breathe, I really know now what had hold on me.
Jeff, let me know when we can start. Can we start? Not yet. Not yet.
Just you and me.
Oh, the slides have to show up. The slides have to show up. The slides have to show up. Slide. They will do it. They will do it. No, you don't.
Me and Mrs. Jones, we got a thing going on. We both know that it's wrong, but it's much too strong to let it go now. We meet every day.
All right, lights are on. All right. Good morning, everyone. Welcome to this second session today morning. My name is Krishna Nandivada. I will be the session chair for these four excellent talks. The first talk will be given by Alish. He'll be talking about thread scheduling under oversubscription. Alish.
Thank you very much. This work would have not been possible without the help of Vicente Beltran and the rest of the team at the BSc. So let me start first explaining the problem that we are trying to solve. Here you can see a simple HPC software stack where an application is using a runtime system to distribute its parallel work in the machine's cores. Typically, at startup, the runtime will create a worker thread per core, and each thread will be responsible for running part of the parallel work exposed by the application. These runtime systems are not always used directly by the application, but sometimes they are used through a library. For instance, the library could be OpenBLAS or Bliss, and this runtime could be OpenMP. As the applications grew more complex, it is possible that other libraries are pulled into the dependency trees, and with these libraries, even another runtime that at the same turn will create also another worker thread per core. This is named an oversubscription scenario, where we have more threads than cores. And where this happens, the Linux process scheduler kicks in and interrupts threads periodically to preempt them, giving them a quantum to run. Unfortunately, these preemptions are known to be detrimental for runtime systems. That's because they are the source of problems such as the log holder preemption, log weighted preemptions, scalability collapse, and cache pollution. But let's see an example of what this means. So let's imagine that this CPU that you can see is running a very important runtime code that depends on a pthread barrier weight function. This pthread barrier weight let's imagine that just one of these threads has all threads have reached the barrier, but one of them, which has received an interrupt. When this interrupt arrived, the thread has all the other threads have started busy waiting for the thread that has been delayed, and while they are busy waiting, they are wasting CPU cycles, while they could allow other threads belonging to the other runtime to run. And what's worse, these busy waiting threads could actually be delaying the very thread that's needed to schedule the thread that will unlock the barrier. This situation could become quickly more complex when runtimes are nested. So for instance, in this case, runtime A for each thread created by runtime A, we'll be spawning a team of threads of runtime B. And this team of threads will have the size of the number of CPUs in the machine. So in this case, we end up having up to 16 threads, greatly increasing the chances of hitting one of the problems that we have seen before. That's not the only case where this could happen. But also when we have multiple processes running in the same node where each of them is using a runtime, and there's no kind of resource partitioning. But why would we want to run multiple processes in the same machine without any kind of resource partition? Well, the idea is that real-world applications are rarely perfectly parallelizable. So they have periods of parallel phases and sequential phases. So theoretically, it could be possible to actually combine both of them to fill the gaps of one application with the other. However, the aggressive synchronization techniques used by runtime systems and the preemptions that we have seen before are actually limiting the potential benefit that we could achieve from this scenario. So let's talk now about our approach to fix this problem. The idea is that what we are searching is for a solution that allows developers to implement their own schedulers. And we want this solution to require any kind of kernel modifications, so it requires no elevated privileges to be deployed. It works seamlessly, it has multi-process support, and is compatible with thread local storage. But if we cannot modify Linux because it requires elevated privileges, and we don't want to modify runtimes because there are too many, how can we do it? We realized that the GNU-C library is the ideal convergence point for our solution because it is used for process initialization, thread creation, blocking operations, affinity management, and is at the same time used by a wide range of applications. So our solution, which we have named User Scheduling Framework, or USF, is a new glibc backend that coexists with the classic traditional glibc implementations. It's a framework that allows users to implement their own scheduling policies without special permissions. And we have used to implement our own cooperative scheduling policy, which we have named SCHED-COOP, and I will talk about it in the next slide. But just to make sure that we're on the same page, what we have implemented actually is what you can see here in the bottom left of the screen. To make use of our scheduling policy, we will just run our application through the change RT-C. The -C is a new option. And our application will simply start under this scheduling policy. But what's a SCHED-COOP? What's a cooperative scheduling policy? Well, that's nothing new. But the idea is that unlike preemptive schedulers, cooperative schedulers allow threads to run as much as they need. So threads can run until they block, they yield, or they end. These kind of policies are not ideal for all kinds of situations, such as interactive applications. But for HPC, it might be exactly what we need to get rid of the problems that I have just mentioned before. So let's take a look at the USF threading model now. The idea is that when a runtime creates a thread, this thread will be intercepted by USF, and this thread will still be created. But the idea is that USF is applying a fine thread placement, and it places each thread in a different CPU. It doesn't allow us to have more than one thread per CPU to avoid oversubscription. So let's imagine that runtime B has already created all threads, and we have now a thread per CPU. And now runtime A is trying to create its first thread. Because all cores are already busy, USF will detect this situation, and it will create the pthread, but it will queue it inside an internal queue. The operation the pthread create will return, so runtime A will be able to create more threads, but all those threads will still be queued. They will only allow it to run one of the runtime B threads blocks. In that case, USF will detect the situation, and it will pop one of the threads in the queue and resume it in that particular core. To implement this behavior, we have to re-implement most of the blocking functions inside the glibc, such as pthread mutex lock, and also their unlock parts, because whenever a thread is resumed, we don't want it to start running in any CPU. Instead, what we do is to queue it again inside the USF queues. At the same time, we had to modify affinity-related calls, because that will interfere with the USF thread, find thread placement. So instead, all these calls are taken as hints, but they are not explicitly respected. Whenever application A forks or another application is called with change RT-C, the new application, its main thread, will be also queued inside the USF queue, because that queue is implemented using a shared memory segment, so it supports to schedule threads belonging to multiple processes. So how we have implemented all this? We have used the Nanos 5 threading library, which implements most of the scheduling logic. Nanos 5 is a library that provides bare-bones services for runtime systems. So essentially, Nanos 5 it manages its own pool of worker threads. It exposes the tasks. It allows to submit tasks to its schedule, to run tasks in its worker threads, to pause tasks, resume tasks, and even running callbacks upon task completion. Using all these semantics, it is possible to implement full runtime systems such as OpenMP. But what we have done here is to actually transform glibc into a task-based runtime system where pthreads are tasks. So far, we have had support for calls such as sleep, poll, semaphore, affinity, barrier, conditional variables, mutexes, and related calls. And this has been enough to run complex applications such as PyTorch. In the future, we will also add support for I/O calls such as read and write. So for our evaluation, we have evaluated USF and SCAD-CoP in multi-runtime and multi-process workloads. But however, we had to address first some workload inference interferences that appear when we are mixing multiple runtimes, because they are not designed to be co-executed in the same node or the same processes. So first of all, we had to avoid disabled thread pinning. We have to set passive wait policies, and we also had to add calls to a schedule inside libraries such as OpenBlast and Bliss, because they implement their own custom busy wait algorithms. And as I have shown you before, pthread barriers are particularly damaging in terms of performance. And not only for USF, which could potentially deadlock it, but also for Linux scheduler directly when it is oversubscribed. So we have modified them with a schedule. Now we will see two case studies, one with nested runtimes, and the other is a multiprocessor scenario with PyTorch. However, in the paper, you can see more case studies. Here you can see the results for the nested runtime scenario, where we are nesting two runtimes. On the y axis, on the left, you can see the number of the parallelism exposed by the outer runtime, and in the x-axis, you can see the parallelism used in the inner runtime. On the left heat map is the baseline that's running Linux over the Linux scheduler, and on the right heat map is a SCAD-CoP. The left heat map shows performance, and the right one shows speed up. But what I want you to see is just looking at the colors. The brighter the color, the more performant is. And you can see that the SCAD-CoP heat map is a little bit lighter in general. And that's because for some configurations has been capable of improving the performance up to more or less 30%. For some configuration, I mean configurations that are not ill-designed. So these are configurations that expose enough parallelism, but not too many, just as on the top right corner, where we have so much parallelism that now we are hitting another problem, a granularity problem, where the problem has been split into so many small tasks that the runtime overhead becomes noticeable. And also in the scenarios like the bottom left corner, where we don't have enough parallelism to fill all the cores in the machine. So here is a multiprocess example. Here we are running a chatbot an agentic AI chatbot powered by PyTorch, where a client application running in one node is sending requests to our server. For each request received for the client, it is running in parallel 3 inferences on 3 different processes, each running a different model. And each of these inference servers is using PyTorch with Bliss that use OpenMP to run their inferences. So the more inferences sent by the client, the higher the oversubscription in the machine. Here you can see the results. On the x-axis, you can see the number of requests per second sent by the client. On the left y-axis, you can see the latency, which are the lines. And the right axis is the throughput, which are the bars. Only the orange metrics belong to CGO results. All the others are executions over the Linux scheduler, where we're testing different kinds of resource partitioning. Let's see them one by one. In the green ones, what we are doing is splitting the cores equally between the 3 processes. So each of them receive the same amount of cores. And we can see that we have the worst performance possible because some of the models are more expensive than the others, and we have a lot of load imbalance. In the red one, what we are doing is to give more cores to the processes that are more computationally expensive. And we can see now that by looking at the throughput bars, we can see that it performs much better. But as the number of requests increases, it eventually collapses because of the noise generated by the runtimes. In the blue one, there's no resource partitioning at all. So it is Linux capable of scheduling all threads by itself. And it also performs remarkably well until it eventually collapses. The purple one shows what happens when there is no oversubscription at all. So each inference server is using a single thread. And now we can see that latency is completely stable for this case because there is no noise. However, it also is higher. The latency is higher for all executions because the machine is under use. Although for high request rates, it performs quite well. For a CGO, it is capable of achieving both high throughput and small latencies for both the small request rates and high request rates. So in conclusion, we have seen that combining multiple runtimes is complex because there are many sources of inferences, but it's useful because it allows for a high degree of flexibility. Also, CGO can effectively manage multiple runtimes without requiring special permissions to deploy it, and USF is compatible with any application that is using the glibc standard synchronization primitives. Its main caveat are custom busy wait barriers. However, we have seen that they are simple to identify and fix. Thank you very much. If you have any questions, I will be happy to answer them.
All right. Thank you, Alish. We have time for a couple of questions. Any questions, please raise your hands. Anyone? All right. Please introduce yourself and ask the question.
Kenjiro Taro from University of Tokyo. Great talk. You may have mentioned this already, but is it true that it doesn't support spin weight? So if some of the threads of a particular runtime systems are running, and they are trying to spin weight with everybody in the runtime system, is the system prone to deadlock? Okay, so is it true that your system in general cannot support spin weight? Because only some of the threads of a particular runtime system may be running at that time, right? And you are not preempting threads, right? You are not preempting. So your scheduler is non-preemptive, right? So is it true that you cannot support spin weight? Okay.
Can you not support spin weight? That's the question.
Right. So maybe you want to speak with them.
Yeah, here.
So we could support spin weights, individual spin weights. What we cannot support are barriers. because for the spin weights, it's just a matter of one thread spinning a little bit until while it's contended, until the thread that's inside the critical region exits, and it must be already inside, so it will eventually exit, and we will be able to continue. But the problem are barriers, because barriers were involving multiple threads, and we can end up collapsing all the CPUs, blocking all of them, without allowing the threads needed to unlock the barrier to be scheduled in any working CPU.
Any further questions while the next speaker is setting up the machine? A quick question, maybe? No? All right. Let's thank Alish. Yes, the next... set it up. Yeah, pull it out and pull it back. Pull it back.
There it goes. That looks better.
All right, the next talk will be given by TB from MIT on a variation of work stealing called waste-efficient work stealing. TB.
Thank you for the kind introduction. Can everyone hear me just fine? Great. Thanks. I'm TB Shardle. I'm a research scientist at MIT CSAIL, and today I'll be talking about our work on waste-efficient work stealing. I want to start off, though, with a quick shout-out to Kyle Singer, the lead author on this work, and the postdoc who really deserves the bulk of the credit for this work, especially for the implementation of our algorithm. Unfortunately, Kyle wasn't able to make it to Australia for this conference, and so I'll be presenting the work in his stead and trying my best to do it justice. Also, if you'll excuse me, I'd like to start off with a fun story about this particular paper. So this work was actually supported in part by the United States Air Force. And because of that support, we had to submit the camera-ready version of the paper for a non-technical review by the Air Force before it could get published. So the moment that our camera-ready was ready, I submitted it for their review, only to discover that they actually wanted 60 days to do that review. And we did not have 60 days before this conference. That happened late Friday night, and so I thought to myself, okay, Monday, I'll just send the Air Force an email asking them if they could expedite the review of this paper. I didn't actually send that email, however, because it turned out Sunday night, I get an email from the Air Force saying that the review is complete, which is great, but I also found very strange. Because in my experience, it's unusual for any US government entity to do something like a paper review so quickly without other prompting, not to mention over a weekend. And I can only imagine that something in the title, waste-efficient work stealing, got that reviewer really excited to read this paper. But what's this paper really about? Well, this paper is concerned with work stealing, or randomized work stealing to be specific. And as many of you may know, randomized work stealing is a popular algorithm for scheduling and load balancing task parallel programs. These are parallel programs you would write in systems such as OpenSilk, OpenMP, ParlayLib, TBB, Rayon if you like Rust. There are actually myriad systems that you can use to write such task parallel programs. And the idea with these task parallel programs is that as the program executes, it's going to generate and synchronize a whole bunch of tasks. Generally speaking, many, many more tasks than there are parallel processor cores on the system. And all those parallel tasks are going to be automatically scheduled and load balanced using a randomized work stealing scheduler, which works roughly as follows. So we start off with a pool of worker threads, typically one worker thread per processor core. And each worker thread, I don't know what that's about. Okay, great. And each worker thread will maintain its own local deck or double-ended queue of tasks. And as it executes the program and new tasks are created and tasks are synchronized, those workers will push and pop tasks from the bottoms of their local decks. Whenever a worker runs out of work to do, it becomes a thief, and it will try to steal work from some other worker by choosing a random victim worker in the system and attempting to take the topmost task out of that random victim's deck. Now, this algorithm has been implemented many times in many different systems and studied extensively in theory. And what we know is that when the program has ample parallelism, which you can quantify, but for now, we can just take that to mean it has plenty of tasks to go around. These schedulers execute parallel programs very efficiently, not just in practice, but in fact, they provide provable bounds on the parallel running time. There is a problem with work-stealing schedulers, though, and that comes on when there are periods of time when there just aren't enough tasks to go around. When that occurs, you can end up with these thief workers in the system attempting to steal work when there's just nothing available to steal. And these thieves are producing what we call waste. These futile steal attempts are what we refer to as waste. And this is generally undesirable because those thieves are consuming time and energy and compute resources for no gain in performance whatsoever. In fact, in practice, there are various pernicious reasons why those excess thieves can actually hurt the overall performance of the program. For example, those steal attempts consume memory bandwidth, and that's memory bandwidth that the workers with work to do no longer get to use. And so that can actually slow down the workers with work to do. So our goal in this work is to bound this waste in work stealing while preserving work stealing's performance, both in theory and in practice. Now, this is a pretty widely known problem, and their researchers and practitioners have explored a variety of ways to address this sort of waste. Very broadly speaking, there are two general approaches to how one mitigates waste. First is to allow thieves to nap, as we'll say in this talk, by calling yield or the sleep syscall intermittently to return cycles back to the operating system for some short period of time. This approach can work well in practice. Sometimes it's coupled with a back-off mechanism of some sort, but generally speaking, even when it works well in practice, it doesn't provide any theoretical bounds on waste, at least none that aren't fairly trivial. An alternative approach is to have thieves sleep, as we'll say in this talk. And by that, we mean we allow the operating system to entirely deschedule that thief thread until a signal arrives in the future that the thief should resume stealing. This general approach has been explored in various contexts as well, and some of those schemes are practically effective, but also don't offer provable bounds on waste. Others may offer theoretical bounds, possibly in more complex models where they're specifically focused on optimizing energy. But to our knowledge, those schedulers are quite difficult to implement, and in fact, to our knowledge, we know of no efficient implementation of those schedulers. Now, our algorithm is broadly going to fall into the second category of approaches. We're going to allow thieves to sleep. And our algorithm, which we call WOOS, is an extension of work stealing that preserves its running time while also bounding waste, both in theory and in practice. So in the paper, we show that WOOS achieves the same theoretical running time as ordinary work stealing while also bounding the waste on P threads to be order min of P times T infinity and T1 plus P squared, where T1 is the work or total amount of computation in the program, and T infinity is the span or length of a longest path of serial dependencies. This theoretical bound turns out to be borne out in practice. We evaluated an implementation of WOOS against several alternative schemes on a variety of Silk benchmarks with varying degrees of parallelism. And what we find is that WOOS performs better than those alternative schemes, broadly speaking, and especially on benchmarks that have limited parallelism. And those are the benchmarks that are most prone to exhibit waste. So today I want to tell you more about this WOOS algorithm that we've developed, as well as cover some intuition for how it achieves the theoretical waste and running time bounds. I'll then talk a bit about how we implement WOOS efficiently, and then hopefully with the time remaining, dive into some of those empirical results. So when we think about how do we design this algorithm to mitigate waste, we realize that this WOOS algorithm has to balance two competing concerns whenever it's adjusting the number of active workers in the system. By active workers, we mean workers which include thieves that are not asleep. So any time during the execution of the program, when you have too many workers for the amount of tasks that are available to go around, you get waste, as discussed before. On the other hand, if you have plenty of tasks to go around and thieves that are asleep, you can actually incur slowdown compared to simply never allowing those leaves to sleep. And if we think about how these two competing concerns play out, we find that we can get waste if the algorithm allows workers to go to sleep too slowly or wakes up workers too quickly. And we can get slowdown if the workers can go to sleep too quickly or wake too slowly. And so we have to carefully balance these two concerns in order to maintain our running time bounds while mitigating waste. So how does WOOS do this? Well, it takes a fairly simple approach of maintaining what we'll call the global wake potential, which essentially measures when is the program using too many or too few workers for the available parallel tasks. Broadly speaking, whenever workers do work, they're going to increase this wake potential. And whenever workers attempt to steal work, they're going to decrease this wake potential. So this wake potential is going to be allowed to go positive or negative. And when the wake potential goes sufficiently negative, when it goes too low, a thief in the system will consume that negative potential and go to sleep by, for example, waiting on a condition variable, or if you're on Linux, a few texts, whatever's convenient. When the potential goes too high and there's a thief sleeping in the system, the algorithm will consume that positive potential and signal the condition variable to wake up the sleeping thief. So it's a straightforward algorithm. How does this algorithm achieve the theoretical bounds on parallel running time as well as the bound on waste that I mentioned before? This isn't the proof, but broadly speaking, the intuition is that we choose these two thresholds to amortize changes in the number of active workers in various ways. So let me show you an example as applied to showing the running time bound for this algorithm. So if we imagine looking at the execution of this algorithm over time and plotting how many active workers there are in the system at each point in time. What we'll find from such a diagram is that there are these vertical edges when the number of active workers will increase or decrease by 1. So if we consider one of those edges where the number of workers decreases by 1, we know from the algorithm that it had to build up enough negative potential in order to put a worker to sleep. It turns out, though, that we can amortize the time to build up that negative potential against the critical path length, T infinity. Meanwhile, we have these edges where the number of workers will increase by 1. And once again, to increase the number of workers by 1, we have to build up enough positive potential in order to signal that the worker should wake up. And that's where we're prone to hurt our parallel running time. But it turns out we can amortize the time it takes to build up that much positive potential against the time it took previously to put a worker to sleep. And because there is, very roughly speaking, a one-to-one correspondence between all of these unit changes in the number of active workers, we can amortize everything ultimately against the critical path length, which allows us to show the parallel running time bound, and a similar symmetric argument can be used to show the waste bound. So that's just a bit of intuition for how WOOS achieves these theoretical bounds on both running time and waste. How do we implement this in practice? Well, to get an efficient implementation of WOOS in practice, we have to balance a couple additional practical concerns. First is this issue of descheduling and rescheduling thieves, putting thieves to sleep. It turns out that on modern systems, this is a pretty expensive operation. Anytime you want to deschedule a thief, you have to talk to the operating system kernel. That requires context switch overhead. That broadly speaking, costs at least microseconds of time. And compared to the operations within an ordinary work stealing scheduler, that's easily 10 to 100 times more expensive than anything else going on in the scheduler. So we want to be careful with how frequently we deschedule and reschedule thieves. Second, we've introduced this new global wake potential, and we're talking about having these workers contribute positive and negative potential to this global variable. That's a whole bunch of parallel threads contributing to a single variable. That's a point of contention. That can easily hurt performance. Finally, in order to achieve good performance in practice from any work stealing scheduler, we want to follow what's known as the work first principle, which says that you want to optimize the workers who have work to do in order to get the best performance possible. As much as possible, limit how much scheduling overhead those workers with work to do have to do. Let them just focus on executing their tasks. Or as the kids these days might say, let them cook. So our implementation of WOOS, which we call Wombat, which we backronymed somehow that I forget right now, addresses these challenges using a variety of techniques. So first off, we choose these two thresholds for waking and sleeping workers carefully in order to accommodate the high cost of descheduling or rescheduling threads. Second, the workers won't actually contribute to the global wake potential directly. Instead, they'll just tally up their local contributions to the wake potential. And then after many failed steal attempts, a thief may try to go to sleep. The first thief that tries to go to sleep won't actually go to sleep, but instead will become a special kind of worker, which we call a sentinel, whose job it is to monitor the system. More specifically, the sentinel will periodically go around to all the other active workers in the system, take their local contributions and move them into the global wake potential, and then look at the changes in that global wake potential to decide when to allow workers to go to sleep and when to signal that workers should wake up. Now I should mention, I'm sweeping a bunch of details under the rug about how this implementation works. You can find many more details if you check out our paper, and you can find even more details if you check out our software artifact. But let me move to talking about the empirical comparison. So we compared Wombat to several state-of-the-art alternative schemes, including the simple one you might think of, just never let thieves sleep. That scheme we call awake. We compared it to napping, having wasteful thieves call sleep with increasing frequency. We also compared it to the protocol inside of Parlay and Rayon, which turns out not to follow the work first principle. The basic idea behind that protocol is that wasteful thieves will eventually go and wait on a condition variable for some signal, and then workers will signal that variable when they push tasks onto their local DEX. Finally, we compared against the existing protocol within the OpenSilk runtime, which is similar to Parlay, except it's actually the thieves that take care of signaling when other thieves should wake up. And OpenSilk uses a whole bunch of heuristics basically to maintain a similar number of wasteful thieves in the system as there are workers with work to do. Now, as I previously showed, Wombat achieves good performance in terms of reducing waste and improving energy efficiency on a whole bunch of Silk benchmarks, especially benchmarks with low parallelism. Here, I'm diving into some of the results on a few of those low parallelism benchmarks and showing what all the different protocols do, just to give you more of a sense of what's going on here. At a high level, what we can see with these different protocols, all the protocols do a pretty good job of maintaining the parallel running time, in this case on 48 cores. Parlay suffers a little bit on one benchmark, but they're generally close to one. And then some of the protocols, Parlay and OpenSilk most notably, will achieve some amount of waste savings on one benchmark or another, but Wombat is the one that consistently manages to reduce the waste from these low parallelism benchmarks, sometimes by factors of 2 or 3 or 4. And when that waste savings happens to come a reduction in energy consumption by 50 to 75%. Notably, this is simply because we're reducing waste. We didn't optimize Wombat specifically to optimize energy efficiency. Now, I have a couple of these case studies I can show you, time permitting, just to see what's really going on with these different protocols. Great, okay. With these different protocols on any given benchmark. So in this case, we're just taking a look at the dedupe benchmark, which happens to implement pipeline parallelism. The idea with dedupe is that we have a stream of data coming in, and we're taking chunks of that data from the stream and spawning off tasks to optionally compress that chunk and append the compressed chunk to some output stream. So this computation actually does a lot of spawns, but it doesn't actually have much parallelism. And what we find is that across the protocols, okay, napping doesn't work very well. Parlay doesn't manage to save very much waste because the frequent spawns essentially cause Parlay to just keep the number of active workers maxed out the whole time. OpenSilk does a better job of adapting to the amount of available parallelism at any given time. Wombat does the best over all these protocols. I have more case studies to share with you, but for the sake of time, I'll just wrap up. So we introduced WOOS, this extension to work stealing, to effectively mitigate waste, both in theory and in practice, without sacrificing the parallel running time of work stealing. And we find that WOOS not only improves waste, but also energy efficiency, as well as several other effects, some NUMA effects, and even turbo boost performance in separate studies. I also want to note that WOOS does not require any specialized hardware or operating system mechanisms to work. condition variables are standard in today's systems. And so we believe that WOOS as an extension is relatively simple and should be easy to incorporate and extend into other work stealing runtime systems. Thank you for your time. I'd be happy to take any questions.
All right, we have time for one question. Yep, please introduce yourself and.
Hello, it's a good work. Will this be open sourced? I want to try it.
Will this be open source? You want to try it? I'm delighted to hear that. Our software artifact is open source and available. Okay. Yes, go ahead and try it. Let us know how it works.
Thank you very much.
All right. Yeah, let's thank TB for an excellent talk. And yeah, we will request the next speaker to set it up. Thank you. All right. The next talk will be given by Yu Yao on improving depth-first search, and she's from BSc. Yu Yao.
Thank you. Hi, everyone. I'm Yao from Barcelona Supercomputer Center, and today I'm going to introduce our work, Digger-based depth-first search, leveraging hierarchical block level stealing on GPUs. And this work is supported by, also supported by UPC and coordinated with China University of Petroleum Beijing. And before we start, let me briefly introduce our logo in the left, maybe the right side. And as we can see in the background, the honeycomb pattern represents the graph and many vertices and edges, and capturing large scale and irregular connectivity. And the B is the main characters of our logo, and it looks like a miner, right? And it holds the drill, which reflects the stack-based nature of DFS. So we keep pushing deeper along one path. So overall, this logo summarizes our goal. That is perform deep traversal on a large graph and map onto massive parallel GPUs. I will introduce our work in these 4 parts, and the first part is the brief introduction and motivations. So the DFS, to make the DFS iterative, we use a stack to perform the serial DFS. So the serial DFS produces the unique lexicographically ordered DFS tree. As we can see that each stack entry is a pair composed of a vertex and its next index. And the next index here is the next neighbor of the vertex to explore the agency list. So let's take this input graph as an example. So we started from the root A, and then first we push A0 at the top. And then we look at the next neighbor, and we go to B, mark B as visited, and push B0. And then update the next index of A to 1. And then we go to D and push D. And then we find that we also try this neighbor, but we find that D has no neighbors, right? So we just pop D here, and then backtrack to B, and go through E, C, and F. So when we when we pop the last entry in the stack, then the stack becomes empty, and then the whole process finished. So that's the tree generated by the serial DFS. We can find that this serial DFS has very strong dependencies, and it's very hard to parallelize. And however, in most application scenarios, we find that DFS doesn't require very strict order of traversal, and it makes unordered DFS a valuable direction for parallelism. So we also take this graph as an example. We just think of, we have two workers, and these two workers explore different branches concretely. So in stack 1, the worker has already traversed A, B, and D. And the second one, stack B, is trying to steal the oldest entry in stack 1. And then these two stacks are working in parallel, and they doing the push and pop work. And and finally, stack 2 pops its last entry, and at this point, both stacks are empty, and meaning that no workers has remaining DFS of frames to explain. So as we can see that two workers are exploring different subtrees. And so this unordered DFS has motivated many research effort, and some analysis has shown that parallel unordered DFS can achieve close to linear work efficiency. And but with the rise of modern parallel processors, especially GPUs with massive parallelism, and then the nature question becomes, so how can we map the CPU-style work stealing DFS into GPU? Actually, there are three main issues. The first one is that GPU provide limited on-chip shared memory, typically like tens to a few hundred kilobytes per stream SM. However, DFS may require stacks as deep as the longest path with tens of thousands vertices. So we need a segmented stack. Maybe the on-chip segments and off-chip segments. So I will introduce our new data structure later. And second one is that even the stack fits in the shared memory of a thread block. DFS performs frequent push and pop operations, and which create a problematic control flow. That is, the threads provided stacks cause word divergence, and while stacks shared within a block require many atomic operations. So it's very hard to get efficient intra-block execution. And third one is the scalability problem. The GPU's massive parallelism is not fully utilized because to saturate the GPU resources, execution must extend from single to multiple block, and that so that many SMs can become active. But this requires costly communications between among blocks, and also it will cause some load imbalance problem. So it's very hard to achieve a scalable inter-block execution. And next, I will introduce our digger-based implementation. Firstly, to overcome the shared memory limitations, we introduce a two-level stack structure. It consists of a fast hot ring in shared memory. So this hot ring is a circular buffer in shared memory, and it is a fast access portion of the stack. And also we have a contiguous region in global memory called code stack, and it is a large capacity portion of the stack. And based on these two segments, we have 4 call operations. Also, we have 2 points for each segment. 2 points is like a starting and the end positions. So the first operation is a fast push. We insert a new entry in the hot ring and update its head. And the second one is a fast pop operation. We pop the top entry in the hot ring and also update its head. And the third one is a flash operation. It is when the hot ring is full, and a batch of the oldest entries is moved to the cold stack. And as this example show, both A and B, these 2 entry pairs are moved to cold segment, cold stack, and the tail pointer in the hot ring and the top pointer in the cold stack are updated. And the last one is the refill operation. When the hot ring is empty and some entries is refilled from the cold stack. So these 2 entries are moved from the cold stack to hot rings. And based this data structure, we introduce the intra-block execution to resolve the second issue. So to achieve efficient intra-block execution, we combine 2 techniques. The first one is a warp level workload. It means that one warp is one DFS worker. And all 32 threads within a warp follow the same DFS steps, paths. And so no warp divergence occurs here. And the intra-block work still link contains 3 main steps. The first one is the victim selection. And idle warp steals from the deepest hot ring above the hot ring cutoff. So the hot cutoff is a parameter we set. And as we can see that in this example, both warp 1 and warp 2 are empty, so they're all safes. And they try to select the victim and scan the remaining tasks among all warps within a block. And they find the warp 0 as the victim. And step 2 is work reservation. The thief claims a batch from the victim's hot ring's tail. So, also both warp 1 and 2 try to reserve work, and they use the atomic cast to lock the task. Firstly, the warp 1 locks the task, reserve the task, and update the tail of warp 0 to 1, and it succeeds to steal. But the warp 2 find that, okay, there's only 1 task in warp 0, so no task steal, so it fails. And step 3 is a local transfer. So after the successful claim, the thief copies the batch from the victim's hot ring into its own and update the heads and start the DFS. As we can see, the warp 1 successfully steals the task. And then, so that's the updated states in block 1. Next, I will introduce the interblock work stealing. So to fully leveraging GPU's massive parallelism, DGRB steals from single block to multi-block execution and trying to activate more SMs and blocks across our GPUs. So when the block becomes idle, the enter block becomes idle, the interblock work stealing happens, and a batch from the victim warps callback will be stored. And how it works, it has four steps. It's quite similar with the intra-block work stealing, so we just briefly introduce it. So the first step is the victim block selection, and step 2 is the victim warp selection. And step 3 is also the warp reservation, and step 4 is a remote transfer. It should be transfer data from the global memory, from the callback of global memory to the hot rate in the shared memory. So you can find more details in our paper. And here we also provide a very specific example to explain how all our techniques collaborate to do the parallel DFS. And here we show the number of vertices each warp visited or traversed. As we can see that it has almost a balanced workload. And as for the performance evaluation, the platform includes 1 CPU and 2 GPUs. We compare, and we do our experiment on all 234 graphs from the widely used graph collections. So we first compare the performance with the two CPU DFS methods and 1 GPU DFS method. And the 2 subfigures show the performance of each method. And the bottom 3 subfigures show the speed up. And as we can see, we always are always almost the best among all the methods. And we also compare our performance with the GPU BFS methods on some representative graphs. So as we can see that our methods outperformance will optimize the GPU BFS method on several graphs. For example, some road graphs, we can achieve like more than 10 speedups. And the reason is that the long and narrow traversals hurt BFS, while it is beneficial to our using our method. And however, on some small diametric some graphs, for example, the L journal graph, we are a little bit worse than BFS. And we also compare the scalability with the MG DFS, the GPU DFS method, and we can get better scalability. And we also show the breakdown, the performance breakdown of our method, and to show that how the performance, where the performance gets in our method. And as we can see that from V1 to V2, the benefit is from the data structure, and we can get about 5% performance. And from V2 to V3, so our methods enable multi-block collaborations and brings very dramatic performance. And also V3 to V4 is to scale to all SMs, and in some graphs, it also scales very well. And this is the block level load balance analysis. And as we can see that our load balance is working very well. So than the baseline. And to conclude, we designed a two-level stack structure, and we develop a hierarchical work stealing mechanism. And also we achieve significant performance gains over existing approaches. So that's all of my presentation. Welcome to our, any questions?
We have time for one question for sure, at least. Yes. Please introduce yourself.
Okay, it's very interesting work. I have one question. Okay. How do you understand the load balancing in this work?
The load balance.
Load balancing.
Okay, thank you for your question. I think, in my understanding, I think maybe we want to make all warps or blocks to deal with very similar tasks, like so that's why we try to extend to implement both intra and inter-block, because we want to scale. We want to distribute all the tasks into different, like many blocks and SMs.
Thank you. Yeah, please set it up. So while he's setting it up, I had one quick question. Did you try on data inputs which are road networks? All your data inputs seem to be power law graphs. If they are road networks, did you?
You mean the data?
Please come set it up. How down? Please. Yeah.
You mean the data set we choose, right? Actually, we choose the three groups in our data set. I think they're almost the most common used data set in graph processing, and actually we don't select very specific graphs with some very specific patterns. I think it's more like a general selection.
Okay, let's thank the speaker. The last talk of the session. Okay, will be given by Hao Dong Bian from Tsinghua University. He'll be talking about runtime adaptive load balancing.
Okay. Hello everyone, my name is Bian Hao Dong. I am currently a first-year PhD student at Tsinghua University and also a teacher at Tsinghua University. Today, I'm going to share my report, Pyrmont, a fine-grained runtime adaptive load balancing for parallel SPMV on multiple CPUs. First, let's review what is SPMV. Here are two pictures. The top one is a mathematical expression. The ith element of the output vector B is computed as a dot product of the ith row of A and the input vector X. The bottom picture shows how it is built in an algorithm. We will need this for our method later. Okay, there are many uses for SPMV, such as graph algorithms, large-scale scientific computing software, AI algorithms, and solver. Right now, there are two main types of work on load balancing. One type is like a merge-buster, which focuses on computation. It uses a 2D way to keep the computation even. For a long time, people have been achieving load balancing based on or extending this method. The other type is like CAMLB, which focuses on memory access. It tries to give each thread the same number of cache length. This method is very innovative and was presented at the ICPP conference in 2024. We use these two as benchmarks and tested many matrices with more than 10 to the 5th power non-zero elements on 48 core Intel and 192 core AMD CPUs. The ratio is the time of slowest thread divided by the fastest thread. Ideally, it should be 1, but in this graph, the ratio is very high, which means the situation is very bad. Also, we find two important observations. First, single focus load balancing strategies, whether computation-centric or memory-centric, fight to achieve both higher G flops and lower ratio on modern medical architectures. Second, static partitioning approaches, which are either computation-centric or memory-centric, struggle to sustain stable load balancing effect across different hardware architectures and diverse metrics. To fix these problems, we need a good load balancing plan. This picture shows an example of dividing work by the number of non-zero elements. By looking at the algorithm details, we counted the micro operations for each thread. With 2 threads, the work gap is 12 times micro operations. When we use 4 threads, this gap gets even bigger, reaching 18 times micro operations. So we first designed a static plan called micro operation level load partitioning. We found 5 operations related to value: branch, load co-index array, load value array, load vector array, and fusing multiplier and ADD. And 3 operations related to row pointers, branch, load row pointers arrays, and store answer array. Then we just use a simple binary search to divide the tasks into threads in order. Next, when the static plan doesn't balance the work well enough, we use a dynamic plan to fix it. We just move the boundaries between nearby tasks. For example, if 4 tasks take 2, 3, 4, and 1 unit of time, the average is 2.5. So we move the length between task 1 and 2 to the right. And the line between 3 and 4 to the left, we have more details about it in our paper. Okay, third, we found that the second method is still not enough. As shown in Figure B, we need to cut big tasks into small pieces and send them to the cores in order. This is good for 2 reasons. First, as shown in Figure C, it trades off computation and memory access better. Second, as shown in Figure D, it is cache friendly. These small tasks fit in the L1 to L caches. This way, the cores don't have to get that from the slow mining memory often, which makes the bandwidth work better. Now, for our test, we used 48-core Intel and 192-core AMD CPU. We compared partner with many methods like CSR5, merge CVR, and SPV8, CAMLB. Intel mass kernel library, and the AMD optimizing CPU libraries. For software, we use the best performance versions of Intel One API on 2 CPU platforms. Our test set has 2,898 sparse matrices from the pseudo-sparse collection. Also, we use the 16 representative matrices for a more detailed look. Here is a performance comparison. The top 6 graphs are Intel results, and the bottom 6 are AMD results. Overall, the speed up is between 1.36 and 7.72. For large matrices with more than 10 to the 4th power non-zero elements, pattern is 1 times faster than any other best measured. To analyze further, we looked at the 16 matrices on Intel. First, we found that better load balancing leads to better speed. Second, despite achieving a load balance, SPV8's poor performance stems from the OpenMP dynamic scheduling policy. Finally, we found that these dynamic plans are not always balanced. Even when we use 4 times more cores, pattern stays strong and keeps the balance very good. We also did a blessing study tests on these matrices for both Intel and AMD CPU. Overall, the experimental results demonstrate a clear pattern. As the load balancing improves, ratio approaches 1, performance scales not barely. Partner consistently reduce the ratio to near its linear across 2 distinct CPU platforms. And scoring the effectiveness and scalability of the proposed load balancing framework. Okay, processing overhead, we use the 2,898 sparse matrices from the pseudo-sparse matrix collection as benchmarks to evaluate 4 parallel algorithms with pre-processing overheads, CAMLB, CSR5, CVR, and SPV8. The results indicate that their average pre-processing overhead is comparable to the parallel computational time needed for SPMV to perform 2011, 10, 15, and 87 iterations. Our method pattern only has very small costs for timing and search, binary search. The SPMV runs we do for timing are actually used for work that helps mass finish. For example, it's a relative solver, so it is not wasted time. Okay, that's all. This work will be on GitHub. On the left is my research craft as a student. We study how to optimize sparse computing for brain-inspired computing. And on the right is my page as a teacher. We research performance optimization for computations and optimization of supercomputing applications. Besides research, I have help students with supercomputing competitions. Okay, thank you.
All right, we have time for a couple of questions. All right, please introduce yourself.
Hello, very interesting work. And I have one question about, can this method be adapted to GPUs? And
GPU? Okay.
Yes. What's the main challenges?
Challenge. Okay. GPU. This work is in CPU. GPU is very high performance. I think GPU have a lot of SM, but we need to consider some warp or SIMD threaders. Okay. In the future, we can do GPU optimize about our work about load balancing. Okay.
Okay, thank you.
All right. Any other questions? Okay, would you mind passing the mic back?
Thank you. Very nice talk. I have a question. I have seen you have invited a lot of partition policy to do the load balancing. I'm wondering how much it will take to calculate this partitioning. Is there some overhead, and how much for each of them? And do you think you need some accelerate method, for example, develop some hardware specific for this partition part?
Partition, okay. Overhead. Part overhead is very low. First is invoking the timing functions. For example, OMP get double time or get time of day. The other is binary search. Binary search. Okay. This algorithm is very
fast.
Low time. Okay.
Thank you.
Any other questions? He has finished quite early, so he has gotten a lot of time credit. Now, I had one quick question to wind up before we wind up. So the load balancing, the way you are doing, seem to be very specific for SPMV kernels.
Okay.
How would you extend this idea to other popular kernels, like say Delaunay mesh refinement, or page ranking, or BFS that she talked about? Can this be extended to other such kernels?
Other work, okay. For example, SPMM, SPGMM.
Non-matrix multiplication. Non-matrix multiplication or non-matrix kernels. Matrix kernels looks similar, but I was just curious if it is.
Okay. The problem is very hard, but the future work, we need to our work to application to some industry about exam 像那个 solver okay 然后 this is our work.
Okay, cool. Thank you. All right, let's thank all the speakers of the session. This ends the session. Hope you have a good lunch. See you in the afternoon.
just wanna love you for my whole life. Do it for you, I'ma make time. I wanna kick it until midnight, just to be with you till the sunrise. I think you're making me crazy. Put my heart up on the main line. I got this trust for you. Got it 'cause I know what you like. I love you. Good and bad, thick and thin, flaws and all. And if you're ever in the wrong, I'll let you know. Yeah, I know that love is unpredictable, but I'm pretty damn sure that this is the kind of love that keeps me up all night. This is what I wanna do for the rest of my life. This is something that can get every bit of my time. This is what they call real love, real love, real love. You saw my halo, even on days when you should hate most. Laid up, I'm stuck with you. So tell me about it, how'd your day go? Kissing on me, missing on me. Every time I see you, got them feelings on me. Kissing on you, loving on me. I won't play with your heart. Good and bad, thick and thin, flaws and all. And if you're ever in the wrong, I'll let you know. Yeah, I know that love is unpredictable, but I'm pretty damn sure that this is the kind of love that keeps me up all night. This is what I wanna do for the rest of my life. This is something that can get every bit of my time. This is what they call real love, real love, real love. Oh, I know that you told me as long as you hold me, I couldn't be safer. No, love me for the real me. Don't know what your deal is, but I'm with you till daylight, 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 till the sun comes up, dancing in the moonlight, moonlight, moonlight. This forever, this forever. This is the kind of love that keeps me up all night. This is what I wanna do for the rest of my life. This is something that can get every bit of my time. This is what they call real love, real love, real love. This is.
You think you like it, you say it's your thing. Wait until you open it. Get that everybody wants it. Sorry, I'm say you're wrong. It's always green on the other side. Always green on the other side. It's always green on the other side.
All right, shall we start? Welcome to the Concurrent Data Structures session. My name is Călin Cascaval. I'm at Google DeepMind. Our first talk is going to be Quentin, talking about UFO trees, practical and probably efficient parallel batch dynamic trees.
Hello, hi everyone, thanks for coming. I'll be presenting our paper on UFO trees. I'm Quentin, and this is joint work with Atharva Sharma, Kishan Gowda, and our advisor Lakshman Dulipala, and we're all from the University of Maryland, College Park. So the problem that we study in this paper is the dynamic trees problem. And the goal in this problem is to maintain some data structure which represents an unrooted forest. And we want to maintain a data structure that supports efficient update operations. So the update operations that we consider in this problem are edge insertions, which we call link, and edge deletions, which we call cut. And while we're supporting these update operations, we also want to be able to efficiently query some information about the tree from this data structure. So the most common type of query we see in dynamic tree data structures is a simple connectivity query, which tells you whether two vertices are connected or not. So in this example, C and D are clearly connected, while A and B are not. Another very common type of query is called a path query. And in this case, we have some edge weights on the edges, and the path query should return the value of some function applied over all of the edges on some path. So in this example, we have integer edge weight on the path, and the function that we're doing here is the sum. So the sum of all of the edges on the path from U to V is 12. And a third type of common query for dynamic tree data structures is a subtree query. And in this case, we typically imagine there's weights on the vertices of the tree rather than the edges. And again, here we apply the value of some function applied over all of the vertex weights. In this case, we're doing sum again. So in the subtree rooted at V, the sum of the weights is 9. And so more recently, people have begun considering the parallel batch dynamic trees problem. And unlike the original dynamic trees problem, here you assume that the input to your problem comes in batches. So you want to process batches of multiple links together and batches of cuts and batches of queries. And in this case, the goal is to develop efficient parallel algorithms that can employ parallelism between all of the operations in a single batch. So why should we care about dynamic tree data structures? Well, dynamic trees are one of the most basic data structures in dynamic graph algorithms, and they're very useful for several more complex dynamic graph algorithms. For example, dynamic trees with path queries can allow you to implement incremental minimum spanning force algorithms or dynamic hierarchical agglomerative clustering. With subtree queries, you can implement fully dynamic graph connectivity or fully dynamic minimum spanning force algorithms. Also, dynamic trees can be used not only for more complex dynamic graph algorithms, but they can also be used to improve the running time of some static algorithms. For example, this linear time max flow algorithm uses a dynamic tree-like data structure to achieve the best known time bound in the static setting. So what are some solutions to the dynamic trees problem? The original solution was the link cut tree data structure. And this data structure only supports connectivity queries and path queries. And the cost of every operation is logarithmic. So what's interesting about this original data structure is, despite it being over 40 years old now, it's still the fastest sequential implementation that's known for this problem. Another really famous solution to the dynamic trees problem is Euler-Tour trees. And this is a data structure that can support connectivity queries and subtree queries, but it cannot support path queries like link cut trees can. And again, the cost of every operation for this is just logarithmic. Importantly, Euler-Tour trees were shown in 2019 to be the first data structure that can support efficient batch parallel updates. Okay, so let's add these two data structures to our table here. And in the rows, basically, we have some things that we might desire out of a good practical dynamic tree data structure. And so the first thing is good sequential performance. And like I mentioned on the previous slide, link cut trees have still the best sequential performance to this day, so this is excellent. Whereas Euler-Tour trees are still efficient, but they're not quite as good as link cut trees in the sequential setting. In the batch parallel setting, link cut trees are fully sequential. It's not known how to parallelize them, so their batch parallel performance is basically bad. Whereas Euler-Tour trees have excellent batch parallel performance because of the efficient batch parallel update algorithms they have. And for query support, we'll say both of these data structures have pretty poor query support because link cut trees can only support path queries and Euler-Tour trees can only support subtree queries. Okay, so now I'll introduce a new class of dynamic tree data structures that exists. And this class of dynamic tree data structures is based on static parallel tree contraction algorithms. And these data structures include topology trees and rate compressed trees. And basically, these data structures take some instance of a static parallel tree contraction algorithm, and they represent these rounds of contraction as like a binary tree. And I'll go into more details about this later. But basically, because parallel tree contraction is a really powerful technique in the static setting, this allows these tree contraction-based data structures to naturally support a diverse set of queries, which includes the 3 types of queries I mentioned earlier, as well as this list of many other queries. Also, because it's well known how to parallelize tree contraction, this means that these contraction-based dynamic tree data structures, it's easy to develop intuitive batch parallel update algorithms for them. So the problem with these data structures is they typically require a tree with all vertices degree less than or equal to 3. And this is obviously a really bad restriction because it severely limits the inputs that we can use it on. And so the typical solution to this problem is a technique called ternarization, where you map any input tree to a larger tree where every vertex has degree at most 3. And when you're doing this mapping, you maintain the properties of interest, such as the connectivity of the tree or, for example, the weights, the length of paths in the tree or subtrees. And so ternarization comes at a cost. The ternarized tree can have up to twice as many vertices, which means your data structure might use much more memory in practice. And perhaps more importantly, in a dynamic setting, if you have a single edge update to your original tree, in the ternarized tree, this can lead to up to 7 edge updates in this ternarized tree. And so although your asymptotic cost bound might be the same, this can give you really, really slow performance in practice, and we'll see this later in our experimental results. Okay, so let's add this class of data structures to our table. So like we said, because of these ternarization overheads, the sequential performance of these data structures is pretty poor. They do support batch parallel updates, but again, due to ternarization, they have pretty poor performance in the batch parallel setting. And like we said, because of them being based on tree contraction, they have excellent query support, and they can basically support any type of query that's of interest. And so now introducing our new data structure, UFO trees, our data structure is also based on tree contraction, so it has the excellent query support of RC trees and topology trees. But our data structure is the first one to not require ternarization. And because of this, our data structure can also get excellent performance in the sequential setting and excellent performance in the batch parallel setting as well, as we'll see later. Okay, so now we'll go into some technical details quickly. I'll be talking about topology trees because our new data structure, UFO trees, follows sort of a similar type of tree contraction. So first I'll talk about topology trees for a bit. So the tree contraction algorithm here basically merges a maximal matching of clusters in each round. And the types of merges you can do is you can merge a degree 1 cluster with degree 1, degree 1 with degree 2, degree 2 with degree 2, or degree 3 with degree 1. And in later rounds of the tree contraction, we say the degree of a cluster is the number of edges incident to that cluster. And so this set of allowed merges ensures that in every round of your tree contraction, the degree of every vertex stays less than or equal to 3, and you have a geometric decrease in the number of vertices. So the topology tree basically represents this tree contraction process as a rooted binary tree, where 2 clusters that merge together have a parent representing the cluster in the next round. And because of the properties of our tree contraction, the height of this tree is logarithmic and the total space is linear. Okay, so let's talk about how you process updates in this data structure. At a high level, basically, the update works like this. First, you delete clusters in the topology tree whose contents have changed, and then you recluster the tree bottom up. So in this example, if we're cutting the edge HI, these clusters highlighted in red have had their contents changed. And these are all the clusters that are ancestors of the endpoints H and I of the update. And because the contents of these clusters has changed, our algorithm should basically delete them because the contractions they represent may no longer be valid or maximal. And so once we've deleted all these clusters, now we have a bunch of components that are separate, and they basically no longer represent a valid instance of our static tree contraction algorithm. And so our algorithm now is just going to basically recluster these components bottom up. And it's going to look like this. And I won't go into all the details here, but in our paper, we prove that these updates can also take logarithmic time. Okay, so now I'll talk about our data structure UFO tree and how it differs from topology trees. So topology trees requires us to merge clusters in pairs. And because of that requirement, it's limited to inputs with degree up to 3. And the reason for this is if you have a really high degree vertex, say this vertex C, this has degree 4, but if you imagine that the vertex C had like degree 1,000,000 or something, if the topology tree has to merge clusters in pairs, this really high degree vertex would have to merge with every one of its neighbors one by one. And this means the tree contraction algorithm could have many, many rounds, and you have a topology tree with really high height. And because of this, the topology tree requires ternary. On the other hand, our UFO tree data structure will allow some certain cases of merging multiple clusters together in a single step. And this allows us to avoid ternary. So specifically, we have the same first 3 rules as topology tree, but we add this new 4th rule, which is you can merge a high degree cluster with all of its degree 1 neighbors. And we define a high degree cluster as having degree greater than or equal to 3. And so with this new rule, the tree contraction basically can only take log n rounds. And so the height of our UFO tree will still be logarithmic. And okay, so here's just this example for the UFO tree. And you notice this high degree vertex C merges with all of its degree 1 neighbors in the first step. And one thing you might notice now is that the UFO tree is no longer a binary tree. Some of these internal nodes can have much more than 2 children. And so this is a challenge for updating the tree, because if you remember, our update algorithm basically deletes any clusters that were changed and reclusters all of the components bottom up. And so if you delete a cluster with many, many children, say you have like a million children, then reclustering all of these children will be way too expensive. And so our solution to the problem of high fan-out clusters, which we define as having greater than or equal to 3 children, is pretty simple. Our solution is just don't delete the high fan-out clusters or the high degree clusters. And in our paper, we basically prove that you can avoid deleting high fan-out and high degree clusters, and you can still correctly recluster the tree. So in this example, if we're deleting the edge CF, in red we highlight all of the clusters that have changed, where the topology tree algorithm might delete all of these red clusters. Now the UFO tree update algorithm is instead going to not delete these high fan-out clusters, which are marked with black lines, but it's going to delete every other cluster. And then again, the algorithm updates it bottom up and finishes reclustering the tree. Okay, and so now I'll give a quick overview of our batch parallel update algorithms. And so the general flow is the same as the sequential setting, where we first delete any change clusters, or for UFO trees, we delete only some of the change clusters, and then we recluster the tree bottom up. And in the sequential setting, there was only a constant number of change clusters per level. But in the batch parallel setting, there's O of k change clusters per level, where k is the size of the batch. And this gives us the opportunity to do some parallelism when you're reclustering every level. So basically, we use a parallel maximal matching algorithm where the matching obeys the rules we said earlier. And the way it works is like this example. So there may be some existing merges, which are indicated in purple, and the rest of these clusters have to be rematched, basically. And so for high degree clusters, our rule was that a high degree cluster can merge with all of its degree 1 neighbors. And since degree 1 vertices are only next to that high degree cluster, there's basically naturally no contention between high degree clusters. So we can basically recluster these all naively in parallel. And so the remaining clusters that need to be reclustered are basically chains of degree 2 nodes. And we can handle this using a list ranking algorithm, parallel list ranking. And so in practice, we actually use an interesting asynchronous greedy matching algorithm, which you can read more about in our paper, or I'm happy to discuss it after. Okay, so now going back to this table, I'll share some of our experimental results and hopefully prove these claims that we made here. So for sequential performance, we claimed excellent performance for linked cut trees and UFO trees. And here's our sequential experiments. So every group here shows a different input, and the bars report the total time to insert all the tree edges and then delete all of the tree edges in a random order. And in the top row, we have various synthetic trees with n equals 10 million, and in the bottom row, we have some spanning trees of real-world graphs. And so the first thing you might notice is the ternarized data structures, which are topology trees and array compressed trees, they do suffer a lot from, they have poor performance sequentially because of the overheads of ternarization. And the next thing to notice is linked cut trees and UFO trees are consistently the fastest 2 data structures in our experiments, which is the one in light green and the one in black. And another interesting thing is we noticed that link cut trees and UFO trees are particularly good on low diameter inputs, such as the star case, and also such as like the BFS graph for low diameter graphs. And so to explain this really good performance on low diameter inputs, we did this other study where we basically generate synthetic trees with gradually decreasing diameter. And we saw that both link cut trees and UFO trees sort of became gracefully faster as you decrease the diameter of the input. And we saw that this is true for both updates and two types of queries. And so to explain this phenomenon we saw in our experiments, we proved these theoretical bounds, which is that UFO trees have also an O of D cost per operation, where D is the diameter of your input tree. And similarly for link cut trees, we proved an O of D squared cost per operation. Okay, and so now looking at batch parallel performance, again, we didn't study link cut trees here because it's not known how to parallelize them. So we basically took the same inputs and we batched them all with a batch size of 1 million. And in these results, again, we see that the ternarized data structures, which are topology trees and rate compressed trees, they suffer a lot also in the batch parallel setting, and their performance can be orders of magnitude worse than the other two data structures. And so here we saw that Euler-Tour trees have relatively stable and fast performance regardless of the input. And so UFO trees can sometimes beat Euler-Tour trees, especially on low diameter inputs. They can do a lot better, and they're never more than 3 times slower. And this is all while having a much higher support for queries. Euler-Tour trees can only support subtree queries, where UFO trees can support many, many more queries. And so this is the main takeaway of our paper, was that UFO trees are the fastest dynamic tree data structure that supports both parallel operations and all types of queries. Okay, that's it. Thank you.
Questions? I have a question. In your clustering algorithm, right, you said you are joining the node with the highest degree with all its 1 degree neighbors. But well, your examples were a little bit degenerate. Only one of those nodes had another connection. If you have multiple of these, which ones do you pick?
You mean if you have multiple high-degree clusters?
If you have a high-degree cluster connected to multiple nodes, there you split the cluster in like node C, D, F. I think it was like a separate node. Oh, we can look at this figure, the other figure. Yeah, F, you split out. It's still a 1 degree connection to C. But you pick that as a separate node. Well, go to the other figure, the bigger one, the larger tree that you had in the later slide.
Oh, you mean, okay.
Yeah, so in this slide, assuming that one of your other nodes will also have branches.
Right, right. So good point. Yeah, so basically when you're doing this reclustering, every degree 1 cluster can basically join onto its high degree neighbor. So the high degree cluster can only merge with its degree 1 neighbors. So for example, if you had a high degree cluster that's sort of in the middle of a chain, it's not allowed to merge with its degree 2 neighbors, only its degree 1 neighbors. And so basically the degree 1 neighbors can just basically join into the cluster with the high degree neighbor.
Okay. Thank you. Next speaker. Our next speaker is AJ, talking about sharded elimination and combining for highly efficient concurrent stacks.
So just a second. Okay, all right, yeah, thank you. Hello everyone, I'm Ajay Singh. I'll talk about faster concurrent stack implementation, which uses sharded elimination and combining. This is joint work with Nikos Metaxakis and my postdoctoral advisor, Paniota Fataru from ICS 4th and University of Crete. So concurrent stacks are fundamental to concurrent applications, and they are used in systems which use inter-process communication structures, or scheduling techniques, memory pools, graph algorithms, or for free list and garbage collection. These stacks provide last in, first out order semantics, where thread modify a shared top pointer using concurrent push or pop operations. However, the problem in terms of performance is that the top pointer becomes a contention hotspot, causing synchronization overheads, and also forms a sequential bottleneck, which limits the throughput or scalability of the concurrent stack. Combining and elimination are two approaches which have kind of impactful solution for this bottleneck issue. In combining, threads delegate their operations to a designated combiner thread, which actually performs the operations on behalf of all the other threads. And therefore, threads are able to avoid repeated access to the shared top pointer, and as a result, they can reduce the synchronization overhead. In elimination, a push can cancel out a concurrent pop, because a push followed by a pop actually has no effect on the stack's state. So this allows both operations to complete, and thereby so it allows operations to complete without even accessing the shared top pointer, right? So this kind of leads to better concurrency in the stacks. So in effect, both these techniques help in reducing the synchronization overhead and also the sequential bottleneck. And as a result, we see lower cache invalidation traffic at the top pointer of the shared stack. There are several implementations which use these approaches. We'll talk about a few which are known to perform well. In elimination backoff stack, which is EBF here, that uses an elimination array as a backoff mechanism. However, the problem here is that it can have high overhead per push-pop pair. And additionally, push-pop pairs may not always eliminate each other despite being concurrent. So in CC-based stack, which was proposed by Fataru and Kalimanis in PPoPP 2012, uses a FIFO list of push-pop operations for combining. And the problem here is that it limits maximum achievable concurrency, because while the combiner is executing, other threads are simply waiting and cannot eliminate or combine concurrently. The TSI, timestamp interval-based stack, is interesting in the sense that it organizes stack as a pool of timestamp nodes, and therefore it has fast push operations, but at the cost of slower pop or peak operations. So we propose sharded elimination and combining, which is a lightweight method that unifies elimination and combining, and as a result, it gives a fast and scalable concurrent stack. This technique essentially uses aggregating and batching structures, which helps in dividing and localizing the contention, which is sort of like similar to the technique used by PPoPP in PPoPP 2025 by Johan Wei, Rupert, Fataru, Jayanti, and Shun. So SEC's per batch 2 counter-based approach significantly lowers down the contention in elimination and combining, such that the elimination combining happens parallelly across batches, unlike CC stack. And also, it helps in eliminating all the push and pop operations per batch, which is unlike EBF, which is elimination backoff stack. And it additionally also helps in determining the return values of the combined operations in much more simpler and efficient way. So at high level, the SEC consists of multiple aggregating structures, which helps in distributing contention across threads. And each aggregator can have multiple batches. Each batch allows threads to cooperatively do elimination and combining. And this happens in parallel with a subset of threads, which helps to localize the contention within a batch. Additionally, each batch has one active batch. So each aggregator has one active batch, where multiple threads can announce, the newer threads can keep on announcing their push and pop operations. And finally, we have a shared stack where all these operations are applied to. So to zoom in, each aggregator's batch has an elimination array where threads announce their push and pop operations, and some shared metadata which is used to count the number of push and pop operations in an active batch, as well as it helps in doing elimination and combination. So threads execute in 3 phases: freezing, elimination, and then combining. In freezing phase, threads determine which push and pop operations are eventually going to be the part of the active batch, and therefore they will participate in the next phases, which is elimination and then combining. And to do that, it uses 2 fetch add counters, which is the part of the metadata, one for pushes and the other for the pop operations. In the elimination phase, threads determine which are the matching push-pop pairs so that they both can complete in such a way that pop returns the value of the announced matching push operation. And therefore helps to kind of increase the concurrency. And after the elimination, the batch can either be empty or can have only push operations or only pop operations. So in combining phase, if the batch is left with all push operations, then a combiner will create a substack and will apply to the shared stack. And if all operations are pops, then the combiner will remove a stack from the top of the shared stack, and then other threads can scan this removed substack and find the return values to return. So let's delve deeper into each of these phases. In freezing phase, threads announce operations in their aggregator's active batch, and the way they do that is that threads first get a slot in the elimination array using fetch and add on either push count or pop count, depending on whether the operation is a push or a pop. So for example, let's say there's a thread A with a push operation, so it will come in and then do a fetch and add on the push count shared variable here, changing it to 1, and then it will get a slot 0, wherein it could announce its shared node which it wants to push to the shared stack. Similarly, thread B with the push operation will increment the push count to 2 and will get a slot 1. Thread C with the push operation will increment the count to 3 and will get the slot 2. And similarly, thread D will increment the push count to 4 and will get the slot 3. And each of these threads will add their shared nodes they want to add to the shared stack in their slots they receive. Similarly, let's say there are a few pop operations. So let's say thread Q with the pop operation comes in. This time it will increment the pop count to 1 and will get a slot 0. Similarly, thread R with the push pop operation will increment the pop count to 2 and will get the slot 1 in the elimination array. So threads can continue arriving with their push and pop operations. So at some point, they have to decide which operations are going to be the part of this active batch to kind of participate in elimination and combination later on. So to do that, threads do kind of follow a freezing mechanism wherein 2 slot 0 threads execute a test and set on is freezer decided shared variable, and the thread which kind of succeeds on doing this test and set sets this test is freezer decided variable to true and becomes the freezer of the batch. And then it goes on to execute a 3 freezing actions, and while other threads simply wait for this freezing thread to finish the freezing mechanism. So as part of these its freezing actions, it saves the pop count and the push count in its pop count at freeze and push count at freeze shared variables. So let's say in this example, the push count at freeze becomes 4 because that's the push count at that time in the active batch, and the pop count at freeze becomes 2. So then the freezer changes the active batch, and this way other threads learn that the freezing mechanism has been completed, so they can go on to execute next step. And as part of the next step, threads try to decide whether they are the part of the batch or not. So the way they do that is they compare their slot value with either pop count at freeze or push count at freeze, again, depending on whether it's a push operation or a pop operation. And if they find out that they are not the part of this active batch, this frozen batch, they have to retry from a subsequent active batch. Otherwise, they go on and then execute in the next phase, which is at the elimination phase. In elimination phase, threads check for whether they have a matching operation or not. So for example, if the thread has a push operation on the elimination array, then it compares its slot value with the pop count at freeze, and if it is lesser, then it learns that there is a matching pop operation. And if it is doing a pop operation, then it compares its slot value with the push count at freeze, and if it is lesser, then it learns that there is a matching pop operation for it to eliminate with. So for example, in this case, thread A, which is doing push operation, has a matching pop operation that is Q, that is from thread Q. And thread B is executing the push operation, which has a matching pop operation from thread R. So both of these threads can exchange their values and simply cancel each other out. So the way they do that is that push operation simply return true, and the pop will return the value of the push operation announced on the particular slot. So these threads eliminate each other, and then the remaining threads, which is thread C and D, will go on into the combining phase. So in the combining phase, the first non-eliminated thread becomes the combiner, which applies the operations on the other threads we have. So while it is doing so, other threads will wait for the combiner to complete to return their own responses. So there could be two cases. First is all operations are push operations in the elimination array. In that case, let's say the current state of the shared stack is that it has two nodes, N1 and N2. So combiner will create a substack of the two nodes in the elimination array, and then with a single compare and swap operation, will push the substack to the shared stack. And then it will set the is batch applied to true, which will help other threads which are waiting to learn that the combining mechanism has finished, so all the push operations can simply return true. The second case is that all operations in the elimination area are pops. So in that case, let's say the current state of the stack is that it has 4 nodes, node N1 through node N4. And what the combiner will do is that it will pop out 2 nodes out at the top of the stack. So in this case, N1 and N2 are the substack, which is popped out. And then it will set the is batch applied shared variable of the batch to true, so that other threads will learn that the combining mechanism has completed. And threads can then simply go on and scan this substack. So thread C with the push operation will return the value from the node N1, and thread D of the push operation will return the value from the node N2. So now coming to the evaluation part, so we compare SEC on this 56-thread machine, and we compare it with CC-based stack, EBF, which is elimination backoff stack, FC, which is flat combining, and TRB is the popular reverse stack, and TSI is the timestamp interval-based stack, which we saw earlier in the slides. So the y-axis here shows the throughput, higher is better, and the x-axis shows the number of threads. So, and we have the slide for 10% update rate and the 100% update rate. In the 10% update rate, 90% of times threads just simply do the peak operation, that is, they simply read the top of the stack. So as we see in here, SEC can be up to 2 times faster than the next best algorithm. And on a 96-thread machine, we see the similar trend. Okay. So in conclusion, we have this linearizable but blocking fast concurrent stack, which unifies elimination and combining approaches in a very lightweight method. And the key approach is that it has aggregating and batching structures, which help in dividing and localizing the contention between threads. And its per batch 2 counter approach significantly lowers down the overhead of both combining and elimination in a way that the batches execute the elimination and combining in parallel, as well as the push up and pop pairs within each batch, unlike EBF, eliminate each other. And additionally, it helps in determining the return values of the combined operations in a very efficient and simpler way. In paper, we have a discussion on how do we reclaim the stack nodes and the batches, plus also we talk about the correctness, and we have some more experiments on different machines with different configuration and workloads. So thank you, and I guess I can take questions now.
Questions?
Ruslan Nikolaev, assistant professor from Penn State. So it's a nice talk and nice technique. I'm just kind of curious, even though it's orthogonal to your talk, but when you allocate batch, can you potentially end up with unbounded number of batches? Because I'm assuming you use an epoch-based reclamation, right? And you're not specifically limiting the number of batches, right?
Yes, that's true. So we are using epoch-based reclamation, basically a Debra algorithm. And of course, we can technically have unbounded number of batches, but they're being reclaimed.
Yeah, that's kind of, I think, the same problem with the, with the PPoPP 25, but I'm just kind of curious, right? Yeah, so just kind of,
So, but like, if it makes it easier to understand. each aggregator has a fixed number of threads assigned with.
Yes.
So kind of, and then they are being divided. So it does keep the number of batches at minimum, but they could still theoretically be.
Yeah, I think there can still potentially be, right?
Yes,
so yeah, okay, okay. Thank you so much.
But I think like reclamation should be. So you can apply other reclamation techniques like hazard pointers as well in here, because reclamation is easier in the sense that combiner. So let's say there's only single thread, right? It's combiner, and that's responsible for a batch. So it knows that when to reclaim, and so it can just like retire it, and whenever other threads kind of give up their pointers in the batch, it could be reclaimed. So
yeah, but
you can use other techniques.
So in other words, you're
lock-free.
saying that they will eventually be limited by the number of concurrent threads, right?
I'm sorry,
the bound will be the number of concurrent threads, right? Eventually, or not?
Yeah. Yes. I think so. I mean, I have to think deeper.
Okay.
Oh,
okay.
yes.
That's
So,
fine.
yeah,
Yeah. Thank you so
exactly.
much.
Yeah. Sure. Sure. So the bound would be the number of threads. Yeah. Yeah.
Thank you. Next speaker. Our next speaker is Evan Wrench, and he's going to talk about concurrent balanced augmented trees.
Hi, everyone. I'm Evan Wrench, and I will be talking about our paper titled Concurrent Balanced Augmented Trees. So this is a collaboration with Ajay Singh, Yoon-Hoon Roh, Panayota Fatoro, Siddhartha Jayanti, Eric Rupert, and Yuan Hao Wei. Augmented search trees are defined as binary search trees where each node stores an extra bit of information about the subtree that is the root of. So this can be something like the minimum or maximum key of the subtree, but for our purposes, it will be the total count of number of keys in the subtree. We're also working with leaf-oriented trees here, so in our example tree, only A, C, and E are in the set. The other nodes are just used for routing purposes. So here, the leaves all have augmented value 1, and the root has augmented value 3, since it contains all 3 leaves. And the reason we'd want to do this is because it allows us to perform some queries in time proportional to the height of the tree, where otherwise it would take time proportional to the number of elements in the set. So for example, rank and select queries give us information about the relative ordering of items in the set, and range algorithm queries allow us to gather information about items within a set interval. So these augmented trees are pretty well studied in the sequential setting. For example, CLRS, which is a well-known algorithms textbook, has an entire chapter devoted to them. However, in the concurrent setting, not much work has been done until recently. So for example, Sell and Petrank provided 2 algorithms for a lock-based unbalanced tree, one for efficient updates and one for efficient queries. However, the augmentation that they use is constrained. So for example, the augmentation function requires an inverse. Kokorin et al. Proposed a weight-free balanced tree, but with the same type of constrained augmentation. And finally, Fatoro and Rupert proposed a lock-free unbalanced tree with an unlimited augmentation function. So our goal for this paper is to combine the benefits of all of these and design a scalable, lock-free balanced BSD that has no limit on the type of augmentation. We will be basing our tree on the work of Fatoro and Rupert on their lock-free augmented unbalanced tree. So first, I'll talk a bit about how their data structure works. Designing a concurrent augmented tree is difficult because after an update, you have to modify the augmented values of multiple nodes, and this has to appear to take place instantaneously in order to maintain the correctness property. So the way they deal with this is that they separate the tree into 2 different connected trees. So here we have a node tree, which is mutable and stores all the keys in the set. And each node points to a version node, which contains the key and its augmented value. So here, the version tree is immutable, and it's updated through a path copying operation. And the idea is that the version tree provides a snapshot of the node tree after a certain set of operations have taken place. And any queries can simply read the version of the root node, and then perform their normal sequential algorithm after that. And yeah. So I'll now talk about how an insert is performed on this tree. Performing a deletion is very similar. So basically, you perform a normal BST traversal from the root to the leaf, and as you traverse downwards, you add any nodes visited onto your stack. Next, you create a new subtree with one internal node and two leaf nodes. One leaf node for the final leaf you visited on your path, and one for the new key you're trying to add. In this case, it's F. So to install this into the node tree, you do a simple compare and swap from the parent of the leaf into this new subtree. If you fail, you simply restart all over again. So now we have that F is inserted into the node tree, but the nodes on our stack now have an incorrect augmented value. For example, the root B has an augmented value 3 when there are now 4 keys in the set. So to remedy this, we start at the top of the stack, and we create a new version node that points to the versions of the children of our current node, and whose augmented value is the sum of their augmented values. And to install this into our new node, we do a compare and swap, and we call this event or refresh. So if our first refresh fails, we try another refresh, and if this fails, they have proven that you can move on to the next node in the set without having to worry about correctness. So we simply continue this with the root here, and after our algorithm finishes, we now have that every node in the tree has a correct augmented value. So again, our contribution is to design a balanced, scalable augmented tree. For the balanced part, we will be adding rebalancing to the lock-free algorithm that we just mentioned. And for scalability, you might have noticed that for each update, it eventually has to update the augmented value of the root. So this creates a high degree of contention at the root. So another goal of ours is to find a way to reduce this in some way. In order to maintain the balanced invariant of our tree, we have to perform certain rebalancing steps. So these can be modeled as taking a patch of nodes in the tree and replacing them with a new patch that has the same keys but in slightly different orientations. And this can be done with a simple pointer swing. So in this case, F scry child is changed from the old patch to the new patch rooted at H prime. We also have that these new nodes cannot start off with versions already installed, because if we have a concurrent update that's refreshing nodes in the old patch immediately before we install the new patch, we can actually lose these updates. So instead, we assign these new nodes to have what we call placeholder versions. And these just indicate that the next update that sees a placeholder version has to recursively fill it in, and any children that also have placeholder versions. So here, if a concurrent update sees that H prime has a placeholder version, it first updates G prime and then H prime, and then it can safely continue on its refreshing. In order to motivate our balanced algorithm, we need to talk a bit about the correctness of the unbalanced algorithm. So here, our stack sort of models a path from the leaf to the root, and we want to maintain the invariant that at any point when we're refreshing a node, one of its children has also been refreshed. And this implies that after we perform a refresh, the update has successfully been brought up to the next level in the tree. This is pretty easy to see if there's no concurrent updates going on to the node tree at the same time. However, we can have concurrent inserts and deletes that modify the tree as we perform these refreshes. So here, we've already refreshed node C and B, and we're trying to bring that update up to node E. So if we have a concurrent insert, this can actually only happen at a leaf, so this doesn't affect our path in any way. And if we have a concurrent delete, this can remove a node in our path. However, we now point to a different node in our path that we know has also been refreshed. So no matter what happens, we can successfully bring our update to the next level. So our invariant holds, and eventually we can bring our update up to the root. However, in the balance case, we now have these rebalancing steps, that can potentially add new nodes onto our path. So, for example, if the node D gets added onto our path here, eventually we will reach node E, and at this point, the child of E has not been refreshed since it was added in the rebalancing step. So our invariant doesn't hold here, and our update will not get correctly brought up to the root. And this motivates the idea that somewhere in our algorithm, we have to add new nodes onto our stack to refresh. So how we do this is at every node, we first check if the child has, or we keep a set of nodes that have been refreshed. And at every node in our update algorithm, we check if its child has been refreshed. And if not, we have a phase where we traverse downwards and add any nodes that haven't been refreshed onto our stack. So if the same thing happens here, where node D gets rotated onto our path, we still update C and B normally. But at E, we notice that node D, which is our child, hasn't been added to the refresh set. So we traverse downwards and add it onto our stack. And then finally, node D sees that its child has been refreshed, so we can continue as normal. And eventually, the update gets correctly brought up to the root. Crucially, after we perform a successful check that our child is in the refresh set, it can be changed by a concurrent operation, like in a rotation, for example. However, we can prove that the new child that gets installed immediately after this check will have an up-to-date version as soon as it's read. So this graph shows the performance of the unbalanced augmented tree in purple and our balanced augmented tree in blue. We only compare the update performance since the query performance of both is exactly the same, or the algorithms for both is exactly the same. So we can see here that the adding balancing significantly improves throughput after multiple threads are involved. And the reason for this is because the benefits of adding balancing outweighs the overhead. So an example of overhead is that we now have to refresh more nodes from the phase where we move downwards in the stack. However, our experiments showed that this only accounts for 6.4% more nodes on average. Another example of overhead is the filling in of nil versions that we mentioned earlier. However, again, each update only has to do around 0.75 of these. And finally, there's the cost of actually performing these rebalancing operations. However, the tree update template we use has a constant number of these amortized per update. And these are weighed against the benefits of balancing the tree. So with a balanced tree, you not only get better theoretical balance for updates, but we also saw a 20% lower average depth on a uniform workload. So this is a workload where keys are inserted and deleted uniformly at random. And for workloads where keys are inserted and deleted in a way that leads to a more unbalanced tree, we saw an even higher benefit. So now that we've added balancing, we also want to find a way to reduce contention at higher levels of the tree. So the problem with contention is illustrated here. We can have, for example, multiple processes, P1, P2, P3, and P4, all updating the same level of the tree at the same time. Now this is usually okay in lower levels, but once we start traversing to higher levels of the tree, we now have two processes updating the same node at the same time. And then finally, for levels 3 and 4, all 4 processes are essentially doing the same work of updating the same node. So yeah, this essentially creates a sequential bottleneck at higher levels of the tree. And the way we fix this is we add a delegation mechanism to our algorithm. So if 2 processes are updating the same node at the same time, since we're doing a compare and swap, only one of them will succeed and the other one will fail. So essentially, the one that fails, in some situations, it can delegate the remainder of its refreshes to the one that succeeds, just because the remaining path that they have to traverse to the root will be the same. So here, if P1 fails and P2 succeeds, P1 can delegate its work to P2. And so P1 will just stay at node B and spin until P2 completes the final update of the root. Similarly, P3 can delegate to P4 at node F. And finally, if P4 succeeds and P2 fails at node D, only P4 can move on. And finally, we only have one process updating the root, which is a big improvement So yeah, this can potentially exponentially reduce the amount of contention we have in our tree. There's a few conditions for when a process can delegate to another. I'll only go over one of them for time reasons, which is that we can't actually delegate inside a node that has been removed due to a concurrent rebalancing operation. So here we have two processes, P1 and P2. P1 is performing refreshes starting from node A, and P2 starting from node B. And after they've built up their stack, this patch of nodes rooted at node D has been rotated out of the tree. So here, the algorithm will first, or both processes will both bring their updates up to node D. And at this point, P1 succeeds in refreshing D, and P2 fails. So P2 delegates to P1, and only P1 moves on to node R. So here, P1 notices at R that its child has not been refreshed, so it begins the phase of moving downwards and adding nodes onto its stack, and eventually gets to node A, which has been refreshed. And now, crucially, when it starts moving backwards up to node R, since it only traversed downwards to A, only P1's update will be brought up to node R, and so essentially P2 incorrectly delegated to P1 since its update is lost at node D. So here we see the scalability improvement that this brings. So again, the purple line is the unbalanced augmented tree with no delegation, and the blue line is the balanced augmented tree with no delegation. So the new green line is our balanced augmented tree with this delegation mechanism. So here we can see that after about 30 threads, delegation starts to add some improvement to our performance. And once we reach 180 threads, the algorithm with delegation is over twice as fast as the one without delegation. And this is because each update has to refresh about 4.8 less nodes on average at 180 threads. We also compare with some unaugmented trees. So here, the purple line is the unbalanced augmented tree with no delegation, and the green, again, is our balanced augmented tree with delegation. And the orange, red, and blue lines are all unaugmented trees. The x-axis here is the percentage of rank queries in their workload, and rank queries are one of the queries that benefit significantly from augmentation. So even with a workload with 0.1% of rank queries, our balanced augmented tree with delegation is essentially just as good as the best performing unaugmented tree. And once we get to higher percentages of rank queries, the balanced augmented tree with delegation is orders of magnitude faster than the unaugmented trees. So in summary, we've designed a scalable, concurrent, balanced augmented tree that has strong theoretical bounds for updates and is also efficient in practice. We've also introduced a delegation mechanism to reduce contention at higher levels of the tree. And this works through both the unbalanced and balanced variants. And finally, in our paper, we have a full proof of correctness and experimental comparison. Thank you.
Questions?
Hi, I was wondering what kind of balancing scheme you use for your trees, and is it possible to extend your methods to different types of balanced trees?
Yeah, so the one we use is called a chromatic tree, which is basically a relaxed variant of a red-black tree. So in our proof of correctness, our algorithm works for pretty much any variant of balancing where you replace one patch of nodes with another. So yeah, I agree. I think it would be interesting to try to apply it to some other types of balance trees.
Thanks. And also, do you think it's possible to support update operations where you change the value at some leaf in the tree rather than just deleting it and reinserting it?
Do you mean like changing a specific key or something like that?
Yeah.
Okay. Yeah, I think the algorithm should be pretty similar in that case. Yeah, because if you're not inserting or deleting a key, I think the augmented values stay exactly the same. So I think, yeah, the extra work you have to do due to the augmentation, you probably wouldn't have to do in that case.
Okay, thanks.
Yeah, I got a question maybe similar as Quentin's as well. So you said that you use, I assume that you use a tree rotation to perform the rebalance, right? Because you said you are red-black trees. I was wondering, is there any maybe intuition that if we want to rebalance tree like using the reconstructions, and do you have maybe any ideas how we can make concurrent updates if we want to rebalance tree using a reconstruction?
I think, so the question was, like, how does balancing, I guess, from a high-level point of view, how does balancing affect the augmentation technique? Is that?
Yes.
Yeah, so I guess the reason why we need this template of replacing one patch of nodes with another is that we're allowed to sort of, as we bring updates up to the tree, we're allowed to fill in the versions. We're allowed to fill in versions a little bit later, I guess, with these nil pointers. So if you did have a balancing template where like nodes physically get moved around, you're not just replacing one patch of nodes with another, I guess, like, while you're bringing up, while you're refreshing nodes, you can get to a node that then gets rotated onto a different path, so that sort of complicates things. Yeah, and I can't really think of a logical way to modify the algorithm to fit that case.
Yeah, okay, I see, thanks.
Yeah.
Any others? Thank you. And our next speaker is Zhang? Yes, Zhang Meng, talking about parallel dynamic spatial indexes.
Okay. Hello, everyone. Good afternoon. I'm Ziyang. I'm a graduate student at UC Riverside, supervised by Yihan Lian. I'm glad to introduce our recent work about the parallel dynamic spatial indexes. This is joint work with Bo, Yan, and Yihan. The story begins at the spatial data. Spatial data are geometric objects in the real world, which are generally points in 2 to 3 dimensions. And the spatial data has been widely used in many real-world applications, such as geographic system, computer graphics, and robotics. The spatial indexes are used to manage spatial data efficiently. They always organize the points in a tree, where each subtree corresponding to a subspace. And there are 3 commonly used spatial indexes, namely the KD tree, the OS tree, and the R tree. The KD tree splits at the object median, so that the 2 subtrees have same number of points. And since the tree is fully balanced, so KD tree has fast queries. But the KD tree generally have slow updates because maintaining the object median is very expensive. And the next one is the OS tree, which is known as the quad tree in 2D and the octal tree in the 3D. And the OS tree splits the space evenly at the mid. And since the computer spatial mid is much easier than the object median, so OS tree can be faster in updates. But the tree can be skewed if the inputs are not uniformly distributed, so OS tree is generally slower in query. And the last one is the R tree. Unlike the KD tree and the OS trees, R trees are object partitioning trees, and the points are grouped using different heuristics. And the query using R tree is generally slower than others, because as we see, the different subtrees may overlap with each other. And meanwhile, since the points are grouped heuristically, the R tree is generally the fastest one on updates. Okay, these spatial indexes have many advantages, such as using linear space and support a wide range of queries. And actually, since they were proposed in the 1970s, they have been widely used in different registries, such as in databases and machine learning. But 50 years ago, the data size is very small, and a good serial implementation is enough. But now we have seen that the data volume grows more and more large. Like, for example, the data set OpenStreetMap contains about 10 billion of the records. And we find it takes about 1 hour to build an index for only 1 billionth points in serial. And meanwhile, the real-world applications involve more and more dynamic data. So it's imperative to consider parallelism for these spatial indexes. And in this work, we focus on the case that points are inserted or deleted in different batches. And this is known as the batch update, which is a common method to improve the throughput for updates. And we will focus on the construction and updates. And the queries are generally won't modify the tree structure and can be trivially parallelized. Okay. But unfortunately, we are only aware of limited work about the parallel spatial indexes. And in the well-known open source library, such as CGO and Boost, most of the indexes are serial. And the only exception is that the KD tree in the CGO, but it has non-scalability issues. And our PKD tree in Sigma last year is a state-of-the-art parallel KD tree that achieves optimal bounds and high parallelism. It's fast in the static case, but has high update bounds. And the ZD tree in the LNX22 is the first parallel OS tree. It has better update bounds than the PKD tree, but it can be twice slower in the practice. Well, this is not desirable because we assume that the OS tree should have faster updates than the PKD tree. So there must be something that we can do to improve the performance of the OS tree. And meanwhile, we are not aware of any parallel R tree that supports parallel updates. And most R tree focus on incremental updates or just fully rebuild during updates. Okay, so we see that different indexes have their own strengths in the serial setting. So it's natural to ask whether these indexes can still leverage their strengths for highly dynamic workloads in the parallel setting. And the answer is, of course, yes. And in this work, we propose the POS tree, which is a parallel OS tree that achieves up to 3 times speed up over the PKD tree. And meanwhile, it provides a similar query performance as the existing solutions. And besides, we also propose the first parallel R tree with batch updates, and we call it aspect tree. It achieves up to 5 times speed up over the PKD tree with similar query performance as existing. So to collect all of this together, we propose the PSI, the scilib. It's a collection of our design of the parallel OS tree and R tree in this work, and also our PKD tree at Sigma last year with batch updates. The implementation provides both strong theoretical guarantees and highly efficient performance, which preserves the strengths of different indexes in parallel and dynamic workloads. And besides, we also perform a comprehensive evaluation for these indexes to identify their best use cases in the real-world applications. And overall, with the scilib, we close the gap between the wide usage of these spatial indexes and the lack of highly efficient parallel implementations. Okay, now we turn to our design of the parallel OS tree. Recall that the OS tree splits the space evenly at the mid, and it generally provides faster updates and slower queries than the KD tree. Before we go more in detail for our solutions, let's first figure out why existing R trees are slow. We find that the reason could be almost every existing OS tree uses a technique that calls a spatial fitting curve to handle the construction and updates. The spatial fitting curve maps high-dimensional data into an ordered integer sequence, so that we can use a 1D data structure, such as a binary search tree, to manage multiple dimensional data. And another advantage using SFC is that it enables integer sorting and can make the following construction or updates cache efficient. But the downside is that the SFC supports only for 2D or 3D points, and higher dimensional data will suffering from the precision issues. And there are 2 commonly used SFC, namely the Z-curve on the left and the Hilbert curve on the right. The difference is that Z-curve is cheap to compute, but the Hilbert curve preserves better localities. And the OS tree is generally based on the Z-curve. So to use SFC, the workflow is to, first, you compute the SFC for all of the inputs, and then you sort the inputs by their SFC, and finally, you split the input and build the index on it. The ZD tree on the LNX22 is the first parallel OS tree that's based on the Z-curve. The idea of the ZD tree is to simply parallelize every building blocks. For example, it parallel computes the SFC, it performs the sorting in parallel, and it recurs in parallel. Okay, so using the SFC makes sorting and updates in ZD tree cache efficient, and it can provide better update bounds than the PKD tree. However, using the SFC brings two drawbacks as well. The first one is that the pre-computing of the SFC introduces additional I/O costs for the whole process. And meanwhile, to use the SFC, you have to manually allocate a new array and associate the SFC code with the inputs. And this can increase the memory footprint for sorting and constructions. And as a result, using SFC makes the ZD tree twice slower than the PKD tree. Again, this is undesirable because the OS tree should provide better construction and update performance than the PKD tree. Well, it seems that the cost for the SFC is fixed as long as you use it. So in our design of the parallel OS tree, we avoid using the SFC at all and derive a new implementation of parallel OS tree based on two observations. Okay, the first observation is that since the OS tree divided space even at mid, so the tree structure is independent of input distribution. So in this case, we can easily build several levels of tree at once. And after that, the remaining task is to distribute the inputs to the corresponding subtrees. But if we just partition points level by level, it needs at least lambda times of writes, which introduce expensive I/O cost. So in our POS tree, we reduce this cost by using the technique called the parallel point sieving. For example, the point sieving will write the inputs directly to the corresponding subtree. And this reduces the number of the writes from lambda times per point to only once. And this is how we can save the I/O without using the spatial fitting curve. The detail of the parallel point sieving can be very complicated, but I believe this image better shows how it looks like. The small balls on the top are the points we need to partition, and the tables are lambda levels of tree we just built, and in the end, the points are forced into the corresponding subtrees. The idea of the point sieving is from the cache-efficient counting sort, and you can find more details in our paper. Okay, the algorithm for our POS tree is simple. For example, assume that we want to insert these grid points into the tree. What will we do? We first fetch lambda levels of tree, and then we sieve the points into the corresponding subtree, and finally, we recurse in parallel. And that's it, we are done. We want to note that the point sieving actually equivalent to perform the integer sort for the points, but without computing the SFC explicitly. And this is why it can be faster than the SFC-based approach. And meanwhile, remove the SFC enable our POS tree flexible to any coordinate types and ranges, rather than just stick to 2D or 3D integers. And most importantly, the POS tree has the same bounds as the ZD tree, but provide much better performance in the practice. Okay, to summarize, we remove the SFC and achieve a parallel OS tree with good performance. But if you really love the SFC and still want to use it anyway, we show in our parallel R tree how we can use it efficiently. Okay, first recall that the KD tree, unlike the KD tree and OS tree that splits space, the R tree groups points using different heuristics. And we are only aware of little work about parallel dynamic R trees. The early design of the R tree is incremental. This approach is simple and dynamic, but it's hard to generalize to parallel batch settings. And instead, most parallel R tree focus on either parallel query or the bulk loading. Well, how can one parallelize R trees? A promising way is to again use the spatial fitting curve, but this time we will use the Hilbert curve. And this is not a new idea. It was first proposed in the 1980s and later realized as a Hilbert R tree. But unfortunately, we find none of them have parallel implementation. Well, is there any parallel data structure to manage the integer sequences? The answer is yes, of course. It's a family of the P tree, specifically the PEC tree. The PEC tree is a self-balanced, parallel binary search tree which handles the imbalance using the tree rotation. The PEC tree uses leaf wrapping to achieve better space and I/O efficiency. For example, when the input has small size, it will be stored in a flat array within the PEC tree leaves. And the PEC tree is a so-called join-based framework to achieve high parallelism. And it supports full interface of the binary search tree, such as tree construction, batch updates, and different queries. And using PEC tree with SFC is very straightforward. First, you sort the input in parallel, and then you split the curve at the mid, and you do it recursively by finding the midpoint for the left and right branch recursively until we reach the base case. Okay. Well, everything good. It seems that the package tree provides an easy solution for parallel CR trees, right? For example, if you want to build a tree, you just call the build function in the package tree. If you want to make batch updates, you just call the update function in the package tree. And nice. Let's try it. We implemented this idea, but surprisingly find that if you directly use the package tree with a Hilbert curve, it would be up to 4 times slower than the PKD tree. Wait, what's going on here? Something must happen to make the package tree such slow, right? And we find there are 2 reasons. The first one is that the package tree keeps the total ordering for all of the points based on the SFC, including rows in leaves. So this means that if you want to insert a point into a leaf, you need to sort all of the points in that leaf, which is an expensive operation. But instead, we can leave points in leaves unsorted. For example, we can directly append the insertion to the end of the array. And this saves the time for the reordering during the updates. And besides, keep points in leaf sorted does not improve the query efficiency, because the points in a leaf generally share a common cache line and will be loaded to the cache during queries anyway. So to summarize, there is no need to keep the points in leaf sorted at all. And besides leaf ordering, the second reason to make the package tree slow is same as the ZD tree, where the computation of the spatial fitting curve matters. Okay, so to address these problems, we propose the aspect tree. It allows the points in leaves of the aspect tree unsorted and reorder them only when necessary. This requires you carefully redesign the drum-based framework, which can take some time. And to avoid the overhead of the SFC, the aspect tree will defer the SFC computation when the points are first touched during the sorting. So this reduces one round of the I/O. And besides, instead of sorting the code point pairs, the aspect tree will only sort the code ID pairs and use that ID to fetch the points when we allocate a leaf node. And this reduces the memory footprint since we not just use an integer ID to represent the whole point during the process. Okay, now we come to our experiments. So in this session, we show that different indexes can preserve their strengths in parallel and dynamic setting. For example, the R tree is fast in updates, and the KD tree is generally fast in queries. And we also show which use case is best suited to these indexes. Our experiments are performed on a machine with 96 cores. We use parallel for parallelism. We show results for 2 types of benchmark. The first one is uniform, where points are uniformly distributed. And the second one is warden, where points have very skewed distribution. Okay, for baselines, the PR tree is our parallel R tree, and the ZD tree is another one that is based on the Z curve. PKD tree is state-of-the-art parallel KD tree. Aspect tree is our parallel R tree using Hilbert curve. And we also include the serial R tree in Boost as a baseline for query. Okay, we first show the results for batch insertion. We test the time by constructing a tree using the incremental batch insertions. The final tree size is 1 billion, and low is better. Okay, the aspect tree is the fastest one among all of the baselines by minimizing the overhead of the SFC. Our parallel OS tree is faster than the ZD tree by removing the overhead of the SFC. Meanwhile, the POS tree is also faster than the PKD tree, since it's easier to compute the spatial mean than object median. And for queries, both POS tree and ZD tree, they are historical independent, so their query time is similar as the static case. And we also test the incremental batch insertion for real-world dataset, such as OpenStreetMap. And our parallel R tree is still the fastest one for all of the baselines. And meanwhile, as a R tree, it provides similar query performance as a highly optimized Boost R tree. For KD trees, maintaining the object median poses large overhead, so its update time is very slow. But the rewarding is that the KD tree is more balanced, so it can remain its advantages in queries. Okay. Next, we show the static tree construction and queries. The tree contains 1 billion 2D points in uniform distribution, and lower is better. Our parallel R tree is the fastest one for tree construction as well. The PL tree provides the fastest KN query for all of the baselines, even faster than the PKD tree. This is that because the PL tree has shallower tree height, and it provides better pruning efficiency by selecting 1 out of 4 subtrees. And for tree construction on skewed distribution, our parallel R tree remains the fastest one. But both POS tree and ZD tree, they are also trees. But the POS tree become much slower than the ZD tree in school distribution. The reason is that since the OS tree splits the spatial mid, so the tree height depends on the input distribution, which is very large if the inputs are not uniformly distributed. But the ZD tree uses the spatial filling curve to manage the points, and the time is dominated by the sorting, so it will not affected by the school distributions. Okay, so far we have seen many different spatial indexes. A quick question would be, how can we pick these trees when we need them? Right? Well, we have a lot of choices. Well, the answer is that all about the operations that we need. We plot this figure based on our experiments. The horizontal axis is update performance, and the vertical axis is the query performance, and higher is better. So for example, if the workloads are update heavy, then you should pick the parallel R tree. If the workloads are more balanced between the updates and the query, then the POS tree generally gives the best overall performance that you need, especially for non-school data. So note that this result is not the universal answer for all of these spatial indexes. We provide a one-page detailed evaluation table in our paper, so you can maybe check it out if you are interested. Okay, I'll stop here. Any questions?
Questions?
Great. Seems I can make everything clear.
All right, well then, thank you.
Thanks.
Break.
session on GPU and heterogeneous computing. My name is Frank Miele, NC State University. I'll be chairing this session. We'll start with the first talk, PRISM, that's going to be given by Zhidong Liu from the Chinese Academy of Sciences. So, Zhidong, go ahead.
Hello, everyone. My name is Zhidong Liu, and I am a co-first author of this paper. I'm from the Institute of Computing Technology, Chinese Academy of Science, working with Professor Ding Wentao's group. I'm honored to introduce our work, PRISM, an efficient GPU-based Lucy compression framework for progressive data retrieval with multi-leveled interpolation. All right, let's get started. With the rapid development of modern supercomputers such as Frontier and the AI competent, peak computing performance has entered an X-scale computing area. Under such massive computational powers, scientific simulations are generating enormous volumes of data and unpredictable rate. For example, the HARC cosmological simulation can produce tens of terabytes of data per second, while in reverse time migration, RTM, a single time step can generate up to 2,800 TB of data. This explosive data growth places tremendous pressures on both storage systems and network bandwidth. Error-bounding Lucy compression is a practical way to address this problem, and the GPU-based design are widely explored. For example, QZFP aimed for high throughput, while QSG High prioritize compression ratios, and the most existing compressors are non-progressive. That said, they are only work at one fixed precision. In real scientific workflow, the same data set is often reused by multiple downstream analysis, and each text may need a different precision. With a non-progressive compressor, you typically have two choices. One is compression once at high precision and compress once at a lower precision to satisfy all tasks, but this greatly reduces the achievable saving in storage and network cost. The second approach is compression and decompression separately per task at a task-specific precision. As a result, non-progressive compressors are hard to use in real-world scientific analysis pipeline. Another important use is progressive analysis. Progressive analysis is the researcher may first load lower precision data to quickly explore the dataset, then switch to higher precision to detailed analysis. With a non-progressive compressor, the first lower precision load becomes throwaway work. Once you need higher precision, you have to reload and redo, which is inefficient. And today, progressive decompression mainly follow two paths. The first approach is based on a residual framework. The compressor stores the residuals, the difference between the original data and the current reconstructed. Across multiple precision stages, user can load this stage incrementally to refine the result, but it has a clearly drawback. Each precision level depends on the previous one, which require multiple rounds of compression and decompression. And the second approach is embedded progressive, and its name is bitplane-based. This approach compresses the data once, and the user progressively fetch bitplane from most significant to less significant, guided by error-bounding rules. Okay, nevertheless, designing a compressor that supports progressive decompression is highly challenging. To enable progressive functionality, existing methods often introduce significant overhead. As shown in the table, non-existing Lucy compressor can achieve both high GPU throughput and high compression ratio at the same time. To address these challenges, we propose Pyrmont. Pyrmont is building upon two key design principles. First, it introduced a progressive data retrieval framework that supports both single-dimensional and multiple-dimensional interpolation. Second, it employs an enhanced lossless compressors tailored to the characteristic of bit plan. With these two core components, Pyrmont enables precision-based, high-throughput progressive decompression, while also achieving high compression ratio and reconstruction quality. Specifically, during compression, Pyrmont consists of pipeline including prediction, bit plan extraction, and lossless compression. Only the necessary, during the decompression, Pyrmont selectively load only the necessary bit plan according to the target precision requirement. And for our first model, the interpolation-based prediction, we aim to maximize both compression ratio and the reconstructed quality. To achieve this, we adopt a hybrid interpolation scheme that combines single-dimensional and multiple-dimensional interpolation. In simple terms, the predictor selects different spline function based on the number of available neighboring data points to predict the current point, as illustrated in the figure. And we first split the original data into 32 plus 32 blocks and initialize the block of vertex and anchor points. We then predict all points with each block using a progressively decreasing stride. After prediction, the difference between the predicted data and original data are quantified by dividing them twice the error bound, converting the original floating point value into integers. The second model is our unified data loading framework. Clearly, the prediction error from one step will propagate to subsequent steps, affecting the overall reconstructed error. Therefore, we partition the data into different error propagation layers, and for each layer, we load a different number of bit plan to ensure that the maximum error bound is satisfied. However, as shown in the figure on the left, we apply different prediction schemes to the same data set. The resulting error propagation layers differ. Despite this, we observe that the data points with the same stride also belong the same layer. Based on this observation, we adjust this propagation coefficients and transform the original level-based error propagation model into a layer-based error scheme. Okay, through these new data loaders, the hybrid prediction is successfully incorporated into the progressive compression framework. And the third model is bit plan extraction. In this stage, we employ register shuffling and byte permutation operation to efficiently transport this quantization code. As discussed earlier, the data is organized into different error propagation layers and is progressively reconstructed from the most significant bit plan to the least significant bit plan. We further used shared memory as an intermediate staging area to reorder right. Okay, and the transform the random introduced by aggregating bit plan to highly coalesced global memory access. Okay, this is the third model. And the final model is a dedicated lossless compression scheme. First, we transform the original two component representations into a sign absolute format. And this format will introduce a large number of leading zeros in the quantization code. Next, leveraging the fact that the bit plane contains many zeros, we design a fast and efficient zero-aware bit plane compression, ZBPC. The key steps are generate a bitmap to record the position of non-zero bytes and effectively eliminating all zero values, and recursively compress repeated bytes within the bitmap in a pyramid fashion. As shown in our results, ZBPC achieved the second highest compression ratio and the fastest throughput among various NVComp libraries. And we evaluate our two repetitive GPUs, H100 PCIe for data-centric workload and RTX 5090 for high-end single GPU environments. And with their corresponding CUDA version listed for reproducibility. And we used a diverse set of real scientific data sets, converting turbulence, convulsions, cosmology, and climate simulations across FP64 and FP32 precision. For baseline, we introduced the state-of-the-art GPU compression with different design goals, high throughput, high compression ratio, and the progressive capability. So the comparison reflects a realistic trade-off in progressive workload. This slide evaluates how much data needed to be retrieved in an end-to-end progressive analysis scenario. For a given error bound, lower byte write directly means less data movement, lower I/O cost. Across all datasets, Pyrmont consistently require the lowest data volume to reach the same error bound. Another important observation is the curve shape. Pyrmont shows smooth, continuously curved, while non-progressive compressor exhibiting clear staircase pattern. This indicates that Pyrmont can naturally support arbitrary error bounds rather than being limited to a few present precision levels. And here we measure compression and decompression throughput on GPUs on the H100 and RTX 5090. Pyrmont consistently delivers the highest throughput across dataset and error bounds. For example, on the pressure dataset at error bound at 1E-8, Pyrmont achieved 20 times higher throughput than HPMDR and still output throughput origin design like CoolZP2 and CoolZP by 2 to 3 times. More important, as the numbers of progressive refined steps increased, Pyrmont advantage became even larger, showing that the score were well with a real progressive workload, not just single-shot decompression. On the left, Pyrmont consistently achieved the highest PSNR at the same bit rate. On the right, we compare compression ratio under non-progressive setting, and Pyrmont matched or even surpassed CoolSC High, which is currently the highest compression ratio GPU compressor, which is supporting, while Pyrmont still supporting progressive retrieval. And this shows that Pyrmont does not sacrifice compression efficiency for progression. It still delivers both strong rate distribution and high compression ratios. And finally, we show qualitative visualization result. Even at 0.5% errors, the reconstructed field already present key structures and are suitable for scientific analysis. At 1% error, the results are nearly in distribution from the original data. This confirms that Pyrmont progressive reconstruction is not only efficient, but also visually and scientific meaningful, support real analysis workflow. Okay, thank you for everyone listening. Any question?
Questions? Let me walk up and.
Oh, okay, thanks for your inspiring lecture. And I have a question. I noticed that you use multi-dimensional interpolation as a predictor. And I also know that there is another compressor named QSC high, and you mentioned also. And so there's my question. What's the difference between your prints and the QSC high? Thank you.
Okay. In fact, we acknowledge that both approaches follow the same technological direction. But however, we introduce additional memory optimization that are not present in QSC high. And as a result, Prism achieve up to 2 times higher decompression throughput than QSC high. Thank you.
Anybody else? So I also had a question about QSC high. I think in the second to last slide, when you showed some results, there were a few cases where it actually outperformed Prism. Did you analyze why that is the case?
In this case?
Yeah, for example, in the QC cases.
GQC.
Temperature. There were a few cases where QSC high was better.
Oh,
right?
okay, okay.
Why?
At the higher error bounded, the Prism actually have a higher compression ratio, but because the QSC high is a non-progressive and the compression ratio is non-progressive and a high compression ratio compressors, and our work Prism have introduced some progressive scheme to even maintain the high compression ratio. So we still have a little gap in the lower error bounded than QSC high. Yes.
Thank you.
Okay, thank you.
All right, any other questions? Going once, going twice. If not, we'll go to the next talk.
Okay, thank you, everyone.
Let's thank the speaker again. So the next talk is dynamic detection of inefficient data mapping patterns in heterogeneous OpenMP applications. It's going to be given by Ali Janisari from Iowa State University. All right.
So good afternoon, everybody. Thank you, Frank, for the introduction. My name is Ali Janisari. As Frank mentions, I am the advisor of my students here for this paper, and I'm going to present. The first author is graduated. The second author cannot be here due to visa issues, so I'm going to present. So the core work here is dynamic detection of inefficient data mapping patterns, so-called, in OpenMP kernel on heterogeneous computing. Let's go on some background information. So you guys, everybody know, I guess, in PPoPP community and HPC community, that, yeah, heterogeneous computing, especially dedicated accelerators, general purpose GPUs are getting more and more important. So, and you can see on different clusters, every node, that you have those components. So how to make a benefit of that, it's sometimes challenging. And about 76% of total compute on top 500 in 224 came from accelerators in supercomputers. So that's a big amount. So that means programmers are trying to use some way to use GPUs more and more. But there are some challenges that we are going to talk about. The main thing is that the so-called data mapping between host and device. As you know, all data that we have is usually on host, and we have to offload it on GPU. This is sometimes costly, and the programmers will face different issues while debugging, while optimization. So the goal of this work was that can we help programmers with some tools that they can find, identify, and so-called have some remedy solution for these problems. So, and I guess everybody, probably most of the people know that what the reason would be that the G flops, the GPU flops is increasing usually 34% per year, whereby the interconnect is behind, is 20% per year. And of course, the interconnect latency is decreasing every year. That's because of amount of data that you have. 20% per year is decreasing. So, and that could be an underlying problem, so that how we can improve this data movement from hosts to devices. There are different ways that programmers use, okay? We have dedicated and specialized programming models for working on GPUs and accelerators. So, and you have probably used CUDA, OpenCL, but one of mainstream programming model that try to make things interesting in a way that you use simply, it's a simplified way of using kind of some directive to offload your kernel on GPUs, OpenMP. And OpenMP is standard and kind of, I would say, portable way to deal with multi-core and many-core, so-called accelerators. And it's really simple because you just need to insert a pragma, and that green line in this example. And then your code here is parallelized on multi-core, and here will be offloaded to GPUs. And of course, that's good because you can have one program write once, and hopefully you can deploy it on different GPUs from AMD to OpenMP to other kind of GPUs to hopefully get same performance. But it's not really so easy that you get same performance on different GPUs. So I have provided a simple example here. The example is Jacobian solvers that is a very known kernel that you can use for GPU offloading. So if you just simply use OpenMP and do it multi-threaded, so-called on a multi-core machine, you just simply add this, and you have a reduction and a for loop here. That's it. Nested for loop here is also a nested for loop. So if you do that, and you see that if it's a scale well, so from 1.4 to 16 GPU, you see that it's scaled, so it's good. But what will happen if you just offload it to GPU? Simply just you write the code for that, and you use OMP target teams distribute. So, and that's a directive that's come since OpenMP 4, if I'm correct. So that you can easily offload the kernel on GPUs, but do you expect also the same trend as you see here? You see not. That's not. So that means a GPU has many cores, so 500 or 5,000, depending on what kind of GPU you have. So you see that you will not get that. So what could be the reason? If you a little bit analyze this example, you can see that since we don't have explicit data mapping clauses in OpenMP, the compiler put the standard, the default one. So here we have an array of A and A new and an error value, so that we see that if when the kernel start will offload it, this data blocks, this matrix also will be uploaded. And that means we have a copy here from host to device, and again back from device to host here. Again, same here, since the programmer didn't write implicitly, this will happen by the programmer. You have again here a copy from host to device from A and A new, the matrix here, and again back here. That's costly. So what would be the solution? The solution is that hopefully you can have everything on the GPU, offload everything, do the work, post kernel, everything, and then at the end you copy back from device to host. So that means the solution is that what you do here, you just write, and that means you need to have experience. You need to profile your code. You need to have somewhat experience to just see how should I do data mapping. And if you do that, you can get a better result. So that means if I add as a programmer these blue lines and have explicit data mapping, not what compiler is giving, so I may get a better result. Yes, we can get really good, significant reduction in the runtime. So the goal is that we provide a tool, okay, so that it analyzes your code and then provide you some suggestion and some actionable things so that you can do on your code and your kernel. And hopefully you will get a kind of better speed up. So alternative, what would happen is you have a managed memory. Of course, it looks great. I don't need to deal about it as a programmer. So the managed memory will be done by either the runtime operating system or sometimes hardware and some drivers. So we have zero copy or unified memory that they are doing that automatically for you, or unified shared memory by OpenMP. So it's that there is no difference between CPU memory and GPU memory, so it will be done in a managed way. But usually, this is not so performant, and your program will suffer from overhead. So, and that's some generalizable solution that you can apply everywhere, but it's not really dedicated or specific to your kernel. So, as I mentioned, that's the problem of performance portability and the stability issue. So usually also having those managed memory into integrating into different compilers, different drivers, hardware is also costly for you. So it's not really feasible. That's why the OpenMP community and usually the programmers prefers to do this explicit management and kind of some hacking style, so-called, to just get best performance. So what tools are available? So there are some tools that can help you. So there is NVIDIA Insight, ComScribe, and Snoopy, so-called, that they visualize the data movement from host to device for you. There is also some other tools like Intel vTune or the AMD ROC profilers, so that you can have profiling with the source code. There is a roofline analyzer that also includes interconnect bandwidth, profiling with Intel, and some other also race detection, so focusing on correctness, like Arbalest or OpenSAN, which is static dynamic approach. But all of these tools are just kind of showing timing information to you, okay, with some visualization, but they don't show you or they don't suggest any optimization for you. So that means that's, as a user, I will see, but I have to do everything by myself and analyze and see what can I do. So the goal of our approach, which we call it OMP data perf, is that to identify those bottlenecks, so-called the inefficient data mapping patterns, and profile them, trace the timing, and also the source attribution. Then we provide some actionable feedback for the user, okay, so that it can see that, okay, and we can predict also how much speed up you could get. And that we do dynamically, okay, with low, approximately, I would say low overhead. That means you don't need to recompile. And also it's compiler and hardware agnostic. So that's what I'm going to present. So we are finding so far, we are finding 4 different so-called data mapping patterns that are inefficient. One is duplicate data transfer. So the name is saying, so the host send a value to GPU and then send the same value. That could be one problem. Around trip data transfer, that the host sends something to device, and the device send it back without reusing. And also repeated device memory allocation, so that you have a pointer on the host, and then you will allocate some space on the device, and you redo again the same thing. And sometimes also you map something from host to device, and you never use it. So these are all 4 different patterns that we try to find it. Of course, you can extend it that. So how we do that, I will just go very high level, but the code is open source, and also in the paper we have all details. So we provided 4 different algorithms for each of these categories, and you can extend it if you have anything more, or if you want to extend that code. So what we do a content-based detection. That means we measure timing of all kernels. So that means we measure the host pointer, device pointer, number of bytes, and all this information. Then we come up with some hashing mechanism so that to hash all these transfer in a chronological order. And we see that which one is more time consuming, which one is faster. In that way, we can sort the issues by so-called the performance impact. And we, of course, also provide some debugging information. Let me go and have one of these cases, the duplicate data transfer. One example here is that the array A. You can see that we do mapping array here, okay? So that means we transfer A twice, and we never read it, so it's not necessary. That's an issue that you will, if A is really big, then your program is suffering a lot. So that means we want to find that. So how we did it, the algorithm is detailed here, but what we do, just high level, I want to tell, so how we did one of them. So for each chronological data operation, we group the events with the same contents. That means same hash ID. Then each pair of events and distinction device is used as a key, so-called, and we report those if we find two events that they have the same key. And in that way, very high level, we can find so-called a duplication in the data transfer. We have other algorithms that you can see in the paper. Let's go and spend some time on so-called on the result. I think I have time, 3 minutes more. Oh, 2 minutes, and I have to be fast. So we analyzed 10 OpenMP kernels, including real-world applications with 3 different inputs, small, medium, large. So we run it on NVIDIA 800, okay? We use Clang 19, okay, with associated LLVM OpenMP runtime. So first of all, the overhead, I can say that's about 5%. So the largest application that we have, the largest overhead was from XS Bench with large input, 33%, and about 7 of 10 applications had less than 7% overhead. And the memory overhead was 72 bytes per each data transfer, so 24 for each target, and about average is about 155 megabytes per hour. You can see that the overhead is reasonable. Now, the prediction that we provide you, and we say that how much speed up you can gain by executing this kernel, we have an error of 14%. So we use some real-world data, real-world kernel, and we found some inefficiency into that. We could recover it. Sometimes we didn't, and we had some kernel that was perfectly parallelized, and so offloaded. We injected some synthetic issues, some artificial so-called errors, and we were able to detect. I just show here 2 case studies here. One, these are different types that we see. When writing this paper, and then we didn't find any paper or any tool that does this for OpenMP. For CUDA, there would be some, but we want to have for OpenMP, so we couldn't find. The closest thing that we found was Arbalest from Vivek Group. I think it was a C workshop 2 years back, so that they are more focusing on correctness, and so-called they have also UUM, use of uninitialized memory. So you can see that with this 5 application from Hackbench, we could find it, and we didn't find anything, and we checked it out. This is for kind of false positive what the related tool is giving. But applying this optimization, you can see that this is before optimization, after optimization. We got about 14% speed up, and we also reduced 99% of the data transfer. So that's something that you would say. Of course, our aim is that you should use the correctness tools like Arbalest, Vec, or other ones that you have got correctness main issue, but we focus on performance bottlenecks, so-called. We call it performance bug. So that means this together should be really helpful. Of course, our tool is open source. You can scan this code and get it, and we are also happy to collaborate with you. Some future stuff that we can do is we have some static analysis, so to just try to reduce the instrumentation overhead. Then we do causal profiling for some asynchronous transfer, and of course, we're using LLMs and AI largely in our code analysis. We had already 2 papers this year, Autopower LLM and Contrap. Autopower LLM was in Knuckle, so we use OpenMP parallelization, and we could beat some of the current I would say, compilers. And contrast is also offloading and some extension of that, which was this year at ICS. So we are going to have now, for some of these inefficient patterns, we can maybe hopefully use LLM and AI to make a hybrid approach. Thank you. Questions? Hope I am on time.
Questions? We got time. Don't be shy. Yep.
Oh, small question. I think this was very interesting. I just wonder, do you consider further extended to multi-GPUs? Because I think multi-GPU is more common in future, I think.
So the question, if I understand, if we are going to extend it to micro GPUs?
Multiple.
Multiple GPUs, oh, okay. Multiple, of course. So this is now what we did for single GPU, but definitely that's also one plan that we want to have for multiple GPUs. Yeah. And that would be a really interesting way of to have.
How hard it is?
How hard is it?
Yeah.
That depends. So if you want to have multi-node GPUs, then you bring MPIs into game. So that means you have to see that you have to multi-nodes first on each node. So you have to bring MPI. But I mean, now what we did
sorry,
is...
I don't mean multi-node is like single nodes. It's rather common that you have multiple GPUs.
So
like NVLink, yeah.
So, I mean, in our experiment, if I correctly understood that what we did here is NVIDIA 800, okay, that we did, and we definitely can do it for, we should be, I think, I don't know, we have done some result, we're going to extend that for multiple GPUs on one single node, you are saying. Yeah, that I think we have done some experiment, we are extending the work to that.
Because I think it'd be very interesting because you not only detect if the data is in GPU or not, you also detect in which GPU.
Correct.
Yeah.
Yeah. That would, of course, make the problem somewhat more complex, but it's really interesting way to research. Thank you for the great question.
Any other questions? So I had one for you. Why constrain yourself to memory movement? I mean, you could certainly look into other GPU optimizations and say if you want to utilize shared memory, there could be additional OpenMP actually existing features that you investigate if you could use that on some of the data on the algorithms. Of course, it would require an analysis also.
Yeah.
Have you thought to go into this direction? And it's a huge extension for the tool, but what would it take?
So you are saying that we are focusing now on offload target and why we are not applying to regular other OpenMP clauses that are common for multi-core and usual. So of course, task or there's other clauses that you have, OpenMP tasking, for example, they're all interesting, but each of these would need some, I would say, work. But you have to also profile, you have to extend the algorithm. But our interest was now only just to see what we can do on GPUs. As I mentioned, the first part, 76% of all speed up coming from accelerator on top 500 supercomputers. So we were focusing, but you're right, that's some of them may be applicable, so we can reuse that also for even just regular OpenMP clauses.
All right, let's thank the speaker again.
Thank you.
All right, so the third talk in this session is root down exposure for maximal click enumeration on GPUs. The talk will be given by Zhe Pan. He's at Tsinghua University.
Sorry, this slide they cannot.
Oh, okay, thanks. Hello, everyone. My name is Zhe Pan from Tsinghua University. Today, I'd like to share our work about graph algorithm, the maximal click enumeration on GPUs, and with a novel load balancing approach known as the root down exposure. And here is the outline. First, I will introduce what the MCE problem is, and then I will introduce the baseline MCE solutions and analysis the challenges about in it about the load imbalance and memory pressure. And next, I will show our solution RDMCE with 3 key techniques, and finally, I will evaluate it. And first, what is the maximal click enumeration? In an undirected graph, a click is a complete subgraph in which every 2 distinct vertices are connected. And the maximal click is a special click that cannot be further enlarged to form a large click. And the MCE problem is to enumerate all maximal clicks in the graph. For example, in the graph G, it has only 4 maximal clicks, and it has many applications such as social network analysis and bioinformatics and computer vision. And the most state-of-the-art MCE algorithm follows the BK framework, which recursively expands the current click R using the candidate P and use the X to check the maximality. And the current work uses the GPUs to accelerate MCE because the GPU's massive parallelism enables high throughput. And the GPU-based MCE solutions is more faster than the CPU-based solutions. However, the MCE problems has many unbalanced trees, such as in the right pictures, the search trees are imbalanced. So the imbalanced tree will cause the severe load imbalance, and it will bring the significant synchronization overhead from the busy workers. They should pause into to share work. And here we summarize the existing load imbalance strategies for the GPU-based graph mining. First, let's see the left picture. It's the host-driven chunking approach, which partitions the entire graph into subgraphs on the CPU side, and then stream these subgraphs into the GPUs once at a time. And then they process the subgraphs in GPUs in a BFS manner. And the second one is the peer-to-peer handoff. In this approach, busy workers periodically check the idle peers during this enumeration. And once the idle peers are found, they will split these works and transfer sub-works to the idle peers, so the idle peers can work together. And the third one is just use a global queue. And in this approach, the workers will identify the heavy workloads and then break them into the global shared queue, and so others can process it. And however, all these strategies share a common problem. They force the busy workers to shoulder the balancing cost. Here, we should highlight the unique challenges of the MCE problem compared to the other graph algorithm. For example, unlike BFS or SSSP, which this graph analysis algorithm, whose workload scales linearly with the number of vertices. However, in the MCE work, the workload scale exponential with the number of vertices because it has exponential number of vertices tree nodes in its search space. And compared to the graph pattern mining problem, the
because this pattern only has vertices smaller than 10 vertices. For example, for the triangle county problem, the pattern only has 3 vertices, so the search tree has the maximum depth of 3. But in the MCE problem, because the maximal click can contain hundreds of vertices, so its search tree is more imbalanced, and the depths can reach 100. And so it resolves the challenges for GPU parallelization, include the severe load imbalance and the memory pressure. First, I'd like to show the load imbalance in the existing strategy. The first one will repeat the data transfer because the CPU will transfer the subgraphs to GPUs. For the other 2 approaches, they should force the BZ workers to shoulder the balanced cost. For example, in the second approach, the BZ workers should check whether it have the idle workers, and if it will split its work and transfer sub work to the idle part. So it will force the workers to shoulder the balance cost. And the next challenge is about the memory pressure. We should pre-allocate memory on GPUs before enumeration because dynamically allocated memory on GPUs are expensive. And we need to require multiple blocks of memories because we need to execute multiple MCE procedures in parallel. What's worse, the state-of-art always use the additional memory blocks, such as the task queue or the buffers for memory copy. It will waste the limited memory. And how to solve this problem? First, we propose a technique known as the root down exposure to solve the load imbalance problem. And our design principle is only expose work, don't transfer it, and let the idle work pull task without interrupting busy ones. And we only need to add 2 variables on the existing framework. The first one is a pointer, and the second one is just a counter. The pointer always points to the root node, and the counter always shows how the remaining works in the root node. And in the idle side, the workers atomically fetch the candidates. And in the busy side, when the counter reaches 0, it will move the pointer deeper in the DFS stack and continue enumeration uninterrupted. For example, in the right, this is the sub tree, and the DFS stack. For example, this is a subtree, and this is a DFS stack. And at the beginning, this pointer will point to the root node, and we have 2 other subtrees induced by the node G and the node K, so the counter is 2. And a new worker, idle worker comes, it will find that this root node has the remaining work, and it will pour the node K into its DFS stack, and the counter will -1. And when the counter reaches 0, it will put the root pointer down and point to this node, and then it will automatically balance the workloads. And there are 3 main benefits. The first is this approach eliminates the synchronization overhead with no pausing, because the BZ workers only to set the root node pointer, and the idle workers will automatically pour its workload. And the second is remove the extra memory buffers. And the third is this approach always chooses the most promising node for splitting, because the root node always have more candidates, and so it always works efficiently. And one main takeaway is that we should not we should only export a reference to the workload, and rather than transfer the workload itself. And then is our second design is about bitmap-centric MCE schema. In this schema, we simplify the memory layout and accelerate computation through the bitmap encoding. And our memory layout include a global graph compacted as a CSR format. And for each workers, we just store a subgraph encoded by the bitmaps. And each worker has a DFS stack. Contains bitmap triples, R, P, and VP. And we just encode the subgraph once per worker into a bitmap. Other workers directly reuse the busy workers bitmap. For example, we do not need to copy the bitmap because the busy workers and the other workers will share the same subgraphs, and it can just access this subgraph and without copy. And no extra data movement is needed during the load balancing. And the benefit is that we do not need to copy the subgraph, and eliminate the memory overhead while preserving the fast bitwise computation. And the third approach is aggressive node generation. And we just add multiple vertices at once, skip the intermediate nodes when possible. Because the vertices connect to all candidates belongs to every maximal click in the branch can be added to the current click together. For example, in the right, when we reach the vertex A, and we say vertex B, C, D, E all connect with the others, so we can just expand the vertex A with B, C, D, E, and get a click A, B, C, D, E, but not as this, just put one vertex once at a time. And this idea is easy, and it eliminates many intermediate nodes like this, and just one node. And that can accelerate the traversal with the minimal added computation. And here is our evaluation of RDM MCE. We compared with all the recent baselines, and for all 12 data sets, it is the only GPU solutions that can complete all 12 real-world data sets, achieving a great speed up over the next best solutions. And others will fail by the memory problem because of their fail memory allocation strategy. And this is the breakdown. We test both of our three key techniques. And this is the sensitive analysis. It tells how to choose when to share the workload. And we test it on the different GPUs, and we test it on the multiple GPUs. And that's all. Any questions?
Questions? Nobody has any questions? Crystal clear? Everybody understood all the results? The results were rather fast. They went by me, actually, the last ones. What were you, I mean, you were looking at multiple GPUs. If you go back one, what were the main lessons learned from these results slides? Maybe you can spend a little bit more time on it. No, it's the final one with the 4 different graphs. You have the slide with four result graphs. It had
4 result graphs.
GPUs and different SMs and all of that, right?
Oh yeah, different SM.
Okay.
This slide.
Yeah.
Oh.
So let us pause over here. Do you want to summarize maybe quickly what the contributions were? So in terms of scaling for SMs, what did you find?
Because the select of, for example, we can use more warps per swim to expand our parallelism. But if we have more warps per SM, and each workers will have allocate more registers, and so we cannot always expand this value. And so for all test case, it seems like a U shape. And when this number grows from the small number to the big number, it will reach the lowest place. It is the has the shortest time. So we chose this value. And the others, for example, for the tau, this tau in our paper, it shows when to expose the when to enable our root down exposure mechanism, and it works in the same way. And others is on different GPUs, and others is on the multiple GPUs. And
yeah, one other question I had for you is you were using atomics to actually fetch. Oh no, were you using atomics to fetch the next subgraph or the next node in the subgraph?
Yeah.
Okay, so that means you're actually working out of the HBM or the DRAM, depending on which architecture you're using. Have you looked into maybe using SRAM, basically the
SRAM?
Yeah, the shared memory.
Oh, shared memory. Oh.
I mean, you can only do it for a subset, but maybe that gives you some speed-up benefits. Did you look into it?
In this version, we just store all the things in the global memory and just use the shared memory for accelerate some operations, like the set intersections. Maybe it will be a future work to gain the further acceleration.
Okay, let's thank the speaker again.
Thanks.
Do we have a speaker for the final paper? Okay. All right, the final paper in the session is Rome, maximizing GPU efficiency for all pairs shortest path via taming fine-grained irregularities. It's going to be given by Weili Luo, and he's at Hong Kong University of Sciences and Technology.
Hello everyone, I'm glad to share my work. Rome maximizing GPU efficiency of all pair shortest path via taming fine-grained irregularity. My name is Weili Luo from the Hong Kong University of Science and Technology, Guangzhou. This is the outline of our presentation. First, we start from the preliminaries of all pair shortest path, and then I will analyze the challenges of partition-based APSP on GPU, and I will move to the ROM, our solution, and the evaluation and the conclusion. At first, the most important concept is the path relaxation. We relax the distance ij by using k as an intermediate vertex. And the second important concept is the semi-ring matrix multiplication. And C is generalized matrix product of A and B. Each element Cij is the semi-ring summation over K of the product Aik and Bkj. In the topical semi-ring, the O plus is the mean operation, and the O times is the plus operation. So the SR gene becomes relaxation operation. Cij is the minimum over K of the summation Aik and Bkj. This is a very important famous algorithm in APSP, Floyd-Warshall algorithm. It has 3 loops, and we need to relax each ij by every k, but it has a poor locality. How to improve the locality? We can block the distance matrix. There are 3 phases for each diagonal block. The first is the diagonal update. This is a Floyd-Warshall operation. And then we perform the panel update. They are the SR gene. And the third, the orange zone, is the outer product update. They are also SR gene. And now we perform the we perform 3 phase for the first diagonal block, then we perform the second, and then the third. So we can finish the block Floyd-Warshall algorithm. Supernodal FW is a permixing method for the APSP because it can save a lot of work. So it partitions graph to reduce the asymptotic cost. Here is an example. S6 separate the S0, S1, S2, and S3, 4, 5. And S2 separate S0 and S1. So in the elimination tree, S6 is the root, and S2 is the descendant of S6, and S2 is the ancestor of S0 and S1. Then we have this E tree. We can reorder the vertices via a post-order traversal of the E tree. So this is the reorder distance matrix. So at last, we can process the E tree from the bottom to the top by the block FW. For example, let's S0 as an example. We need to perform the D00 for the diagonal update, and the panel update, we only need to update D02 and D06. These areas are empty, so we can ignore them. So the structure sparsity saves the work. But the super FW on GPU has some challenges. We summarize 3 irregularities. The first is the granularity irregularity. In different level, it has different number of the operation. They are very, the number is very large, and they are very different. Most tasks are individually too small to utilize the GPU efficiently, and the high volume of GPU invocation introduced the significant launch overhead. And the second irregularity is the shape irregularity. Here is a case study of a graph. This is the supernodal size, and this is the SR genes dimension in phase 3 outer product phase. And this shape irregularity cause computational load imbalance. And it also develop memory access regularity. And the third irregularity is the dependency irregularity. We use the E3 level 2 as example. Level 2 has S2 and S5. So we need to perform update for D22 and D55, and the panel update of D22 and D55, they are independent. And however, both D22 and D55 need to update D66 in the outer product phase. So there is conflict. As the E3 becomes deeper, the number of conflicts is that there are more conflict. So our solution has 3 key ideas. The first is the workload aggregation. The second is optimized kernels design, and the third is async scheduling. For the workload aggregation, we design merge engine for 3 cases. The first is descendant panel update. For example, this is a descendant panel update. And the second is the descendant outer product. And the third is the ancestor descendant outer product. And then we also design a batch and tie engine for 4 cases. The first is smaller diagonal updates. The second is unmergeable panels. And the third is conflict blocks. And the fourth is residual small tasks. This is the overview of our workload aggregation. We need to process from the bottom level 3 to the top, and we use the merge engine first, then we use the batch and tie engine. So we get a lot of batch. Maybe some of them have a lot of ties. So there are 0 batch. There are different types of batch. We need to design some optimized kernel for each batch. So we tire GPU execution model per task. For example, the batch SR gene, we make each CTA is responsible for 1 batch time. For example, this is 1 batch tire from the BTE. Then at last, we design async scheduling. It has 3 CUDA streams for the kernel with different types. For example, a conflict stream, batch stream, and a large stream. And we also overlap the host and the GPU workflow. For example, the ME and BTE in this June is prepare work for the phase 2. But at the same time, the GPU also is processing work for the phase 1, so they are overlapped. We evaluate our work in 8 RTS 4090 and 2 CPU, AMD 7402, And the data set we use have a lot of have a lot of graph with different structure. And the baseline is Super FW. This is the CPU method and configured by 32 threads. And we compare the end-to-end time. And the second is the crew graph. This is the batch single source shortest path solver. And the third is fast APSP. And it is also a partition-based APSP algorithm. And the GPU method, we use the GPU workflow time. This is the results. Compared to the CPU baseline, Rome achieved end-to-end speed up ranging from 15 to 244 times. And compared with the GPU baseline, the speed ups ranging from the 11 times to more than 1,000 times. This is the ablation study. We can see this is the execution time. We can see the ME, merge engine, and batched entire engine play an important role in our solution. And all components ablation is the naive Super FW on GPU. We can see ROM achieve a significant speed up compared to Super FW naive version. At last, let me do a conclusion. The partition-based APSP algorithm on GPU has some problem. The irregularity causes extremely low GPU efficiency. So our solution, ROM, we structure workload and use an async pipeline to maximize throughput. The results achieves significant speed up than the existing baseline. Thank you for listening.
Any questions? Can you go back to slide 19?
19.
Yeah. So I was wondering, in cuGraph, you're using only one GPU, and then in fast ASP, it's 8 GPUs. Why the difference?
The fast APSP is designed for multiple GPU, and the original version of fast APSP implementation has more than hundreds of GPU. But the cuGraph, the advantage is it is a single source shortest path solver, and it has the lower complexity. So we don't need to implement the cuGraph to a lot of GPU because the communication will have a very large overhead.
Oh, did you try that, and did you get negative results, or are you just saying that?
Not yet, but maybe.
Okay, but in the next slide, when you have the results, so it's 1 GPU for one and then 8 GPUs for the other when you compare. But for Rome, it's always 8 GPUs, right?
No, Rome is single GPU.
Oh, okay. Thanks for that clarification. I missed that. Okay. Any other questions? Okay, so let's thank all the speakers actually again. Oh, wait. There's one question.
So I see you are comparing the result to the CPU.
Yeah.
Basically, the baseline is CPU, so you wrote a GPU kernel and you compare that to CPU, right?
No.
Oh, baseline is also a GPU implementation.
We compare with the CPU is the end-to-end time of the CPU version and the ROM end-to-end time. It includes the data transfer, the E3 build, and the kernel time. Yeah, end-to-end time.
Okay, I see. I also noticed that you implement on AMD, right? Do you have any specific implementation on AMD compared to NVIDIA GPU?
Not yet.
Okay, I see.
Sorry.
Sorry, too detailed question. Thank you.
Yeah, thank you for your question.
Last calls? No takers? Okay. So let's thank all the speakers again. Thank you. And
yeah, thank you.
That concludes the session and for today also PPoPP.
Okay, so sessions are over, but I like to welcome everybody to the business meeting, which is going to happen on the upstairs. So after a break, 20 minutes break. So there will be a session, chair report, as well as best paper, our announcement. So I welcome everybody.